Tonight we're checking a very old signal, a faint background hum that fills all of space. Astronomers call it the cosmic microwave background, the CMB, and they treat it less like a mysterious omen and more like a carefully archived data set, full of maps and tables and graphs. It's simply the oldest light we can see, stretched out and cooled down over billions of years, waiting to be read like a long, slightly noisy report about how the universe began. There's nothing dramatic about it on the surface, just a persistent glow that's been travelling for so long that it's become part of the furniture of existence itself. But if you look at it closely enough, with the right instruments and enough patience, it tells you almost everything worth knowing about the early universe. The story begins shortly after the Big Bang, when the universe was hot and dense and filled with a mixture of photons, particles of light, along with electrons and atomic nuclei. Everything was packed together so tightly that light couldn't travel far before bumping into something. The photons kept scattering off free electrons, bouncing around constantly like someone trying to walk through a crowded room in the dark. The universe was like a thick fog where light existed everywhere, but couldn't move in a straight line. You could think of it as being trapped in a glowing opaque soup, where every direction looked the same because nothing could see more than a tiny distance. The CMB existed then as trapped energy, part of that uniform brightness, unable to escape or travel freely. As the universe expanded, it cooled. That's just what happens when space gets bigger. The energy spreads out, temperatures drop, and things that were once too hot to settle down finally get a chance to organise themselves. Eventually, the universe reached a temperature where electrons could bind with nuclei to form neutral atoms, mostly hydrogen and helium. This process is called recombination, though that's a bit of a misnomer since the electrons and nuclei had never been combined before, but the name stuck. And what matters is that once recombination happened, most of those free electrons that had been scattering light were suddenly locked up inside atoms. Without all those free electrons in the way, photons could travel much farther without being deflected. The universe transitioned from opaque to transparent, not with a dramatic flash or sudden clearing, but with a gradual lifting of the cosmic fog. It's not that the light turned on, it's that the obstruction finally moved out of the way. The moment when this happened is called the surface of last scattering, which sounds technical, but just means the last time most of the CMB photons interacted strongly with matter. After recombination, these photons began streaming freely through space in all directions, and they've been travelling ever since. The light we see today as the CMB is essentially a snapshot of that moment, preserved and carried forward as the universe expanded around it. It's not a picture taken by a camera, but a fossil glow originating when the universe was around 380,000 years old. Very young compared to its current age of nearly 14 billion years. Imagine taking a photograph of a room, and then watching that photograph age while the room itself continues to change. The CMB is like that photograph, except the room is the entire universe, and the photograph is made of light. Here's where things get interesting in a quiet, technical way. The photons released at last scattering started out in the visible or infrared range, glowing with the kind of light you might expect from something extremely hot. But as space expanded, it stretched the wavelength of the light itself. This isn't some metaphorical stretching, it's a real physical effect. As the fabric of space expands, it pulls the wavelengths along with it, making them longer and longer. Longer wavelengths mean lower energy, so over billions of years, those originally bright photons have been stretched into microwaves. Today, they correspond to a temperature of about 2.7 degrees above absolute zero. The photons didn't lose heat in the way a cup of coffee cools down by transferring energy to its surroundings. They cooled because the space carrying them grew larger, diluting their energy across a bigger volume. The discovery of the CMB was almost accidental, in the way many important discoveries are. Two engineers, Arno Penzias and Robert Wilson, were working with a radio antenna in New Jersey in the 1960s, trying to use it for satellite communications. They kept picking up a persistent noise they couldn't eliminate. It didn't matter what time of day it was, what season, or how much they cleaned the equipment, even scrubbing out the pigeon droppings that had accumulated in the antenna. The noise remained, a faint hiss coming from every direction in the sky. At first it was just annoying, the kind of problem you'd expect to solve with better shielding or by repositioning the antenna. Only later did they learn, after consulting with physicists, that they were picking up microwaves from the cosmic background itself. This annoying static turned out to be the universe's oldest, most widespread signal, a discovery made as much by troubleshooting as by grand theoretical design. Once scientists realized what they were looking at, they measured the CMB more precisely and found something remarkable. The spectrum of the radiation, the way its intensity varies with wavelength, matched almost perfectly with what's called a blackbody spectrum. A blackbody is a theoretical object that absorbs all radiation falling on it and emits radiation in a specific pattern depending only on its temperature. Real objects approximate this behaviour to varying degrees, but the CMB turned out to be one of the most perfect blackbodies ever measured. Its temperature was about 2.7 Kelvin, and the smoothness of the spectrum across the sky was striking. This near-perfect blackbody curve confirmed that the early universe was once hot, dense, and extraordinarily uniform. In the scientific logbook, it became one of the cleanest entries. Background temperature around 2.7 Kelvin, blackbody-like, consistent with a hot Big Bang. By the late 20th century, scientists wanted better measurements. The Cosmic Background Explorer satellite, known as COBE, launched in 1989 with two major tasks. First, confirm the blackbody spectrum with high precision. Second, look for tiny variations in temperature across the sky. The spectrum measurement went extremely well, matching theoretical predictions so closely that it was almost eerie. The temperature map, though, was more challenging. At first, the sky looked almost perfectly uniform, with only a few large-scale features visible. One of these was a dipole pattern, a slight warming in one direction and cooling in the opposite direction, caused by our own motion through space. The Milky Way and the local group of galaxies are moving relative to the rest frame defined by the CMB, and this motion creates a Doppler shift that shows up as a temperature difference. Useful information, but not what cosmologists were most excited about. After subtracting the effects of our local motion and emissions from our own galaxy, COBE revealed something more subtle. Small temperature fluctuations in the CMB at the level of tens of microkelvin. These tiny ripples represented regions that were slightly denser or less dense in the early universe. If the universe had been perfectly uniform, gravity would have had nothing to work with, no seeds to grow into the galaxies and clusters we see today. But these small imperfections gave gravity something to grab onto. Over time, the denser regions attracted more matter, while the less dense regions became voids. Visually, the map looked like a mottled pattern of slightly warmer and cooler spots. Nothing dramatic to the untrained eye, but scientifically it was incredibly rich. It was the first clear indication that the early universe carried just enough structure, just enough departure from perfect smoothness, to eventually form the cosmic web of galaxies we observe. The next step in refining these measurements came with the Wilkinson Microwave Anisotropy Probe, WMAP, which launched in 2001. WMAP provided much higher resolution than COBE and collected data over several years, building up a detailed, high-quality map of the entire sky. The result was a pixelated temperature map where each pixel represented a small patch of sky, and carried a value indicating how much warmer or cooler that region was compared to the average. From these patterns, cosmologists could extract statistical information about the universe's age, composition, and geometry. The era of precision cosmology had arrived, moving beyond simple detection into careful parameter estimation. Then came Planck, launched by the European Space Agency in 2009. Planck was even more sensitive and observed the CMB at multiple frequencies, which allowed scientists to carefully separate the true cosmic background from foreground emissions like dust and gas in our own galaxy. The final Planck maps show an intricate pattern of fluctuations, each tiny colour difference corresponding to a small temperature variation of just a few hundred microkelvin. To the eye, when you see these maps in popular science articles, they look like colourful ovals with splotches of red, blue and yellow. To cosmologists, they're dense datasets from which you can extract power spectra, a compact, mathematically precise way of summarising the pattern of fluctuations across different angular scales. Planck's results refined the values of key cosmological parameters with impressive precision, narrowing down uncertainties that had been much larger just a decade before. Understanding how scientists convert a complex sky map into useful numbers requires a bit of explanation, but it's not as abstract as it sounds. Imagine you have a photograph of a textured surface, maybe a close-up of fabric or a section of wall. You could describe that texture in words, but a more precise way would be to measure how much the brightness varies at different scales. Are there large patches of similar colour, or is the variation mostly at small scales? The CMB analysis works the same way. Scientists compute what's called a power spectrum, which is essentially a graph showing how strong the temperature fluctuations are at different angular scales across the sky. These scales are labelled by something called the multipole number, which is just a way of quantifying the size of features. Low multipole numbers correspond to large-scale features spanning big chunks of the sky, while high multipole numbers correspond to small-scale features. The power spectrum is where the real information lives. It's not that every individual pixel on the sky map is unimportant, each one represents a real measurement, but the overall pattern is what tells you about the physics. The spectrum has peaks and troughs, and these aren't random. They reflect physical processes that were happening in the early universe, specifically acoustic waves in the hot plasma. Before recombination, the universe was filled with this plasma of photons, electrons and nuclei, and it behaved somewhat like a fluid. Regions of higher density would attract more matter through gravity, but the pressure from all those packed-in photons and particles would push back. This created oscillations, sound waves travelling through the plasma, with regions alternately compressing and expanding. When recombination happened and the photons decoupled from the matter, these oscillations were effectively frozen in place, leaving an imprint in the CMB as a pattern of slightly hotter and cooler spots. What were, once travelling sound waves became a static temperature map, like recording a song and then analysing its waveform long after the music has stopped playing. The positions and heights of the peaks in the power spectrum depend on several key parameters. The first peak, for instance, is sensitive to the total density of matter and energy in the universe, and to the curvature of space itself. If space is flat, the peak appears at a certain position. If space has positive or negative curvature, the peak shifts. The second and third peaks tell you about the balance between ordinary matter and dark matter, and about the physical conditions in the plasma, like how much pressure the photons were exerting. By fitting theoretical models to the observed power spectrum, scientists can infer the best fit values for things like the Hubble constant, the density of dark matter, the density of ordinary matter, the amount of dark energy, and the age of the universe. It's an inverse problem. You observe the pattern and work backward to figure out what combination of parameters would produce that pattern. The numbers that come out of this process are impressively precise. The universe is approximately 13.8 billion years old. About 68% of its total energy content is dark energy, 27% is dark matter, and only about 5% is the ordinary matter that makes up stars, planets, and people. Space appears to be flat or very close to it. Within the measurement uncertainties, these aren't wild guesses. They're constrained by the detailed shape of the power spectrum and by the consistency of the data with theoretical predictions. In the logbook, the CMB allows scientists to fill in a detailed summary, numbers extracted from analysing a faint hum. It's worth pausing to appreciate that the peaks in the power spectrum represent frozen sound waves. Before recombination, the universe was filled with plasma oscillating under the competing influences of gravity and radiation pressure. Dense regions would collapse inward due to gravity, but the pressure from tightly packed photons would resist and push back, causing the region to expand again. This created oscillations at different scales, with some regions going through one full cycle of compression and expansion, others going through 2 cycles, and so on. When recombination occurred, the photons suddenly streamed away, and the matter was left behind in whatever configuration it happened to be in at that moment. The CMB carries the imprint of those oscillations because the photons that decoupled from denser, hotter regions have slightly higher energy, and thus appear slightly warmer, than photons from less dense, cooler regions. Sound converted into a temperature map, a record of vibrations that happened nearly 14 billion years ago. Of course, the CMB signal isn't the only thing present in the microwave sky, and extracting the true cosmic background from everything else is a major challenge. Our own galaxy emits radiation at microwave frequencies, mostly from dust grains and electrons spiraling in magnetic fields. There are also point sources like distant galaxies and quasars. Missions like WMAP and Planck observe at multiple frequencies to distinguish the CMB from these foregrounds, since different physical processes have different spectral signatures. For example, dust emission has a spectrum that rises steeply at shorter wavelengths, while the CMB has its characteristic black body shape. By comparing observations at different frequencies, you can model and subtract the foreground contributions. Data processing also involves masking regions where the foreground contamination is too strong, like the plane of the Milky Way, and carefully assessing noise from the instruments themselves. The beautiful CMB maps you see in publications are the result of extensive, methodical cleaning, much like editing a long report for clarity, by removing extraneous details and focusing on the core information. The CMB doesn't stand alone as a source of cosmological information. Its parameter estimates can be compared with other independent measurements. Galaxy surveys map the large-scale structure of the universe and provide constraints on dark matter and dark energy through patterns like baryon acoustic oscillations, which are essentially the grown-up version of those early sound waves. Observations of distant supernovae measure the expansion history of the universe and the effects of dark energy. Measurements of gravitational lensing reveal how matter is distributed. The fact that these independent methods largely agree strengthens confidence in the standard cosmological model, often called lambda CDM, where lambda represents dark energy and CDM stands for cold, dark matter. Where there are tensions, like the current discrepancy between different measurements of the Hubble constant, they become topics of careful investigation. The CMB's role in all this is to act as a baseline, a set of early universe conditions that any viable theory must respect. There's also information in the polarization of the CMB light. Polarization refers to the orientation of the light waves, a property that can carry additional clues about how the light was scattered in the early universe. When photons scatter off electrons, they can become polarized depending on the geometry of the scattering. The CMB has two types of polarization patterns, called E modes and B modes. E modes are relatively easy to detect and provide additional constraints on cosmological parameters. B modes are much more subtle and can be produced by gravitational waves from the inflationary epoch, the brief period of exponential expansion thought to have occurred in the universe's first fraction of a second. Detecting primordial B modes would be a major discovery, offering direct evidence of inflation, but the signal is so faint that it requires extremely sensitive instruments and careful control of systematic errors. These polarization measurements add extra columns to the data set, refining our understanding of what happened in those earliest moments. It's important to remember that the CMB is not something that happened once and then ended. It's always present, bathing the universe in a faint microwave glow. If you built a perfect microwave detector and pointed it at any patch of sky far from bright sources, you would pick up this signal. It doesn't turn on or off, it's simply part of the environment, a constant low-level background tone. Our instruments sample it, map it, and reanalyze it with new techniques as technology improves, but the signal itself remains stable. For someone drifting off to the sound of rain and a black screen, the thought is almost soothing. While life goes on in one small corner of space, a very old light continues to travel, carrying a record of the universe's early days. It's been travelling for so long that its journey spans most of the history of the universe itself, and yet it's still here, still detectable, still quietly providing information. Closing out tonight's quality control check, the CMB has passed every major test of consistency with our best cosmological models. Its detailed structure has given us a clear, if incomplete, picture of the universe's birth and composition. The data may look like maps, graphs, and power spectra, technical outputs from satellites and ground-based telescopes, but behind those shapes is a single, ancient glow. When you strip away all the jargon and the mathematical formalism, what you're left with is light from a time when the universe was young, smooth, and just beginning to develop the structure that would eventually become galaxies, stars, and planets. That light has been stretched and cooled by the expansion of space, but it hasn't disappeared. It's still there, filling the universe, waiting to be measured by anyone with the right equipment and enough patience. The process of studying the CMB is methodical and cumulative. Each mission builds on the work of previous ones, improving resolution, reducing noise, and refining parameter estimates. COBE gave us the first clear detection of fluctuations. WMAP turned those fuzzy patches into a detailed map and extracted precise cosmological parameters. Planck pushed the measurements to even higher precision and explored polarization more thoroughly. Future missions and ground-based experiments continue to probe the faint signals, looking for subtle effects that earlier instruments couldn't detect. The work is ongoing, not because the CMB is changing, but because our ability to measure it keeps improving. There's a certain elegance to the fact that so much information can be extracted from such a simple signal. The CMB is, at its core, just a background glow, uniform to within 1 part in 100,000. But those tiny deviations from uniformity, those little ripples in temperature, encode a wealth of information about the universe's contents, age, and geometry. The power spectrum distills all that complexity into a single curve, and from that curve scientists can read off parameter values with impressive precision. It's a reminder that nature doesn't always reveal its secrets through dramatic, obvious phenomena. Sometimes the most profound insights come from carefully analysing the boring, persistent background hum that's always been there. What makes the CMB particularly valuable is its simplicity relative to other cosmological probes. Galaxy surveys are complicated by the messy physics of how galaxies form and evolve, processes involving star formation, supernova feedback, black hole growth, and gas dynamics, all of which are difficult to model from first principles. Supernovae are useful distance indicators, but there are questions about whether their properties have changed over cosmic time, and whether dust or other effects might systematically bias the measurements. The CMB, by contrast, comes from a time when the universe was much simpler. There were no stars yet, no galaxies, no complex structures, just hydrogen, helium, a trace of lithium, dark matter, photons, and neutrinos. The physics governing the CMB is linear, meaning small perturbations behave predictably without complicated interactions, and well understood. This makes the theoretical predictions robust and the interpretation of the data relatively clean. That said, even the CMB has its complications and limitations. One issue is something called cosmic variance, which is an irreducible uncertainty that comes from the fact that we only have one universe to observe. The large-scale features in the CMB, those corresponding to low multipole numbers, are particularly affected by this. There are only so many independent large-scale patches on the sky, so the statistical uncertainty in measuring their properties can never be reduced below a certain level, no matter how perfect your instruments are. It's like trying to estimate the average height of people in a city by measuring only 10 individuals. You might get unlucky and sample mostly tall or mostly short people. The CMB has the same problem at large scales. For small-scale fluctuations, there are many more independent regions, so the measurements are statistically more robust. Another limitation is that the CMB only gives us information about the universe at one particular moment in time, the epoch of recombination. It tells us what conditions were like when the universe was 380,000 years old, and from that we can extrapolate backward to infer what must have happened even earlier, during the first fraction of a second. But the CMB doesn't directly tell us about what happened afterward, how the first stars formed, when galaxies assembled, how cosmic structure evolved over billions of years. For those questions, we need other observations, like surveys of galaxies at different distances and thus different times in cosmic history, studies of the intergalactic medium, and measurements of the star formation history across cosmic time. The CMB also doesn't directly detect dark matter or dark energy. It infers their presence through their gravitational effects on the distribution and evolution of ordinary matter and radiation. The patterns in the CMB are sensitive to how much dark matter there is because dark matter affects the gravitational potential wells that ordinary matter falls into, and it affects how the acoustic oscillations behave. Dark energy shows up in the CMB through subtle effects on the geometry of space and the late-time integrated Sachs-Wolf effect, where photons gain or lose energy as they travel through evolving gravitational fields. These are indirect detections, powerful and convincing, but they don't tell us what dark matter and dark energy actually are. That remains one of the biggest open questions in physics. Still, within its domain, the CMB is extraordinarily informative. It has transformed cosmology from a field where order of magnitude estimates were considered good progress into one where percent-level precision is routinely achieved. The age of the universe is known to better than 1%. The density of dark matter is constrained to a few percent. The amplitude and tilt of the primordial power spectrum, parameters describing the initial seed fluctuations that grew into all cosmic structure, are measured with similar precision. These tight constraints have turned cosmology into a mature science, where new theories are judged not by whether they seem plausible, but by whether they can match the detailed quantitative predictions of the standard model. Looking forward, there are still things to learn from the CMB. Ground-based experiments are currently hunting for the faint B-mode polarization signal that would indicate gravitational waves from inflation. Space missions are being designed to push measurements to even higher precision, to probe finer angular scales, and to search for subtle deviations from the standard model that might hint at new physics. There's also interest in measuring distortions in the CMB spectrum, deviations from the perfect blackbody shape, that could arise from energy injection in the early universe, perhaps from decaying particles or other exotic processes. These spectral distortions would be incredibly faint, much harder to detect than the temperature and polarization fluctuations, but they would open a new window on the universe's first million years. Another frontier involves cross-correlating the CMB with other datasets. For example, as CMB photons travel toward us, they pass through the large-scale structure of the universe, and their paths are bent slightly by gravitational lensing. This lensing distorts the CMB pattern in subtle ways, and by measuring that distortion, scientists can map the distribution of matter along the line of sight. This lensing signal can then be cross-correlated with galaxy surveys to learn more about dark energy and the growth of structure. The CMB can also be cross-correlated with traces of hot gas in galaxy clusters through the Sunyaev-Zeldovich effect, where CMB photons gain energy by scattering off hot electrons. These cross-correlation studies squeeze additional information out of the CMB data and help connect the early universe to the late universe. Even with all these future possibilities, the core story of the CMB remains simple. It is light from the early universe, released when the cosmos became transparent, stretched and cooled by expansion, and now arriving at our detectors as a faint microwave glow. It carries in its pattern the memory of sound waves that rippled through the primordial plasma, and from that pattern we have learned the universe's age, composition, and geometry. It is one of the most important discoveries in the history of science, and yet it sits there quietly, a background hum that has been present for nearly the entire age of the universe, unnoticed by most of the matter and energy around it, simply propagating through space according to the rules of physics. For those settling into sleep, the CMB offers a sense of continuity and scale. It connects the present moment to a time nearly 14 billion years ago, a time before stars, before planets, before anything resembling the structures we see in the night sky. It reminds us that the universe has a history, one we can study and understand through careful observation and analysis. And it does all this not through grand gestures or dramatic events, but through the patient accumulation of data, the slow refinement of measurements, and the quiet confidence that comes from seeing the same answers emerge from multiple independent lines of evidence. The universe, it turns out, is willing to tell us its story. We just have to listen to the hum. The next story is about to begin. Please relax and enjoy. Tonight is not about dramatic explosions or colliding galaxies or theories of parallel universes. Tonight is just about checking the universe's numbers, carefully, patiently, the way an accountant might review a long ledger at the end of a quiet day. For decades, astronomers have kept a kind of cosmic logbook, filling in columns of data, distances to galaxies, their brightnesses, how much their light has shifted toward red. Simple measurements, neat rows of figures, and by filling in this ledger over many years they discovered something unexpected. The universe isn't just expanding, it's speeding up. To make the mathematics work, to make the observations fit together, they had to add a new line to the cosmic budget, a smooth, invisible entry called dark energy. In the early 20th century, many of the faint smudges visible through telescopes were thought to be nearby clouds of glowing gas, tucked somewhere within our own Milky Way. Astronomers sketched them, catalogued them, gave them numbers. But as telescopes improved and spectroscopy became routine, those smudges turned out to be something far stranger. Entire galaxies, vast collections of stars lying millions or even billions of light years beyond our own. Each smudge was a new line in the logbook, a new entry with basic information: brightness, spectrum, rough distance. At this stage, no one expected these galaxies to reveal anything particularly odd about the universe. They were simply being organised, inventoried, the way a librarian might catalogue books on newly installed shelves. Among the tools astronomers used to measure distances were Cepheid variable stars. These are stars that brighten and dim in a regular cycle, their light rising and falling like a slow heartbeat. Henrietta Leavitt, working with photographic plates at Harvard, discovered that the period of a Cepheid's pulsation, the time it takes to go from bright to dim and back again, is tightly linked to its true luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This meant that by measuring the period you could determine the star's true brightness. And by comparing that true brightness to how bright it appears from Earth, you could calculate its distance. Cepheids became standard candles, objects whose true luminosity is known, allowing astronomers to install the first reliable rulers across cosmic space. With these stars, fuzzy impressions of distance turned into measured entries, tick marks on a scale that stretched far beyond the Milky Way. But distance alone wasn't enough. Astronomers also needed to know how galaxies were moving. This came from studying redshift, the stretching of light as objects move away from us. When a galaxy recedes, the wavelengths of light it emits are stretched to longer, redder values, much like the pitch of a siren drops as an ambulance drives away. By measuring the positions of spectral lines in a galaxy's light and comparing them to laboratory values, astronomers could determine how much the light had been redshifted, and from that, infer the galaxy's recession speed. Now each galaxy had two numbers in the ledger, a distance, often derived from Cepheids, and a speed, measured from redshift. 2 columns in a table. It doesn't sound like much, but putting those two numbers side by side would reshape our understanding of the cosmos. Edwin Hubble and his colleagues plotted these two quantities, recession speed versus distance, and found a roughly straight line relationship. The farther away a galaxy was, the faster it appeared to be moving away from us. This did not mean Earth was at the centre of some explosion. Rather, it meant that space itself was expanding, stretching distances uniformly in all directions. Imagine dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot, not because they're racing across the surface, but because the surface itself is growing. The Hubble constant, the slope of that distant speed line, became a single number summarising the expansion rate. It was written at the top of the logbook like a header, a key figure that described how fast the universe was growing. The natural next question was, how does this expansion change over time? Matter exerts gravity, and gravity pulls things together. So over the vast stretches of cosmic history, the expansion should slow down. The universe began in a hot, dense state, and has been expanding ever since. But with all that matter pulling inward, the expansion rate should gradually decrease. Early cosmological models, based on general relativity and estimates of the universe's matter content, predicted a decelerating expansion, fast in the distant past, easing off more recently. For many decades, cosmologists assumed that with better measurements, they would eventually detect this slowing, written into the logbook as a gentle downward curve when plotting distance against redshift at very large scales. To measure this deceleration, astronomers needed standard candles that could be seen at much greater distances than Cepheids alone could provide. Type Ia supernovae became those candles. These are exploding stars, specifically white dwarfs that accumulate matter from a companion star until they reach a critical mass and detonate. The explosion is violent but also remarkably uniform in brightness. Because the conditions that trigger a Type I supernova are fairly consistent, these explosions reach roughly the same peak luminosity. By observing these supernovae in distant galaxies, astronomers could extend their cosmic distance measurements much farther into space and farther back in time. Each supernova became a carefully measured entry: peak brightness, redshift, host galaxy, uncertainty. The spreadsheets grew longer, the data more refined. In the 1990s, 2 major research teams set out to measure the deceleration of the universe by observing distant type, Ia supernovae. They expected to find that these supernovae, located billions of light-years away, would appear either slightly brighter or slightly dimmer than predicted, depending on how much the expansion had slowed. The teams worked independently, checking each other's data, refining their calibrations. When the results came in, they found something no one had anticipated. The distant supernovae were dimmer than expected, not by a huge amount, but consistently dimmer. This meant they were farther away than they should have been for their measured redshifts. The distance-redshift relationship curved, but in the wrong direction. Instead of slowing down, the expansion of the universe was speeding up. At first, there was skepticism. Could the dimness be caused by dust along the line of sight, absorbing some of the light? Could the supernova themselves evolve over cosmic time, becoming intrinsically fainter in the distant past? Astronomers checked these possibilities carefully. Dust typically reddens light, and the observed dimming didn't show the expected colour signature. Detailed studies of supernova properties at different redshifts suggested that evolution alone couldn't explain the effect. The simplest explanation, strange as it sounded, was that the universe really was accelerating. The logbook now contained a stubborn discrepancy that couldn't be erased by adjusting the usual parameters. To make the equations of general relativity match these observations, cosmologists had to reintroduce a term that Albert Einstein had once added to his equations and later reportedly called his greatest blunder: the cosmological constant. This term represents a uniform energy density that fills all of space, a kind of background tension or pressure. In practical terms, dark energy behaves like negative gravity, not pushing galaxies apart in the everyday sense, but causing the expansion of space itself to accelerate. It doesn't clump into galaxies or stars. It remains smooth and spread out, like a faint mist of energy present everywhere, unchanging over time. In the cosmic ledger, it appears as an extra column in the budget, not just ordinary matter and dark matter, but a new dominant entry labelled with the Greek letter lambda, representing the cosmological constant's contribution to the total energy density of the universe. When cosmologists add up the universe's contents, they now speak in terms of fractions of the total energy density. A small fraction is ordinary matter, atoms, the stuff of stars and planets and people. A larger fraction is dark matter, invisible material whose presence is inferred from its gravitational effects on galaxies and galaxy clusters. And the majority, roughly 70%, is dark energy. These numbers come from combining multiple independent observations, supernova distances, the distribution of galaxies on large scales, and the patterns in the cosmic microwave background. Together, they form a consistent picture. The universe's ledger looks like a pie chart with three main slices, and the largest slice belongs to dark energy, even though we detect it only through its subtle influence on the expansion rate. The cosmic microwave background provides some of the tightest constraints on dark energy. This is the cooled afterglow of the early universe, radiation left over from a time when the cosmos was hot and dense, about 380,000 years after the Big Bang. Today, this radiation has cooled to just a few degrees above absolute zero and appears as a faint microwave signal filling the sky. The CMB is not perfectly smooth. It has tiny temperature variations, fluctuations at the level of 1 part in 100,000. These fluctuations encode information about the universe's contents and geometry. By measuring the angular size and amplitude of these variations, plotting them as a power spectrum of peaks and troughs, cosmologists can infer how much ordinary matter, and dark energy the universe contains. Dark energy affects the geometry of space, influencing the apparent size of structures imprinted in the CMB. The data from satellites like WMAP and Planck fit best with a universe that includes a cosmological constant, adding another independent line of evidence to the logbook. Baryon acoustic oscillations offer yet another way to track cosmic expansion. In the hot, dense early universe, ordinary matter and radiation were tightly coupled, and pressure waves, sound waves, rippled through the plasma. These oscillations left a characteristic scale imprinted in the distribution of matter. Today we see a faint echo of those sound waves in how galaxies cluster. When astronomers map the positions of millions of galaxies and measure their clustering, they find a small excess of galaxy pairs separated by a specific distance, roughly 500 million light-years. This is the Baryon acoustic oscillation scale, a standard ruler imprinted by the physics of the early universe. By measuring the apparent size of this ruler at different redshifts, at different epochs in cosmic history, astronomers can track how the expansion rate has changed over time. The measurements agree with a universe dominated by dark energy, providing yet another column of evidence in the cosmic ledger. The standard cosmological model that emerges from all this data is called lambda CDM, where lambda represents the cosmological constant and CDM stands for cold dark matter. The model is described by a small set of parameters: the density of ordinary matter, the density of dark matter, the density of dark energy, the Hubble constant, and a few others related to the initial conditions of the universe. Fitting this model to observations is a careful process. Cosmologists adjust the parameters until the model's predictions, how supernovae should appear at various distances, what the CMB power spectrum should look like, how galaxies should cluster, line up with the measurements. It's a kind of curve fitting, but a powerful one, because a single, simple model accounts for many different types of data collected with different telescopes and techniques. So far, Lambda CDM fits the logbook better than any known alternative. The numbers work. But what is dark energy really? There are a few possibilities, and none has been confirmed. It might be a true cosmological constant, a fixed energy density inherent to the vacuum of space itself, unchanging throughout cosmic history. Quantum field theory suggests that empty space is not truly empty, but filled with fleeting virtual particles, and this quantum vacuum might have an associated energy density. The problem is that naive calculations predict a vacuum energy far larger than what we observe, a discrepancy so enormous that it's known as the cosmological constant problem. Another possibility is that dark energy is not constant but slowly evolving, represented by a field that changes over time, sometimes called quintessence. If dark energy varies, its density might have been different in the past and could change in the future, leading to different expansion histories. A third idea is that dark energy is not a substance at all, but a sign that general relativity needs to be modified on very large scales. Perhaps the equations that describe gravity on cosmic scales are different from those we use in the solar system, and what we call dark energy is really a bookkeeping shortcut for more complex gravitational behaviour. These options live as neat columns of theories in the logbook, but the spaces under direct detection remain blank. The presence of dark energy affects the long-term future of the universe. If dark energy is a true cosmological constant, its density remains fixed even as the universe expands. Over billions of years, the accelerated expansion continues. Galaxies outside our local gravitationally bound group gradually move away faster and faster, eventually slipping beyond our cosmic horizon. The universe becomes more and more spread out, colder and emptier. On human timescales, this means nothing. The changes are imperceptibly slow. But extrapolating the trend far into the future suggests a universe that continues to expand indefinitely, with distant structures fading from view as space stretches between them. If dark energy evolves, other futures are possible. It might weaken over time, allowing gravity to regain influence, or it might strengthen, leading to more exotic scenarios. These are mathematical extrapolations, like projecting a trend line far beyond the current data, but they illustrate how sensitive the fate of the universe is to the nature of dark energy. Modern surveys are designed to refine our understanding by gathering vastly more data. Wide-field telescopes on mountaintops and in space are mapping millions of galaxies, measuring their redshifts, detecting thousands of supernovae, and charting the clustering of matter across the sky. Spectroscopic campaigns measure galaxy distances with high precision. Weak gravitational lensing surveys observe how the gravity of foreground structures subtly distorts the images of background galaxies, providing another way to map the distribution of matter and infer the effects of dark energy. Each survey adds many more lines to the cosmic logbook. The goal is not to overturn the Lambda CDM model, but to test it rigorously, to tighten the error bars on dark energy's properties, to check whether its effects truly match a simple cosmological constant or show hints of something more complex. The measurements are becoming precise enough that even small deviations from the standard model might become visible. And so we arrive at a curious situation. Dark energy is not a vague idea or a speculative hypothesis. It is a well-constrained component of our cosmological model. Its density is measured, its effect on the expansion of the universe is clear, and it appears consistently across multiple independent observations. Yet its physical nature remains unknown. We have a precise number for how much of the universe's energy budget is dark energy, but we don't know what that energy actually is. It's an unusual kind of mystery. The numbers are clear, the phenomenon is robust, but the underlying explanation is pending. For now, dark energy remains a carefully recorded but unexplained line in the universe's accounting, a placeholder in the equations that works beautifully but offers no insight into the mechanism behind it. The logbook stays open. Every night, telescopes continue their work. On remote mountaintops and aboard satellites in orbit, Instruments collect light from distant galaxies. Spectrographs split that light into rainbows, revealing redshifts. Cameras capture the brief flare of supernovae, recording their brightening and fading over weeks. Software pipelines process the data, flagging candidates, measuring distances, adding entries to spreadsheets. Teams of astronomers review the numbers, checking for systematic errors, comparing results from different surveys. Slowly, entry by entry, the cosmic ledger grows more detailed. Each new measurement narrows the possibilities for what dark energy can be. Each tightened error bar rules out certain models, constrains certain parameters. The universe itself seems indifferent to our questions. Space continues to stretch, pulling distant galaxies farther away whether or not we understand the mechanism. The acceleration continues, a slow, steady increase in the expansion rate that will play out over billions of years. On a single human night, the change is immeasurably small. The distant galaxies we see tonight are in nearly the same places they were yesterday, their redshifts unchanged to any precision we can detect. But over cosmic time, the effect is profound. Galaxies that are already far away will move farther, their light redshifting into the infrared and beyond, eventually becoming undetectable. The observable universe will, in a sense, shrink, not because space itself contracts, but because the expansion carries distant objects beyond the reach of light that can ever reach us. For those who find comfort in mystery, dark energy offers a particularly pure example. It is not hidden in the sense of being inaccessible. We see its effects clearly in the data. It is hidden in the sense that we do not yet know what it is made of, why it exists, or whether it is truly a property of space itself or a sign of something deeper. The history of physics is full of such mysteries. Electromagnetism was once a collection of curious phenomena, magnets, sparks, chemical reactions, before Maxwell unified it into a single framework. Radioactivity was a strange glow from certain rocks before it revealed the structure of the atomic nucleus. Dark energy may be similar, a well-measured effect awaiting a theoretical explanation that will, in hindsight, seem natural. Until that explanation arrives, cosmologists continue the work of refining the logbook. They cross-check measurements, compare supernovae at different redshifts, search for subtle variations in the baryon acoustic oscillation scale, scrutinize the polarization patterns in the cosmic microwave background. They develop more sophisticated models, testing whether dark energy could have varied slightly over time, or whether alternative theories of gravity might fit the data just as well. They propose new missions, space telescopes designed to observe thousands more supernovae, ground-based surveys to map the distribution of galaxies in unprecedented detail, experiments to measure the cosmic expansion rate with independent methods. Each of these efforts is a line item in the ongoing audit of the universe, a check on the numbers, a search for discrepancies that might hint at new physics. There is something calming about this work. It is meticulous, patient, cumulative. It does not promise immediate revelation or sudden breakthroughs, though those can happen. Instead, it proceeds by adding one measurement at a time, comparing one dataset against another, gradually building a more complete picture. The universe is large, ancient, and indifferent to human timescales, but it is also surprisingly willing to reveal its properties to anyone willing to look carefully and keep careful records. The logbook is not a secret document. The data are published, shared, scrutinized by researchers around the world. The process is open, transparent, and collaborative, a collective effort to understand the cosmos through observation and reason. And so, as the rain falls outside and the night deepens, we can imagine those telescopes continuing their quiet work. A supernova flares in a distant galaxy, its light travelling for billions of years before finally reaching a detector on Earth. The signal is recorded, time-stamped, added to a catalogue. In a few weeks, follow-up observations will measure its peak brightness, confirm its type, determine its redshift. Another entry in the ledger. Somewhere else, a survey telescope scans a patch of sky, collecting spectra from hundreds of galaxies in a single exposure. The data are transmitted to computers, processed through pipelines, and distilled into measurements of galaxy positions and redshifts. Another set of points on a plot, another constraint on the expansion history. And in an office or a lab, an astronomer examines the latest results, comparing them to predictions, noting where the model fits well and where tensions remain. Another day's work in the long project of understanding the universe. Dark energy is still there, filling space, gently accelerating the expansion. It does not announce itself with fireworks or fanfare. It is simply part of the universe's structure, woven into the fabric of space-time, present in every cubic meter of emptiness between galaxies. We infer its presence from the dimming of distant supernova, from the geometry encoded in the cosmic microwave background, from the clustering of galaxies on the larger scales. We give it a name and assign it a fraction of the cosmic energy budget. We write down equations that include it, and those equations match the observations. But we do not yet know what it is. Perhaps one day, a new theory will emerge that makes dark energy seem obvious. Perhaps a clever experiment will detect some property of the vacuum that explains the cosmological constant. Perhaps a refinement in observations will reveal that dark energy is not quite constant, that it evolves in a way that points to a specific underlying field. Or perhaps dark energy will remain a mystery for generations, a well-measured number in the cosmic ledger, a confirmed phenomenon that resists deeper explanation, reminding us that the universe is under no obligation to make itself comprehensible to us. For tonight, though, we can let the questions remain open. The logbook will be there tomorrow, with new entries added, new measurements recorded. The universe will still be expanding, and the acceleration will still be there. Subtle and steady, a fact of nature that we have learned to measure even if we do not yet understand its cause. The rain continues to fall, the screen stays dark, and somewhere, far overhead, light from distant galaxies continues its long journey toward Earth, carrying information about the expansion of space, about the stretching of wavelengths, about the gentle, persistent influence of dark energy. And someone, somewhere, is quietly updating the numbers. It's worth pausing to consider just how strange this situation is from a historical perspective. For most of human history, the universe was thought to be static, unchanging, eternal. The stars wheeled overhead in their predictable patterns, the planets wandered among the constellations, but the overall structure of the cosmos seemed fixed. Even Einstein, when he first applied his theory of general relativity to the universe as a whole, found that his equations predicted either expansion or contraction. To force them to describe a static universe, he added the cosmological constant as a kind of mathematical fix, a repulsive term to balance gravity's attraction. When Hubble's observations revealed that the universe was actually expanding, Einstein reportedly abandoned the cosmological constant, considering it unnecessary. The universe could simply be coasting outward from some initial state, slowing down under its own gravity but still expanding. For decades, that was the working picture. The universe began in a hot, dense state, the Big Bang, and had been expanding ever since, gradually decelerating. The main question was whether there was enough matter to eventually halt the expansion and cause a collapse, leading to a big crunch, or whether the expansion would continue forever, gradually tapering off toward a static state. Both scenarios assumed deceleration. The idea that the expansion might be accelerating, that something was actively driving galaxies apart faster and faster, was not seriously considered. It seemed to violate common sense. Where would the energy come from? What mechanism could possibly overpower gravity on cosmic scales? And yet, when the supernova data came in during the late 1990s, that's exactly what they showed. The universe wasn't just expanding, it was accelerating. Einstein's discarded cosmological constant had to be brought back, not as a mathematical trick to create a static universe, but as a genuine physical component, dark energy, that dominated the universe's energy budget. In a way, Einstein's intuition had been correct. There was an additional term in the equations. He just had the sign wrong, or rather, the context wrong. He wanted it to balance gravity and create stasis. Instead, it overwhelms gravity on large scales and drives acceleration. This historical twist adds a layer of irony to the story. The cosmological constant was introduced for the wrong reasons, abandoned when observations contradicted those reasons, and then reintroduced when different observations demanded it. It's a reminder that science doesn't always proceed in a straight line. Ideas are proposed, tested, discarded, and sometimes resurrected in new forms when new data arrive. The logbook of science, like the cosmic logbook, has its share of crossed-out entries, marginal notes, and second thoughts. What matters is not the elegance of the path, but the accuracy of the destination. The discovery of cosmic acceleration also highlights the importance of precision in astronomy. The effect is subtle. The distant supernovae were only about 25% dimmer than expected in a decelerating universe. That's not a dramatic difference. It required careful calibration, multiple independent observations, and rigorous checks for systematic errors. If the measurements had been just slightly less precise, the signal might have been lost in the noise, attributed to uncertainties or unaccounted for effects. But because the observations were good enough, because the teams cross-checked their work, the signal came through clearly. It's a testament to the power of patient, careful measurement. Sometimes the most profound discoveries come not from seeing something spectacular, but from noticing that the numbers are slightly off from what you expected, and taking that discrepancy seriously. The role of technology in this story cannot be overlooked. The discovery of dark energy required sensitive digital cameras capable of detecting faint supernovae in distant galaxies, automated telescopes that could survey large swathes of sky, and software pipelines to process vast amounts of data. It required international collaboration, with teams sharing data, techniques, and insights. It required decades of prior work building the cosmic distance ladder, calibrating standard candles, and refining cosmological models. No single observation or single insight made the discovery possible. It emerged from the cumulative effort of many people using the best tools available, building on the work of earlier generations. The logbook was filled in page by page, year by year, with each generation adding its contribution. There's also something humbling about dark energy. It reminds us how little we know about the universe. We've identified the basic components: ordinary matter, dark energy. But we only truly understand one of them. Ordinary matter, the stuff of atoms and molecules, is well described by the standard model of particle physics. We know how it behaves, how it interacts, what it's made of. Dark matter remains mysterious, but at least we have plausible candidates, hypothetical particles that interact weakly with ordinary matter, perhaps detectable in underground experiments or particle colliders. Dark energy is more elusive. It doesn't clump, doesn't form structures, doesn't interact with matter in any obvious way except through its effect on space-time itself. It's the least tangible component of the universe, yet it makes up the largest share of the total energy. This imbalance between what we know and what exists is a recurring theme in cosmology. Before galaxies were understood, most of the universe by mass was a mystery. Once galaxies were mapped, most of the mass within them turned out to be dark matter, another mystery. Now, with dark energy included, the mysterious components, dark matter and dark energy together, make up about 95% of the universe's total energy content. We live in a universe where the familiar is a tiny minority. It's as if we've been studying a vast library and have so far only learned to read 5% of the books. The rest remain in languages we don't yet understand, their content inferred only from their weight and the space they occupy on the shelves. But this is not a reason for despair. It's an invitation. Each mystery is an opportunity for discovery, each gap in the logbook a place where new knowledge might be written. The history of astronomy is full of surprises. No one expected to find galaxies beyond the Milky Way. No one anticipated that the universe was expanding. No one predicted dark matter or dark energy. Each discovery opened new questions, new avenues of inquiry. The fact that we don't yet understand dark energy doesn't mean we never will. It means we're still in the early stages of a longer investigation. Consider how the search for dark energy has evolved. The initial discovery came from supernovae, but subsequent measurements have used entirely different methods. The cosmic microwave background encodes information from when the universe was less than 400,000 years old, long before the first stars formed. Baryon acoustic oscillations probe the large-scale structure of matter, the way galaxies are distributed across billions of light years. Weak gravitational lensing measures how the cumulative gravity of all matter, dark and ordinary, distorts the paths of light from distant sources. Each of these methods provides an independent check on the others. The fact that they all point to the same conclusion, that dark energy makes up about 70% of the universe's energy density, is powerful evidence that the phenomenon is real, not an artifact of one particular measurement technique or a subtle error in one dataset. This convergence of evidence is how confidence builds in science. A single striking result, like the supernova observations, raises eyebrows and prompts further investigation. But when multiple independent methods, using different instruments, different physical principles, and different sources of data, all arrive at consistent answers, the case becomes compelling. The universe is not trying to deceive us. It's telling us the same story through multiple channels. Our job is to listen carefully, compare the accounts, and extract the underlying truth. The current generation of surveys is pushing this even further. Projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and upcoming missions like the Euclid Satellite and the Vera C. Rubin Observatory are designed to measure dark energy's properties with unprecedented precision. They will observe millions of galaxies, thousands of supernovae, and map the distribution of matter across vast volumes of space. They will measure how the expansion rate has changed over billions of years, looking for any hint that dark energy is not truly constant. Even a small variation, a few % change in dark energy's density over cosmic time, would be a major clue, potentially pointing toward a specific theoretical model. These surveys are also searching for tensions in the data, places where different measurements don't quite agree. One such tension involves the Hubble constant, the current expansion rate of the universe. Measurements based on the cosmic microwave background predict one value, while measurements based on nearby supernovae and Cepheids give a slightly different value. The discrepancy is small, only a few %, but it persists even as both measurements become more precise. This could be a sign of unaccounted for systematic errors, or it could hint at new physics. Perhaps dark energy evolves in a way not captured by the standard model, or perhaps there's an additional component of the universe we haven't yet included in the ledger. Resolving this tension is one of the priorities of modern cosmology. There are also more speculative ideas floating in the theoretical literature. Some models propose that dark energy is connected to extra dimensions of space, hidden from ordinary experience but influencing the large-scale behavior of the universe. Others suggest that dark energy might be related to the cosmological event horizon, the boundary beyond which objects recede faster than light and become forever unobservable. Still others explore whether dark energy could decay over time, gradually converting into other forms of energy, or whether it might interact with dark matter in subtle ways we haven't yet detected. These ideas are mostly untested, waiting for observations precise enough to distinguish them from simpler models. They live in the margins of the logbook, speculative annotations pending confirmation or refutation. One thing that makes dark energy particularly challenging is that it has no direct laboratory analogue. We can't create a patch of dark energy in a lab and study its properties. We can't bottle it, measure its temperature, or probe its structure. All our information comes from its effect on the expansion of the universe, a phenomenon that plays out over billions of light years and billions of years. This makes dark energy a fundamentally cosmological problem, one that can only be studied through astronomy. We have to wait for light from distant galaxies, decode the information it carries, and infer the properties of dark energy from patterns in redshifts, brightnesses, and clustering. It's detective work on the grandest possible scale, with the universe itself as the only laboratory. Yet despite these challenges, progress is being made. The parameters describing dark energy are being measured with increasing accuracy. The equation of state, the relationship between dark energy's pressure and its density, is being constrained to within a few % of the simplest model, a true cosmological constant. Future surveys promise even tighter constraints, potentially revealing subtle deviations that could point to the true nature of dark energy. It's painstaking work, requiring patience and precision, but it's work that steadily narrows the range of possibilities, ruling out some models and focusing attention on others. In the meantime, the universe continues its expansion, indifferent to our efforts to understand it. Dark energy pervades every cubic meter of space, its influence steady and unrelenting. Galaxies move apart, their distances increasing year by year, century by century. The effect is too slow to notice in a human lifetime, but it's there, written into the structure of space-time itself. And we, brief sparks of consciousness on a small planet orbiting an ordinary star, have found a way to measure it, to quantify it, to add it as an entry in our cosmic logbook. That achievement, however incomplete our understanding, is worth acknowledging. We may not yet know what dark energy is, but we know it exists, we know how much there is, and we know what it does. That's not nothing. That's a foothold, a starting point for deeper inquiry. The story of dark energy is still being written. New chapters will be added as new data come in, as new telescopes come online, as new theoretical ideas are proposed and tested. Perhaps the mystery will be solved within a generation. Perhaps it will take longer. Either way, the logbook will continue to grow, line by line, number by number, each entry a small piece of the larger puzzle. And somewhere, on some quiet night, an astronomer will notice a pattern in the data, or a theorist will have an insight that ties disparate observations together, and another piece of the cosmic story will fall into place. Until then, we wait, we measure, and we think. The universe is patient. We try to be patient too. The next story is about to begin. Please relax and enjoy. Tonight we are conducting a census of alien worlds, and there is nothing particularly thrilling about it. This is administrative work, the slow and methodical task of counting planets that happen to orbit stars other than our own sun. Imagine an astronomer seated at a desk scrolling through columns of data, star names, orbital periods, planetary radii, a few sparse notes about detection confidence. Each discovery is logged, verified, cross-referenced, and added to an ever-growing table. The work resembles that of a patient clerk processing immigration forms or updating property records, except the entries describe worlds separated from us by light years rather than city blocks. Exoplanets are no longer the subject of wild speculation or rare headlines. They have become routine catalogue entries, and the catalogue itself has grown so large that no single person can hold all the details in memory. Instead, the information lives in databases, sortable and searchable, each row representing a distant world reduced to a handful of numbers and flags. For most of human history, the idea that other stars might host planets was pure conjecture, a philosophical exercise with no supporting evidence. People reasoned by analogy. Our sun has a family of worlds circling it, so perhaps other suns do as well. This seemed reasonable, even elegant, but remained entirely speculative. Telescopes improved, astronomy advanced, yet no one could point to a specific star and say with confidence that it harboured planets. The tools simply were not sensitive enough. Even into the middle of the 20th century, exoplanets belonged more to the realm of imagination than measurement. The census form existed only as an idea, blank columns waiting for the first real entries. Philosophers and scientists could sketch what such a form might look like. Fields for orbital distance, planetary mass, perhaps atmospheric composition. But every line remained empty, awaiting the moment when technology would catch up to curiosity. The breakthrough came not from seeing planets directly, but from detecting their influence on the stars they orbit. Consider the basic mechanics. When a planet circles a star, both objects actually orbit their shared centre of mass, a point called the barycenter. For a star much more massive than its planet, this point lies close to the star's core but not exactly at the centre. As a result, the star wobbles slightly as it moves through space, tracing a small repeating loop. This wobble is minor, but it produces a detectable effect. As the star moves toward us, the light we receive shifts slightly toward the blue end of the spectrum, and as it moves away, the light shifts toward red. These are Doppler shifts, the same phenomenon that changes the pitch of a siren as an ambulance drives past. Astronomers began monitoring the light from nearby stars, splitting it into spectra and measuring these tiny shifts night after night. Over weeks and months, patterns emerged, gentle, repeating waves in the spectral data, like a slow heartbeat encoded in light. Each stable wave represented a planet tugging its star in a predictable rhythm. The planet itself remained invisible, but its signature appeared on the page as a series of measurements, a wobble recorded in wavelengths and translated into a claim. A planet exists here, with this mass, at this distance, completing an orbit in this many days. The first confirmed exoplanet around a sun-like star was announced in the mid-1990s, and it immediately became the first real entry in the census, a single line in what would soon become a very long list. What surprised astronomers was not simply that planets existed elsewhere, but that many of the first discoveries contradicted expectations derived from our own solar system. The early entries in the census featured so-called hot Jupiters, giant planets comparable in size to Jupiter, but orbiting extremely close to their stars, often closer than Mercury orbits our Sun. These worlds completed their years in just a few Earth days, subjected to searing temperatures that would vaporize metals. In our solar system, gas giants live in the cold outer regions, far from the sun's heat. The discovery of hot Jupiters suggested that planetary systems do not all follow the same blueprint. Rather than causing alarm or confusion, these strange entries simply expanded the census categories. Astronomers added new columns and notes: close-in giants, ultra-short periods, extreme temperatures. The universe, it turned out, does not organise itself according to the one example we knew best. The filing system had to grow to accommodate worlds that did not fit the original template. While the radial velocity method continued to find planets by measuring stellar wobbles, another technique began to dominate the census work: the transit method. This approach is elegant in its simplicity. When a planet passes directly between its star and our line of sight, it blocks a tiny fraction of the star's light, causing a brief, shallow dip in brightness. If the planet's orbit is aligned just right, this dimming happens at regular intervals, once per orbit. Astronomers monitor stars continuously, recording their brightness over time and producing what are called light curves, smooth lines tracing the star's output. Most of the time, the line stays flat, but when a planet transits, a small notch appears, a gentle downward dip followed by a return to baseline. The depth of the dip reveals the planet's size relative to the star, and the spacing between dips gives the orbital period. Each transit is like a checkbox on a survey form, a repeating signal that confirms the presence of a planet and allows its basic properties to be inferred. With enough transits recorded, the light curve becomes an attendance sheet for the planetary system, each world marking its presence with a predictable pattern of dimming. The transit method brought a new level of efficiency to the census. A single telescope, staring at thousands of stars simultaneously, could detect multiple planets at once simply by watching for these periodic dips. The task became almost mechanical: collect light curves, search for repeating patterns, flag candidates, verify with additional observations or different methods. Each confirmed transit added another row to the database, and the rows began to accumulate rapidly. But the transit method also revealed subtleties that hinted at hidden complexity. In systems with multiple planets, the gravitational pull between worlds can cause slight variations in the timing of transits. A planet might arrive at its expected transit a few minutes early or late, tugged by the gravity of an unseen companion. These transit timing variations show up as small deviations in an otherwise regular schedule, like margin notes scribbled on a form indicating that something else is present in the system. By carefully modelling these timing shifts, astronomers can infer the existence of additional planets, even those that do not transit. These indirect detections fill in gaps, adding extra lines to the census based on the gravitational fingerprints left in the data. In rare cases, astronomers manage to take direct images of exoplanets, capturing actual photons reflected or emitted by the planet itself. This requires blocking out the star's overwhelming glare using specialized instruments and analyzing what remains, a faint point of light offset from the star. Direct imaging works best for planets that are large, far from their stars, and often young and still radiating heat from their formation. The resulting images are not dramatic photographs of swirling clouds or colourful landscapes. They are subtle, carefully processed spots, pixels that have been teased out of noise and identified as separate from the star. Each direct image is a profile picture in a database, otherwise dominated by graphs and numbers, a visual confirmation that adds texture to an entry, but does not fundamentally change the nature of the census work. These images are rare because the conditions required, bright planet, dim or blocked star, favourable geometry, are difficult to achieve. Most planets remain invisible, known only through their effects on light and motion. One mission in particular transformed the scale of the census. A space telescope launched to stare at a single patch of sky for years, monitoring over 100,000 stars continuously. The mission's task was straightforward but demanding. Watch for the tiny repeating dips in starlight that indicate transiting planets. Each star became a line in the survey. Either it exhibited transit signals, or it did not. The telescope recorded brightness measurements with exquisite precision, sending the data back to Earth where teams of scientists processed it, cleaned it, and searched for patterns. Over time, the catalogue of candidate planets grew into the thousands. Some, Candidates required follow-up observations to confirm their planetary nature and rule out false positives. But the sheer volume of detections established a new reality. Planetary systems are common. The mission did not explore strange new worlds in the narrative sense. It simply stared and counted, adding entry after entry to the galactic spreadsheet. The work was repetitive, methodical, and enormously productive, demonstrating that patience and precision could map the sky one light curve at a time. Following that mission, newer surveys expanded the approach, scanning nearly the entire sky, but focusing on bright nearby stars. These are follow-up census rounds, trading deep focus on one region for broader coverage across many regions. The goal is to catalogue planets around stars close enough for detailed follow-up study, where future telescopes might analyse atmospheres or search for signs of habitability. Each new survey finds more planets, adding variety to the catalogue, some with short orbits, others with longer periods, single planets and multi-planet systems, hot worlds and cooler ones. The spreadsheet grows steadily, each mission contributing a new batch of rows, occasional corrections to earlier entries, and updates to detection confidence levels. As the census expanded, patterns emerged in the types of planets being discovered. Astronomers developed a rough classification system based on size and composition, though the boundaries are fuzzy and many planets fall into intermediate categories. Hot Jupiters are the gas giants orbiting close to their stars, easily detected because their large size causes deep transits and their proximity produces strong radial velocity signals. Mini-Neptunes are smaller, roughly between Earth and Neptune in size, likely with thick atmospheres of hydrogen and helium surrounding a rocky or icy core. Super-Earths are more massive than Earth but smaller than Neptune, potentially rocky or water-rich, though their exact compositions remain uncertain without direct atmospheric measurements. Many of these categories do not exist in our own solar system, which meant that new labels were needed. The classification process resembles a librarian sorting books into genres. Radius goes in one column, mass in another, density calculated from the two, and from these numbers, a tentative type assigned. The catalogue reveals that certain sizes are common. Mini-Neptunes and super-Earths populate the lists in large numbers, while others, like true Earth analogues, remain relatively rare in the current data, possibly due to detection biases rather than actual scarcity. Some planetary systems are tightly packed, with several worlds orbiting close to their star in orderly configurations. Observations show systems where 5 or 6 planets complete their orbits within a distance smaller than Mercury's orbit around our Sun. In some cases, the planets are locked in orbital resonances, meaning their periods form simple ratios. One planet might complete exactly 2 orbits for every 3 of its neighbours. These resonances stabilise the system, preventing close encounters and collisions. From an observer's perspective, such systems produce a series of transit dips, each with its own depth and timing overlapping like entries in a ledger. The light curves become layered schedules, multiple planets checking in at different intervals. These compact systems demonstrate that gravity can arrange planets in configurations very different from the widely spaced giants and inner rocky worlds of our solar system. They are not exotic or dramatic in themselves, they are simply efficient solutions to the equations of motion, alternative ways for matter to organise around a star. The concept of the habitable zone is often invoked in discussions of exoplanets, but it is a calm, technical definition, rather than a guarantee of life. The habitable zone is the range of orbital distances from a star where a rocky planet with a suitable atmosphere could, in principle, maintain liquid water on its surface. The zone's location depends on the star's brightness. Hotter stars have habitable zones farther out, cooler stars have them closer in. Being in the habitable zone does not mean a planet is habitable, only that its temperature might allow for liquid water, which is considered a key ingredient for life as we know it. Planets in this zone still need the right atmospheric pressure, composition, and other factors. In the census, habitable zone planets receive a small extra annotation in their entry, a note that says the temperature conditions are potentially moderate, neither too hot nor too cold. This is useful for prioritising follow-up observations, but it remains a preliminary flag, not a final verdict. When a planet transits, astronomers have the opportunity to study its atmosphere if it has one. As the planet crosses in front of the star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. By carefully analysing the spectrum of this transmitted light, researchers can detect the presence of certain gases, water vapour, hydrogen, methane, or other molecules that leave distinct absorption features. These observations are technically challenging, requiring large telescopes, long observation times, and sophisticated data analysis to tease out faint signals from noise. The resulting spectra are often ambiguous, with detections at low confidence levels, but each hint of an atmosphere adds another column to the database. The census expands from simple size and orbit to include atmospheric ingredients, at least for the brightest and most favourable cases. The process feels like reading faint handwriting on an old document, deciphering one careful measurement at a time, building up a picture from fragments. The data from all these surveys and methods are compiled into online catalogues, public databases where each confirmed exoplanet is listed with its properties: host, star coordinates, orbital period, radius, mass, when available, detection method, discovery date, and confidence metrics. For astronomers, these tables are the primary interface to alien worlds. A researcher interested in mini-Neptunes can filter the catalogue by size, export a list, and analyse trends. Someone studying tightly packed systems can sort by the number of planets per star. The catalogue is a living document, updated as new discoveries are confirmed, refined as follow-up data improve initial estimates, and corrected when errors are identified. Each entry is a planet reduced to a row, and the table itself is a map of the sky's planetary population, incomplete but growing. A casual observer browsing these catalogues sees numbers, flags, and references to scientific papers, a far cry from colourful illustrations or artists' concepts. But this is the real substance of the census, data organised for analysis, not spectacle. The census is incomplete and biased by the methods used to detect planets. Transit surveys are most sensitive to planets with short orbital periods because these transit more frequently and are easier to catch during limited observation windows. They also favour planets around small stars because a given planet causes a deeper dimming relative to a smaller star's light. Radial velocity surveys are best at finding massive planets close to their stars where the gravitational tug is strongest. Direct imaging favours large, distant and young planets that shine brightly in infrared light. As a result, the catalogue is weighted towards certain types of worlds and underrepresents others. Small planets in long orbits, for example, are difficult to detect and remain largely uncounted. Astronomers are aware of these biases and work to correct for them statistically, estimating how many planets are likely to exist based on the fraction they can detect. The true census includes not only the thousands of confirmed planets, but also the carefully calculated estimates of missing entries, the planets we have not yet seen but can infer from the patterns in the data. The overarching lesson from this decades-long effort is that planets are common. With thousands of confirmed exoplanets and many more candidates awaiting verification, the evidence strongly suggests that most stars host at least one planet, and many host several. Planetary systems are not rare exceptions, but standard features of stellar evolution, as ordinary as the stars themselves. Our solar system, once the only known example and the template for all speculation, is now a single entry in a vast catalogue, neither typical nor particularly unusual, simply one configuration among many. The story of exoplanet discovery is not one of dramatic revelations or singular breakthroughs, but of steady accumulation, observations piling up, methods improving, catalogues expanding. The work continues, methodical and patient, adding row after row to the spreadsheet of alien worlds. The process of confirming an exoplanet candidate involves layers of verification, each step adding confidence that what has been detected is genuinely a planet and not some other phenomenon masquerading as one. A single transit signal might be caused by a background eclipsing binary star system aligned by chance with the target star, or by instrumental noise, or by stellar activity such as star spots rotating across the star's face. To distinguish planets from imposters, astronomers perform follow-up observations using different techniques. They might take spectra to check for the radial velocity wobble that should accompany a transiting planet. They might use high-resolution imaging to see if the star has a nearby companion that could be the real source of the signal. They might observe additional transits to verify the periodicity and depth remain consistent. Only after these checks are satisfied does a candidate receive the designation of confirmed planet, and only then does it earn a permanent place in the catalogue. The confirmation process is unglamorous. a series of cross-checks and statistical tests, but it is essential to maintaining the integrity of the census. Each confirmed planet represents not a single observation, but an accumulation of evidence from multiple sources. The stars themselves vary widely, and this variation affects the planets around them. Hot, bright stars burn through their fuel quickly and have short lifetimes, while cool, dim stars can shine for trillions of years. The most common stars in the galaxy are red dwarfs, small and cool with habitable zones located very close in. Planets orbiting red dwarfs complete their orbits in days or weeks, and because they orbit so close they often become tidally locked, with one side perpetually facing the star and the other in permanent darkness. These worlds present a different kind of environment, potentially habitable but subject to strong stellar flares and unusual temperature gradients. The census includes many planets around red dwarfs because these stars are numerous and their close inhabitable zones make planets easier to detect. Larger, sun-like stars are less common and massive blue stars are rarer still. The catalogue reflects this distribution. Most entries list host stars that are smaller and cooler than our Sun, which means that the typical exoplanet orbits a star quite different from the one we know. The masses of exoplanets, when they can be measured, provide clues about composition. A planet's mass combined with its radius gives its average density. High density suggests a rocky composition, similar to Earth or Venus. Low density indicates a substantial gaseous envelope, like Jupiter or Saturn. Intermediate densities might point to water-rich worlds, planets with deep oceans or thick layers of ice, though distinguishing between a water world and a rocky planet with a thick hydrogen atmosphere is difficult without additional data. For many planets, especially smaller ones, detected only by transits, mass remains unknown or poorly constrained, leaving composition as an open question. The census thus contains entries with varying levels of completeness. Some planets have well-measured radii, masses, orbital parameters, and atmospheric hints. Others have only a radius and orbital period, the bare minimum. This unevenness is characteristic of an ongoing survey, where not every target can receive equal attention and where observing time is allocated based on scientific priorities. Stellar activity complicates the census work. Stars are not static light sources. They have spots, flares, and oscillations that can mimic or obscure planetary signals. A dark star spot rotating across the visible face of a star causes a dip in brightness that might be mistaken for a transit. Distinguishing between these false signals and genuine planets requires careful analysis of the light curve's shape and timing, as well as knowledge of the star's rotation period and activity level. Young, active stars are particularly challenging targets because their variability can swamp the subtle signals of transiting planets. Older, quieter stars provide cleaner data, but even they are not perfectly steady. Astronomers have developed statistical methods and machine learning algorithms to filter out stellar noise and identify the periodic, symmetric dips characteristic of transits. These tools have become essential as the census has grown, allowing large datasets to be processed efficiently without manually inspecting every light curve. Some planetary systems exhibit unusual dynamical arrangements. Planets in highly eccentric orbits, for example, follow elongated ellipses rather than near-circular paths, swinging close to their stars at one point in their orbit and receding to much greater distances at another. These eccentric orbits can result from gravitational interactions, either between planets in the same system or with external companions. They add complexity to the census, requiring more detailed modelling to accurately determine the planet's properties. Other systems contain planets on inclined orbits, tilted relative to each other or to the star's equatorial plane. Such configurations suggest a history of dynamical upheaval, perhaps involving planet-planet scattering or the influence of a distant stellar companion. The census captures these systems as outliers, entries with unusual parameter values that prompt further investigation. The search for planets around binary star systems introduces another layer of complexity. In a binary system, two stars orbit each other, and planets can form either around one of the stars individually or in a circumbinary orbit, circling both stars together. Detecting planets in binary systems is challenging because the light curves and radial velocity signals must account for the motion of both stars. Nevertheless, several circumbinary planets have been confirmed, their transits appearing as dips in the combined light of the binary pair. These planets add variety to the catalogue, demonstrating that planetary formation is robust even in environments with multiple gravitational anchors. The orbital dynamics of such systems are intricate, with the planet's orbit influenced by the changing gravitational field as the two stars move. Yet the census treats them with the same procedural care as any other entry: orbital period, size, host star details, and notes on the detection method. Ground-based observatories contribute to the census alongside space telescopes. Networks of small, automated telescopes scan the sky for transits, while larger facilities follow up on candidates with high-resolution spectroscopy and imaging. Ground-based radial velocity surveys have been particularly productive, using instruments mounted on telescopes in Chile, Hawaii, and other sites with clear, stable skies. These surveys monitor hundreds of stars over many years, accumulating velocity measurements with precision of a meter per second or better. The combination of space-based transit surveys and ground-based radial velocity follow-up creates a complementary workflow. Space telescopes find the candidates, and ground-based instruments confirm and characterize them. The census is thus a collaborative effort, drawing on data from many sources and integrating measurements taken in different wavelengths and using different methods. The question of how planets form remains an active area of research, informed by the census data. According to current models, planets coalesce from disks of gas and dust that surround young stars. Small particles stick together, growing into larger clumps, which eventually become planetesimals and then protoplanets. Gas giants form when a core becomes massive enough to gravitationally capture hydrogen and helium from the surrounding disk. Rocky planets form closer to the star, where temperatures are too high for volatile materials to condense. However, the diversity of exoplanets challenges these models. Hot Jupiters likely formed farther out and migrated inward, their orbits altered by interactions with the disk or with other planets. Super-Earths and mini-Neptunes, common in the catalogue but absent from our solar system, suggest formation pathways that depend sensitively on disk conditions and timing. The census provides the raw material for testing these models: distributions of planet sizes, orbital periods, and multiplicities that theorists compare with predictions from simulations. Each new entry refines the constraints, helping to distinguish between competing scenarios. Red dwarf stars, because of their abundance and the ease of detecting planets around them, have become a major focus of the census. The nearest exoplanets are found around red dwarfs, some only a few light-years away. These stars are dim, so their habitable zones lie close in, and planets in these zones transit frequently, making them accessible to current instruments. Several rocky planets in the habitable zones of red dwarfs have been confirmed, and these are considered promising targets for atmospheric characterization. However, red dwarfs are prone to violent stellar flares that could strip away planetary atmospheres or sterilize their surfaces with radiation. The census notes these systems without judgment, simply recording the parameters and leaving questions of actual habitability to future investigation. The architecture of multi-planet systems reveals regularities that hint at underlying physical processes. Many systems show planets with similar sizes, sometimes called peas-in-a-pod configurations, where neighbouring planets differ in radius by only a few %. This uniformity suggests that planets within a system share a common formation environment and have experienced similar evolutionary histories. Other systems exhibit a wider range of sizes, possibly indicating different formation times or locations within the protoplanetary disk. The spacing between planets also follows patterns, with most systems showing regular, nearly evenly spaced orbits in logarithmic terms. These statistical regularities, extracted from the census, guide models of planet formation and migration, offering clues about how the initial chaotic disk of material settles into an ordered planetary system. Measurements of planetary obliquity, the tilt of a planet's spin axis relative to its orbital plane, are possible for a few transiting planets using a technique called the Rossiter-McLaughlin effect. When a planet transits, it blocks light from different parts of the rotating star at different times, causing a subtle distortion in the star's spectral lines that reveals the orientation of the planet's orbit relative to the star's rotation. Some hot Jupiters are found on highly tilted or even retrograde orbits, moving opposite to the star's spin. This suggests violent dynamical histories, possibly involving close encounters with other planets that ejected them into misaligned orbits. These measurements add another column to the census, obliquity values that enrich the dynamical picture of each system. The concept of occurrence rates quantifies how common different types of planets are. By accounting for detection biases, astronomers estimate the fraction of stars that host planets of various sizes and orbital periods. Current estimates suggest that small planets, particularly those in the super-Earth and mini-Neptune size range, are extremely common, with most Sun-like stars hosting at least one. Gas giants are less common, found around perhaps 10 to 20% of Sun-like stars. Rocky planets in Earth-like orbits, similar size, similar distance from a Sun-like star, are harder to detect and thus less well constrained, but preliminary estimates suggest they might be present around a significant fraction of stars. These occurrence rates transform the census from a list of individual discoveries into a statistical portrait of the galaxy's planetary demographics. The numbers allow astronomers to estimate the total number of planets in the Milky Way, a figure that runs into the hundreds of billions, making planets more numerous than stars. Future missions will push the census into new territory. Next-generation space telescopes with larger mirrors and more sensitive instruments will be able to detect smaller planets, including true Earth analogues, and characterize their atmospheres in greater detail. Ground-based extremely large telescopes, with mirrors tens of meters across, will obtain high-resolution spectra of exoplanet atmospheres, searching for gases that might indicate biological activity. These future observations will add new columns to the database: atmospheric biosignature detections, surface temperature maps, measurements of day-night temperature contrasts. The census will deepen and broaden, filling in gaps and extending into parameter spaces currently inaccessible, yet the fundamental nature of the work will remain the same: careful observation, patient data collection, statistical analysis, and catalogue updates. The human element of the census involves thousands of researchers across many countries, each contributing expertise in instrumentation, data analysis, theoretical modelling, or statistical interpretation. Teams coordinate their efforts, sharing data through public archives and collaborating on follow-up campaigns. When a particularly interesting planet is discovered, multiple groups may study it independently, combining their results to build a more complete picture. The scientific papers that announce new planets or refine known properties are densely technical, filled with tables, figures, and equations. These papers are the formal record of the census, each one adding to the collective knowledge. For those involved in the work, the satisfaction comes not from any single discovery, but from the gradual accumulation of understanding, the sense that the galaxy's planetary population is being mapped with increasing precision. The cultural impact of the census is quiet but profound. Knowing that planets are common shifts the context for thinking about life in the universe. If most stars have planets, and if many of those planets reside in conditions that might allow liquid water, then the potential sites for life are numerous. This does not prove that life is common, but it changes the calculation from one where habitable planets are rare and precious, to one where they are abundant. The next question becomes not whether habitable worlds exist, but whether life arises on them, a question the census alone cannot answer. Yet the census lays the groundwork, providing the targets for future searches and the statistical framework for estimating how many worlds might host biology. Imagine falling asleep while the census is still underway. New missions are being planned and launched, equipped with more sensitive instruments capable of detecting smaller planets, longer orbits, and fainter atmospheric signals. Some future entries may describe rocky worlds in temperate orbits around quiet stars, places where conditions might, in principle, support life. But from the perspective of this story, they will remain what all exoplanets are in the census: cells in a table, coordinates and periods and radii, notes and confidence intervals. The listener drifts off with the image of a vast unfinished spreadsheet, rows extending beyond the screen, each one a world documented but not visited, known but not explored. Somewhere, a telescope is pointing at a star, collecting photons, waiting for the next tiny dip in brightness. The data will be downloaded, processed and analysed. If a pattern is found, a new row will be added. The census of alien worlds continues quietly, methodically, while we sleep, one light curve at a time, the galaxy revealing its population not in a burst of discovery but in the slow, patient accumulation of entries in an ever-growing catalogue. The The next story is about to begin. Please relax and enjoy. Tonight we're going through the universe's paperwork, and the numbers don't quite add up. It's not a dramatic discrepancy, nothing that sets off alarms or suggests fraud, just a persistent gap that shows up whenever astronomers try to reconcile what they can see with what gravity tells them must be there. They can count stars, measure the glow of gas clouds, estimate the mass of dust scattered between galaxies. They can weigh these components with reasonable confidence. Then they watch how things move, how stars orbit galactic centres, how galaxies wheel around each other in clusters, how light bends around massive objects, and the motion always implies more mass than the visible inventory can account for. Over decades, this gap has been given a name: dark matter. It's not a particularly romantic term, more like a placeholder in a ledger for an entry that hasn't been filled in yet. Something is there, exerting gravitational pull, shaping the architecture of the cosmos, but it doesn't emit light, doesn't absorb it, doesn't interact with electromagnetic radiation in any way we can detect. It simply pulls. The tools for weighing the sky are surprisingly straightforward. Light tells us about visible matter. Stars shine, gas glows when heated, dust absorbs and re-emits radiation. By measuring brightness and temperature, astronomers can estimate how much ordinary matter is present in a given region. But light only goes so far. To understand the total mass, they turn to motion. When an object orbits another, its speed depends on the gravitational force holding it in place, which in turn depends on how much mass lies inside its orbit. A planet circling the Sun moves at a speed determined by the Sun's mass. If the Sun were suddenly more massive, the planet would need to move faster to avoid being pulled in. If the Sun lost mass, the planet could afford to slow down. This relationship between orbital speed and enclosed mass is a quiet but reliable witness. Even when mass is invisible, its gravitational signature appears in the motion of things around it. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the COME cluster, a dense congregation of galaxies bound together by their mutual gravity. He measured how fast individual galaxies were moving within the cluster, zipping around the cluster's centre like bees in a swarm. The speeds were alarmingly high. With only the visible mass from stars accounted for, the cluster should have flown apart long ago. There simply wasn't enough gravitational glue from the light-emitting matter to hold such fast-moving galaxies together. Zwicky calculated that the cluster needed far more mass than could be seen, perhaps hundreds of times more. He called it missing mass, a dry, accountant-like phrase that would echo through the decades. At the time, many dismissed his findings as an anomaly or an error in measurement. The idea that most of a galaxy cluster's mass could be invisible seemed implausible, almost absurd. But the numbers kept not adding up. The discrepancy became harder to ignore in the 1960s and 70s when Vera Rubin and her collaborators turned their attention to the rotation of spiral galaxies. They measured how fast stars and gas clouds orbit the centres of these galaxies at various distances from the core. The expectation was straightforward. Most of a galaxy's visible mass, its stars and gas, is concentrated toward the centre, so objects farther out should orbit more slowly, just as Neptune plods along its orbit more leisurely than Mercury races around the Sun. But that's not what they found. Instead, the rotation curves, graphs plotting orbital speed against distance from the galactic centre, stayed flat. Stars at the outer edges of galaxies were moving just as fast as those closer in, as if there were additional mass spread throughout the galaxy, extending far beyond the visible disk. This wasn't a small effect. The implied extra mass was enormous, often several times the mass of all the visible stars and gas combined. The rotation curves became a recurring line item in the cosmic ledger, more mass than light implies. Galaxy clusters, revisited with more modern instruments, told the same story from a different angle. Between the galaxies in a cluster sits vast amounts of hot gas, so hot it emits X-rays. By observing these X-rays, astronomers could weigh the gas and add it to the count of visible matter. They also measured the motions of galaxies within the cluster, as Zwicky had, but with better precision. And they studied the pressure and temperature of the gas itself, which must be held in place by the cluster's gravity. All three methods, light from stars, X-rays from gas and dynamics from motion, converged on the same conclusion. There is far more mass present than can be accounted for by anything that shines or glows. The extra mass doesn't emit light, doesn't heat up detectably, but it pulls relentlessly and consistently. Gravitational lensing added yet another layer of confirmation. According to Einstein's general relativity, mass warps space-time and light travelling through curved space-time bends. A massive object like a galaxy cluster acts as a lens, distorting the images of more distant galaxies behind it. The shapes of these background galaxies appear stretched, smeared into arcs or multiple images, in patterns that depend on the total mass of the foreground cluster. By carefully measuring these distortions, astronomers can map the distribution of mass in the cluster, regardless of whether that mass emits any light at all. Time and again, lensing maps reveal mass concentrations that don't align neatly with the visible galaxies or gas. There's a gravitational landscape sculpted by something unseen, a topography recorded in the bending of light. The lensing studies don't care whether the mass is bright or dark, they simply measure where space-time curves, and the curvature is always stronger than visible. Matter alone can explain. One particular collision between galaxy clusters provided an especially clear case. The bullet cluster is the name given to a system where two clusters have smashed into each other and partially passed through. The hot gas in each cluster, being made of ordinary matter, interacts electromagnetically. As the clusters collided, the gas clouds slowed down, colliding and heating up further, leaving a glowing blob of X-ray emitting gas lingering in the middle of the system. The galaxies themselves, being mostly empty space with stars far apart, passed through each other largely unscathed. But the gravitational lensing maps told a different story. The main concentrations of mass, as revealed by the bending of background light, were not centered on the hot gas, but rather on the clusters of galaxies themselves, which had sailed through the collision. This spatial separation was a smoking gun. Most of the mass in the system was in a component that didn't interact or slow down like normal matter. It felt gravity. It exerted gravity, but it didn't collide or radiate. It behaved exactly as dark matter should, invisible, non-interacting except through gravity, and dominant in the mass budget. Zooming out to the larger scales, the structure of the universe itself offers evidence. Galaxies are not scattered randomly across space, but are arranged in a cosmic web of filaments and sheets surrounding vast, nearly empty voids. This structure grew from tiny density fluctuations in the early universe, regions that were slightly denser than average, and gradually pulled in more matter through gravity. Computer simulations can model this growth, starting from the conditions shortly after the Big Bang and evolving forward through billions of years. When these simulations include only ordinary matter, the resulting structures grow too slowly and remain too diffuse. The universe ends up smoother and less clumpy than what we observe. But when dark matter is added, an invisible component that doesn't interact with light or itself except through gravity, the simulations suddenly match reality. The dark matter collapses first, forming a gravitational scaffolding, and ordinary matter flows along this invisible framework, gathering in the densest regions to form galaxies and clusters. The cosmic web is essentially a map of dark matter's distribution, with galaxies as bright tracers lighting up the nodes and filaments of an otherwise invisible skeleton. The cosmic microwave background provides yet another line of evidence, perhaps the most precise. This faint glow of microwave radiation fills the entire sky, the cooled remnant of the hot plasma that filled the universe when it was only a few 100,000 years old. Tiny temperature variations across the sky, spots slightly warmer or cooler than average, carry information about the density fluctuations that seeded all structure in the universe. These fluctuations also encode information about the composition of the universe, how much ordinary matter, dark matter, and dark energy there is. Decades of observations from satellites and ground-based telescopes have measured these temperature variations with extraordinary precision. The data are then fit to theoretical models that predict the pattern of fluctuations based on different cosmic ingredients. The best-fitting model is remarkably consistent across independent measurements and includes roughly 5% ordinary matter, about 27% dark matter, and the remainder in dark energy. Dark matter isn't just a footnote in this accounting. It's a dominant component, several times more abundant than all the atoms in all the stars, planets, and gas clouds put together. The cosmic microwave background is like a cosmic census form, filled out by the universe itself, and it clearly lists dark matter as a major entry. Given all this evidence, it's natural to ask whether dark matter might simply be ordinary matter that's too dim to see. Faint stars, cold gas, black holes, or other compact objects made of normal atoms. These possibilities have been carefully examined and largely ruled out. If dark matter were made of dim stars or cold gas, it would still interact with light in subtle ways, absorbing or emitting radiation at certain wavelengths, or leaving fingerprints in the abundances of light elements forged in the Big Bang. None of these signatures match what we observe. Surveys have also looked for compact dark objects like black holes or brown dwarfs by watching for microlensing events, brief brightenings of distant stars caused when a dark object passes in front of them and temporarily magnifies their light. While some such objects have been detected, they are far too rare to account for all the missing mass. The numbers just don't work. Most of the dark matter must be something fundamentally different from ordinary atomic matter, something that doesn't participate in electromagnetic interactions at all. The behaviour of dark matter in the early universe offers another clue. Particles can be classified by how fast they were moving when the universe was young. Hot dark matter consists of particles that were relativistic, moving at or near the speed of light, during the era when structures began to form. If dark matter were hot, it would have smoothed out small-scale density fluctuations, preventing galaxies and smaller structures from forming until much later. Simulations with hot dark matter produce a universe that's too smooth, with fewer galaxies and a different large-scale structure than we see. Light neutrinos, for example, would be a form of hot dark matter, and while neutrinos do exist and have a small mass, they cannot account for all the dark matter. Cold dark matter, by contrast, consists of particles that were moving slowly in the early universe, allowing them to clump together efficiently on all scales. Simulations with cold dark matter reproduce the observed cosmic web, the abundance of galaxies, and the hierarchy of structures remarkably well. Warm dark matter lies somewhere in between. This classification, hot, cold, warm, is another piece of the paperwork, narrowing down the properties of whatever dark matter is. If dark matter is made of particles, what might those particles be? One leading candidate is called a WMAP, short for weakly interacting massive particle. These hypothetical particles would have mass, comparable to heavy atomic nuclei, and would interact with ordinary matter only through gravity and the weak nuclear force, the same force responsible for certain types of radioactive decay. WMAPs would mostly pass through ordinary matter without leaving a trace, but very rarely. One might collide with an atomic nucleus, producing a detectable signal. WMAPs are appealing because they arise naturally in extensions to the standard model of particle physics designed to solve other problems, such as the hierarchy problem related to the mass of the Higgs boson. Another candidate is the axion, a much lighter particle proposed to solve a puzzle in the theory of the strong nuclear force. Axions would interact even more weakly than WMAPs, but under the right conditions they could be detected through their conversion into photons in the presence of a strong magnetic field. Sterile neutrinos, hypothetical cousins of the known neutrinos but even more aloof, are another possibility. Each of these candidates is not pulled from thin air, but is grounded in attempts to resolve multiple puzzles in fundamental physics, making them plausible entries on the list of suspects. Detecting dark matter directly is extraordinarily difficult. If dark matter particles rarely interact with ordinary matter, you need a very large detector and a very long time to catch even a single event. Direct detection experiments are built deep underground in mines or tunnels to shield them from cosmic rays and other background radiation that could mimic a dark matter signal. These detectors often use tanks filled with ultra-pure liquids like liquid xenon or argon, cooled to extremely low temperatures. The idea is simple. Wait for a dark matter particle to collide with a nucleus in the liquid, causing the nucleus to recoil and produce a tiny flash of light, or a small amount of charge. Years can pass with only a handful of candidate events, and even those are often ambiguous, potentially explainable by residual background radiation or detector noise. It's painstaking work, like auditors listening for the faintest click in a vast, mostly silent archive. So far, despite decades of effort and increasingly sensitive detectors, no clear, unambiguous dark matter signal has been confirmed. Particle colliders offer a complementary approach. At facilities like the Large Hadron Collider, protons are smashed together at enormous energies, briefly recreating conditions similar to those in the early universe. If dark matter particles can be produced in these collisions, they would immediately escape the detector without leaving a trace, but their presence could be inferred from missing energy and momentum. The total energy and momentum before a collision must equal the total after, so if some goes missing, it suggests invisible particles carried it away. Researchers have searched extensively for such signatures, but so far no convincing evidence for dark matter production has emerged. Indirect detection efforts take yet another tack, watching the sky for excess gamma rays, positrons or other particles that could result from dark matter particles annihilating each other or decaying. Some tantalizing hints have appeared over the years: an excess of gamma rays from the centre of the Milky Way, an unexpected abundance of positrons in cosmic rays, but none have withstood scrutiny as definitive proof. Each potential signal either fades with better data or finds a more mundane explanation. Not everyone is convinced that dark matter exists as particles at all. Some researchers have proposed that instead of adding invisible matter, we should modify our understanding of gravity. On scales the size of galaxies and larger, perhaps the force law that Newton and Einstein described breaks down or changes form. One well-known proposal is modified Newtonian dynamics, or MOND, which suggests that at very low accelerations, far below what we experience on Earth, gravity becomes stronger than Newton's law predicts. MOND can fit the rotation curves of many galaxies quite well without invoking dark matter. It's an elegant idea. Instead of adding a new, unseen component to the universe, you adjust the rules. But MOND and related theories struggle with other observations. They have difficulty explaining galaxy clusters, where the missing mass problem is even more severe than in individual galaxies. They don't naturally account for the patterns seen in the cosmic microwave background, or the success of large-scale structure simulations that include dark matter. The bullet cluster, with its clear spatial separation between ordinary matter and the gravitational mass, is particularly hard to explain without invoking an actual dark component that can pass through collisions unscathed. Modified gravity theories remain a minority view, not because they're wrong by default, but because dark matter, despite being unseen, provides a single, consistent explanation for a wide range of phenomena, while modified gravity often requires different tweaks for different contexts. Focusing back on individual galaxies, dark matter is thought to form vast halos that extend far beyond the visible disk of stars and gas. These halos are roughly spherical, or somewhat elongated, and they contain the bulk of a galaxy's mass. The exact distribution of dark matter within these halos is a subject of ongoing debate. Simulations of cold dark matter typically produce halos with a dense central cusp, where the density rises steeply, toward the centre. But observations of some galaxies, particularly small dwarf galaxies, suggest flatter central densities, a core rather than a cusp. This discrepancy has sparked extensive discussion. It might indicate a problem with the cold dark matter model, or it might reflect the complex interplay between dark matter and ordinary matter. Supernova, energetic outflows from massive stars, can blast gas out of a galaxy's centre, and the changing gravitational potential can redistribute dark matter, smoothing out the central cusp. Star formation, gas inflows, and feedback processes all leave imprints on the dark matter distribution. These are the fine print details of the inventory, the nuances that don't undermine the overall picture but add texture and complexity. So where do things stand? Observations from many independent lines of evidence support the presence of a dominant invisible mass component. Rotation curves, galaxy clusters, gravitational lensing, the cosmic web, and the cosmic microwave background all point in the same direction. There is far more mass in the universe than we can see, and this extra mass behaves like cold, non-baryonic matter that interacts with ordinary matter almost exclusively through gravity. The numbers are precise. Cosmological models can pin down the amount of dark matter to within a few % of the total mass-energy budget of the universe. The problem is firmly established. The missing entry on the balance sheet has a name, and its influence is mapped across cosmic scales. Yet the true identity of dark matter remains unknown. We know what it does, how much of it there is, how it clumps, how it shapes galaxies and clusters, but we don't know what it is. This is a rare situation in science, where the problem is well defined and the evidence overwhelming, yet the answer remains elusive. It's as if the universe handed us a detailed invoice with one line item labelled only as miscellaneous, but that miscellaneous item accounts for most of the total. Living with this uncertainty is part of modern cosmology. researchers continue to build more sensitive detectors, refine simulations, search for new particles at colliders, and scan the sky for indirect signals. Each null result narrows the parameter space, ruling out certain masses or interaction strengths for hypothetical particles. Each new observation of galaxy dynamics or large-scale structure adds another data point to the map. The search is incremental, methodical, and patient. There's no guarantee that dark matter will reveal itself in the next decade or even the next century. It might be composed of particles so weakly interacting that direct detection remains forever out of reach, knowable only through its gravitational effects. Or it might be something entirely unexpected, a phenomenon or particle type not yet imagined by current theories. The universe has surprised us before. For now, the ledger remains open. Dark matter behaves consistently, predictably, across every scale we can measure. It holds galaxies together, binds clusters, guides the growth of structure, and leaves its fingerprint in the ancient light of the cosmic microwave background. It is as much a part of the universe's architecture as stars and gas, even if it never emits a single photon. The fact that we cannot yet see or touch it directly does not diminish the confidence with which we trace its influence. Gravity is a faithful record keeper, and dark matter's presence is recorded in the motions of galaxies, the shapes of light bent around clusters, and the subtle ripples in the radiation from the early universe. These are not ambiguous hints, but clear, repeated signals, all pointing to the same conclusion. As the rain continues outside and the screen stays black, the thought settles in quietly. Most of the universe's matter is invisible to our eyes. It doesn't shine in any wavelength, doesn't heat up, doesn't leave trails we can follow directly. But it is there, shaping the cosmos, a quiet partner to the bright matter we see. The story of dark matter is not one of mystery in the sense of lacking evidence. It's a mystery in the sense of knowing a thing exists, measuring its effects with precision, yet still waiting to meet it face to face. It's a balance sheet with a placeholder, a line waiting to be filled in. The universe's accounting is incomplete, but not chaotic. The numbers, though, they don't quite add up in the way we'd like, are consistent, robust, and reliable. Dark matter is real in every way that matters, except visibility. And so we wait, patiently, for the day when the inventory is complete, when the missing entry finally gets a full name and description, when the ledger closes and the universe's balance sheet is reconciled. Until then, the rain falls, the galaxies spin, and the invisible mass holds everything together, unseen but undeniable. As the rain continues outside and the screen stays black, the thought settles in quietly. Most of the universe's matter is invisible to our eyes. It doesn't shine in any wavelength, doesn't heat up, doesn't leave trails we can follow directly. But it is there, shaping the cosmos, a quiet partner to the bright matter we see. The story of dark matter is not one of mystery in the sense of lacking evidence. It's a mystery in the sense of knowing a thing exists, measuring its effects with precision, yet still waiting to meet it face to face. It's a balance sheet with a placeholder, a line waiting to be filled in. The universe's accounting is incomplete, but not chaotic. The numbers, though they don't quite add up in the way we'd like, are consistent, robust, and reliable. Dark matter is real in every way that matters, except visibility. The implications ripple through everything we understand about cosmic history. In the earliest moments after the Big Bang, when the universe was a hot, dense soup of particles and radiation, dark matter was already there, woven into the fabric from the beginning. As the universe expanded and cooled, ordinary matter remained tightly coupled to radiation, unable to clump together because photons kept jostling atoms apart. But dark matter, immune to electromagnetic forces, could begin collapsing under its own gravity immediately. It started forming the first structures while ordinary matter was still a smooth, glowing fog. By the time the universe cooled enough for atoms to form and light to travel freely, the moment captured in the cosmic microwave background, dark matter had already created gravitational wells, pockets of enhanced density scattered across space. These were the seeds. When ordinary matter finally decoupled from radiation and could respond to gravity, it fell into the wells dark matter had prepared, like water flowing into depressions in the ground. The first stars formed in these dark matter halos. the first galaxies assembled where dark matter had already gathered. Every luminous structure in the universe, from the smallest dwarf galaxy to the largest supercluster, owes its existence to the invisible scaffolding dark matter provided. This dependence goes deeper than just structure formation. The timing of when galaxies formed, how quickly stars ignited, the evolution of cosmic chemistry, all of it is tied to dark matter's presence and properties. If dark matter were slightly warmer, moving faster in the early universe, small halos would have been erased, and the first galaxies would have formed later and been more massive. If there were less dark matter overall, structures would grow more slowly, and the universe today would be a lonelier, emptier place. If there were more, galaxies would be denser, more tightly packed, and perhaps less stable. The specific amount and behaviour of dark matter that observations point to are what allow the universe to produce the rich tapestry of galaxies we see, including ones like our own Milky Way, a spiral galaxy of moderate size, old enough and stable enough to harbour planets and the chemistry of life. It's a sobering thought. We exist not despite dark matter, but because of it. The invisible component isn't some extraneous detail, it's foundational, a necessary condition for everything that followed. Our own galaxy swims through a dark matter halo that extends hundreds of thousands of light years beyond the visible disk, far past the orbit of the outermost stars. The Sun, in its journey around the galactic centre, moves through this halo, and at any given moment countless dark matter particles are passing through the Earth, through the walls of buildings, through our bodies. If dark matter is made of WMAPs or similar particles, trillions upon trillions flow through each square centimetre every second, utterly unnoticed. The Earth is transparent to them, offering no more resistance than air offers to neutrinos. This constant, invisible rain of dark matter particles is one reason direct detection is so challenging. The interaction probability for any single particle is vanishingly small. A WMAP might pass through light years of lead without interacting once. Detectors must be large, patient, and extraordinarily sensitive to catch even a single collision, and even then distinguishing that collision from background noise is difficult. It's like trying to hear a whisper in a stadium full of noise, except the whisper happens only once a year, and you're not entirely sure what it sounds like. Some experiments have reported tantalizing signals over the years, candidate events that looked like they might be dark matter interactions. In the late 1990s and early 2000s, the DEMA experiment in Italy observed an annual modulation in their detection rate, a signal that rose and fell with the seasons in a way that could be explained by Earth's motion through a dark matter halo. As Earth orbits the Sun, it sometimes moves in the same direction as the Sun's motion through the galaxy, encountering a higher flux of dark matter, and sometimes moves against that motion, encountering less. This would produce a predictable annual variation. The DEMA result has persisted for decades, but other experiments using different detector materials and techniques have not seen consistent signals in the same parameter space. The lack of independent confirmation has left the field cautious. Dark matter detection is an arena where extraordinary claims require extraordinary evidence, and single experiments, no matter how carefully conducted, are not enough. Reproducibility and consistency across multiple detection methods are essential, and so far that consensus has not materialized. The community has also grappled with smaller-scale puzzles that might hint at gaps in the cold dark matter model, or at least in how we simulate it. One such puzzle involves the abundance of satellite galaxies around large galaxies like the Milky Way. Simulations predict that dark matter halos should host hundreds or even thousands of smaller subhalos, remnants of the hierarchical assembly process where small structures merge to form larger ones. Each subhalo could, in principle, host a small satellite galaxy, but observations show far fewer satellite galaxies than predicted subhalos. For a long time, this missing satellites problem was seen as a potential crisis for cold dark matter. However, more recent work suggests that the discrepancy may not be a failure of the dark matter model, but rather a reflection of how difficult it is for small halos to form stars. If a halo is too small, it may lack the gravitational pull to retain gas after the first supernovae explode, or it may be stripped of gas by the ultraviolet radiation from nearby galaxies. In other words, not every dark matter subhalo needs to light up as a visible galaxy. Many could remain dark, invisible clumps of matter with no stars. recent discoveries of extremely faint dwarf galaxies around the Milky Way, detected only because they pass in front of background stars or are caught in deep imaging surveys, have begun to fill in the expected population. The missing satellites may not be missing after all, just very dim. Another puzzle concerns the structure of dark matter halos on the smallest scales. Some simulations predict that halos should contain dense, smaller clumps within them, a graininess at scales far below what we can currently observe directly. If true, these clumps might leave subtle signatures, perhaps through their gravitational lensing effects on distant quasars, or through perturbations in stellar streams, long rivers of stars torn from disrupted dwarf galaxies. Researchers are actively searching for these signs, hoping that the fine structure of dark matter halos can reveal properties of the dark matter particle itself, such as its mass or interaction cross-section. So far the data are consistent with smooth halos, but sensitivity is improving, and future surveys may detect the predicted substructure or rule it out, refining the picture further. There is also the question of whether dark matter interacts with itself, even weakly. Most models assume dark matter is collisionless, meaning particles pass through each other as easily as they pass through ordinary matter. But some researchers have explored the possibility of self-interacting dark matter, where dark matter particles do occasionally collide with each other, exchanging momentum and energy. This would affect the shapes and density profiles of dark matter halos, potentially solving some of the small-scale puzzles like the core-cusp problem. If dark matter self-interacts, collisions in the dense centers of halos could transfer energy outward, puffing up the core and creating a flatter density profile. Observations of galaxy clusters, where collisions between clusters can separate the dark matter and gas in measurable ways, provide constraints on how much self-interaction is allowed. The bullet cluster itself places limits, but other clusters studied in detail have added to the picture. Current evidence suggests that if self-interaction exists, it's quite weak, but the door remains open, and the question is far from settled. The search for dark matter has also prompted physicists to consider increasingly exotic possibilities. What if dark matter isn't a single type of particle, but a whole hidden sector, a dark ecosystem with multiple particle species that interact with each other through forces we don't yet know? Just as ordinary matter includes protons, neutrons, electrons, and is governed by electromagnetism and the nuclear forces, dark matter might have its own complexity, its own periodic table, its own version of chemistry. If true, dark matter could form structures within structures, dark atoms, dark molecules, perhaps even dark planets or dark stars, objects made entirely of dark matter that exist alongside our own visible universe, but remain invisible and intangible to us. These ideas are speculative, but they're grounded in the recognition that we should not assume dark matter is simpler than the ordinary matter we know. Nature has surprised us with complexity before, and humility suggests we should be prepared for it again. Some theories even propose that dark matter might decay very slowly, over timescales comparable to the age of the universe. If dark matter particles are unstable, they would gradually transform into lighter particles, potentially releasing photons or other radiation in the process. Such signals would be faint, diffuse, and difficult to detect, but they could appear as subtle excesses in the spectrum of light from galaxies or clusters. A few anomalies, like an unexplained emission line at a specific energy seen in X-ray observations of galaxy clusters, have been tentatively attributed to dark matter decay, but alternative explanations involving known atomic processes are also possible. These hints are intriguing but not conclusive, and the search continues for a smoking gun, an unambiguous signal that can only be explained by dark matter doing something other than just pulling. The relationship between dark matter and dark energy, the other mysterious component of the universe's inventory, adds yet another layer. Dark energy is even stranger than dark matter, a form of energy that fills all of space and drives the accelerated expansion of the universe. Unlike dark matter, which clumps and forms structures, dark energy appears to be perfectly smooth, a uniform background that doesn't change over time or space. Together, dark matter and dark energy make up about 95% of the universe's total mass energy content. Ordinary matter, the stuff of stars, planets, and people, is a mere 5%, a rounding error in the cosmic ledger. The interplay between these components determines the fate of the universe. Dark matter slows the expansion through its gravitational pull, while dark energy accelerates it. The balance between them shapes the ultimate destiny of galaxies, clusters, and the cosmic web. If dark energy continues to dominate as current observations suggest, the universe will expand forever, growing colder, emptier and darker as galaxies drift apart and stars burn out. Dark matter, despite its abundance, cannot prevent this. It can only slow the inevitable, shaping the structures that exist while they can. Reflecting on the journey so far, it's striking how the evidence for dark matter has accumulated through such diverse methods. No single observation proves its existence beyond all doubt, but the convergence of independent lines of evidence creates a powerful case. Rotation curves from hundreds of galaxies, X-ray observations of dozens of clusters, gravitational lensing maps from multiple systems, the large-scale distribution of galaxies across billions of light-years, the precise measurements of the cosmic microwave background from satellites separated by decades, all tell the same story, all point to the same invisible component. This is the hallmark of a robust scientific conclusion. When many different experiments, using different techniques, performed by different teams, over many years, all arrive at the same answer. That answer is very likely to be correct, even if the underlying explanation is not yet fully understood. Dark matter is in this category. Its existence is supported by a web of evidence so dense and interconnected that removing it would require explaining away not just one puzzling observation, but an entire suite of them, each individually strong and collectively overwhelming. What remains is the identity question, and that question is genuinely open. The dark matter particle, if it is a particle, has not yet appeared in our detectors. The theoretical candidates remain hypothetical, their properties constrained but not confirmed. This is not a failure of science, but a reflection of how difficult the problem is. Dark matter is elusive by its nature, interacting so weakly that detecting it requires pushing technology to its limits and beyond. The experiments are marvels of engineering, operating at the edge of what's possible, waiting in silence for a signal that may come tomorrow or may never come in our lifetimes. The work is slow, methodical, and requires patience, qualities not always celebrated in a world that values quick answers and immediate results. But science, at its best, is patient. It's willing to sit with uncertainty, to live with open questions, to continue searching even when the path forward is unclear. And so, the universe's ledger remains open, the balance sheet incomplete. Dark matter is recorded on every line, in every equation, its presence undeniable, and its influence pervasive. It holds galaxies together, guides the formation of structure, and makes the universe as we know it possible. Yet it remains a name without a face, a force without a form, a mass without light. The search continues in underground laboratories, at particle colliders, in observatories scanning the sky, in computer simulations exploring parameter space, in theoretical workshops where physicists imagine new possibilities. Each effort adds a small piece to the puzzle, narrows the range of options, rules out another corner of possibility. Progress is incremental but real. The mystery is patient, and so are we. The rain continues to fall outside, steady and unhurried, as the galaxies spin through space, held together by something we cannot see but know must be there, waiting quietly to be understood. The next story is about to begin. Please relax and enjoy. The universe, for the most part, behaves itself. Stars burn through their fuel at predictable rates, planets trace ellipses around their suns with metronomic consistency, and galaxies spin like enormous patient pinwheels across billions of years. Tonight we're simply conducting a quiet audit of certain gravitational peculiarities, what you might call overachieving gravity wells, that have been accumulating entries in the cosmic ledger for quite some time. Nothing dramatic, nothing to worry about. Just a slow review of how an abstract mathematical curiosity became one of the central filing systems of modern astrophysics. In the 1700s, long before anyone had proper telescopes or any real sense of what stars actually were, two men independently stumbled onto an interesting calculation. John Migel, an English clergyman with a talent for natural philosophy, and Pierre-Simon Laplace, the French mathematician, both asked a simple question. What if an object was so massive and so compact that even light couldn't escape from it? At the time, light was thought to be made of tiny particles, little corpuscles zipping through space, and gravity was understood as a force that pulled on everything with mass. If light had mass, then gravity could slow it down, maybe even stop it entirely. They calculated something called escape velocity, the speed you'd need to break free from a gravitational pull, and realised that if you made an object massive enough or squeezed it down small enough, that escape velocity could exceed the speed of light. They called these hypothetical objects dark stars. The math was tidy, the logic sound, but without Einstein's relativity or any way to actually observe such things, the idea was filed away as a curious footnote. For more than a century it gathered dust in the margins of physics, an impractical thought experiment that led nowhere in particular. Then, in the early 20th century, Albert Einstein rewrote the rulebook. His general theory of relativity proposed something profoundly different. Gravity wasn't a force pulling objects together across empty space, but rather a consequence of mass telling space-time itself how to curve. Imagine the universe as a flexible grid, a vast sheet of graph paper that bends and warps wherever you place mass or energy on it. A planet rolls along the curves created by a star, not because the star is yanking on it with invisible strings, but because the planet is simply following the straightest possible path through curved geometry. Clocks tick at different rates depending on how deep you are in a gravitational well. Light, which always travels in straight lines locally, follows paths that appear bent when viewed from far away. Everything in the universe becomes a participant in this geometric dance, following the contours of space-time without complaint. Einstein wrote down a set of field equations, 10 interlocking differential equations really, that describe how mass energy and the curvature of space-time balance each other. They're the universe's rules of accounting, and like any good ledger, they have to stay balanced on both sides. Within months of Einstein publishing these equations, a German physicist named Karl Schwarzschild, serving on the Russian front during World War I, found an exact solution. He considered the simplest possible case, a perfectly spherical, non-rotating mass sitting alone in space. What does space-time look like around such an object? Schwarzschild worked through the math and delivered a precise description. For most purposes, far from the mass, everything looked normal. Planets would orbit just as Newton predicted. Light would curve slightly, nothing alarming. But as you moved closer, something strange appeared in the equations. There was a particular radius, now called the Schwarzschild radius, where certain mathematical terms went to infinity. The geometry seemed to break down, at least on paper. For a mass like the Sun, this radius was about 3 kilometres. For Earth, less than a centimetre. These numbers seemed absurdly small, far smaller than any real object could be squeezed. So for decades, physicists treated the Schwarzschild radius as a mathematical artifact, a quirk of the coordinate system, perhaps a sign that the equations needed different variables or a better interpretation. It was filed as a minor anomaly, not a physical thing you'd actually encounter. But stars, as it turns out, don't live forever. They spend most of their existence in a stable balance. Nuclear fusion in their cores produces outward pressure that holds them up against the relentless inward pull of their own gravity. It's a truce that can last billions of years. Eventually, though, the fuel runs out. For stars like our Sun, the end is relatively gentle. The core contracts into a white dwarf, a dense ember about the size of Earth, supported by what's called electron degeneracy pressure, a quantum mechanical effect that keeps electrons from being squeezed too close together. For more massive stars, the core can collapse further, crushing atoms until protons and electrons merge into neutrons, forming a neutron star, a city-sized sphere with the mass of a sun, held up by neutron degeneracy pressure. These are extreme objects, but they're still objects in a traditional sense. They have surfaces, structures, a kind of solidity. In the 1930s, an Indian astrophysicist named Subramanian Chandrasekhar calculated that there's a limit to how much mass a white dwarf can hold, about 1.4 solar masses. Beyond that, electron pressure simply isn't enough. A similar limit exists for neutron stars, somewhere around 2 to 3 solar masses, though the exact number is still debated because we don't fully understand how matter behaves at such densities. The troubling implication was clear. If a stellar core is massive enough when it collapses, There's no known force that can stop gravity from continuing to compress it. No pressure, no quantum effect, nothing in the standard physics toolkit can hold it up. The equation suggested that such a core would just keep collapsing, shrinking past the size of a neutron star, past any conventional stopping point, until it reached that problematic Schwarzschild radius, and perhaps beyond. This was deeply uncomfortable for many physicists. Surely nature had some mechanism, some last-minute reprieve that would prevent such an extreme outcome. Surely the universe wouldn't allow something so singular, so pathological. But the math kept leading in the same direction. By the middle of the 20th century, physicists like J. Robert Oppenheimer and his students were working through the details of gravitational collapse, following the equations past the point where intuition gave out. What they found was that once an object collapsed within its Schwarzschild radius, it formed a one-way boundary in space-time. Cross that boundary going inward, and you could never return or even send a signal back out, not without travelling faster than light, which relativity forbids. The terminology was awkward at first. People spoke of gravitationally completely collapsed objects, or frozen stars, because from the outside time dilation made it appear that anything falling toward this boundary would slow down and freeze just above it. But in the 1960s, the physicist John Wheeler popularised the term black hole, and it stuck. The name was slightly misleading. There's no actual hole, no tear in space-time, just a region where the geometry has become so steep that escape is impossible, but it was vivid, simple, and far easier to say than the alternatives. Once the label was in place, the concept became a file folder you could point to, discuss, refine. It made the uncomfortable idea manageable. So what is a black hole, really, in the calmest possible terms? It has two main features. First, the event horizon. This is the one-way boundary at the Schwarzschild radius. It's not a physical surface, there's no wall, no membrane. If you were falling through it, you wouldn't feel anything special at the moment of crossing. Locally, space-time is smooth. But from that point on, every path you could take, every possible future trajectory, leads inward. The geometry has tilted so steeply that inward is as inevitable as forward in time. Second, the singularity. Somewhere at the centre, the equations predict a point of infinite density and curvature. This is almost certainly a sign that general relativity is incomplete, that we need a theory of quantum gravity to describe what really happens there. But from the outside, it doesn't matter much. The horizon is the boundary that controls what we can observe and interact with. To an observer far away, anything approaching a black hole appears to slow down, redden, and fade, taking an infinite amount of time to actually cross the horizon. To the infalling object, time passes normally, and the crossing happens in finite proper time. It's just space-time following the rules, even when those rules become deeply strange. If black holes are invisible by definition, how do astronomers find them? They look for the effects. One of the earliest and most reliable methods involves binary star systems. Imagine a normal star orbiting an invisible companion. Gas from the star can spill over and spiral toward the unseen object, forming a disk of material that heats up through friction and magnetic interactions. As this gas accelerates and compresses, it reaches temperatures of millions of degrees and emits X-rays. Telescopes detect these X-ray sources, and by measuring the orbit of the visible star, how fast it moves, the period of its orbit, astronomers can calculate the mass of the invisible companion using straightforward Newtonian mechanics. If that mass exceeds the limits for white dwarfs and neutron stars, and there's no other plausible explanation, you've quietly identified a stellar mass black hole. Cygnus X1 was one of the first such cases, flagged in the early 1970s. No dramatic visuals, just a persistent X-ray signal and careful orbital data pointing to something compact and massive that couldn't be anything else. The centres of galaxies provided another, even more striking ledger entry. For decades, astronomers noticed that stars near the cores of many galaxies moved surprisingly fast, as if they were orbiting something enormous but invisible. In our own Milky Way, careful observations tracked individual stars looping around an apparently empty point called Sagittarius A. By plotting their positions year after year, astronomers traced full orbits for some of these stars, measuring periods and speeds with increasing precision. The math is simple. Orbital dynamics tell you the mass enclosed within the orbit. For Sagittarius A, the The numbers pointed to about 4 million solar masses packed into a region smaller than our solar system. There's no conventional cluster of stars or gas cloud that could be that compact and that massive without collapsing or producing light. The only explanation that fits the data is a supermassive black hole, sitting quietly at the galaxy's centre, organising the motions of stars around it like a heavy bookend holding up a long shelf. Light itself offers clues through gravitational lensing. When light from a distant galaxy passes near a massive object on its way to us, the curved space-time bends the light's path, splitting the background source into multiple images or arcs. This is how space-time acts as a lens, and the distortion pattern depends on the mass and distribution of the lensing object. Sometimes these patterns hint at compact, massive concentrations along the line of sight, and occasionally those turn out to be black holes, either isolated or at the centres of galaxies. The evidence arrives as careful measurements of brightness, position, and shape, cross-checked against models of mass distribution. It's detective. Work conducted with photon counts and sky coordinates, more ledger entries than spectacle. Then there are gravitational waves. According to general relativity, accelerating masses produce ripples in spacetime itself, spreading outward at the speed of light. These ripples are extraordinarily faint. Even violent cosmic events produce distortions measurable only in billionths of a metre. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first confirmed gravitational wave signal. The source was two black holes, each about 30 times the mass of the Sun, spiralling into each other and merging. The signal lasted a fraction of a second, a brief rising chirp in the data as the black holes circled faster and faster before coalescing. That chirp encoded their masses, their spins, their distance from us. It was cosmic drama recorded not as a movie, but as a clean, tidy signature on a graph. Since then, dozens more black hole mergers have been detected, each one adding a precise entry to our catalogue of these objects, and confirming that binary black holes exist, that they merge, and that spacetime really does ripple when massive objects accelerate. Most of the light we associate with black holes doesn't come from the black hole itself, of course. It comes from the accretion disk, the swirling mass of gas and dust that spirals inward. Material doesn't fall straight in because it usually has some angular momentum, some sideways motion. Instead, it settles into a flattened disk, orbiting faster as it moves closer, heating up through friction and compression. Magnetic fields threading the disk can extract energy and launch powerful jets perpendicular to the disk, carrying matter and radiation away at near-light speeds. This is how quasars work. Supermassive black holes at the centres of distant galaxies, actively feeding, producing more light than entire galaxies of stars. From our perspective, billions of light-years away, these appear as bright points that outshine everything around them. The black hole itself remains dark, a silent consumer at the centre, but the infalling material writes a brilliant entry in the sky's ledger, visible across most of the observable universe. It's now understood that supermassive black holes, millions to billions of solar masses, reside at the centres of most large galaxies. They're not the dominant mass of the galaxy. The stars and dark matter far outweigh them. But they occupy a central position, both literally and organisationally. Their gravity shapes the orbits of nearby stars. Episodes of active accretion can drive powerful outflows that heat or expel gas from the galaxy, potentially regulating star formation. Over cosmic time, these central masses grow through mergers with other black holes and by gradually accreting gas. They're like heavy bookends. Not the entire library, but stabilising presences that quietly influence how everything else arranges itself over billions of years. Imaging a black hole directly is a challenge, because by definition the object itself emits no light. What you can image is the shadow it casts against a glowing background. In 2019, the Event Horizon Telescope collaboration released the first such image, showing the supermassive black hole at the centre of the galaxy M87. The technique involved linking radio telescopes across the globe, from Hawaii to Chile to the South Pole, creating an effective dish the size of Earth. Each telescope recorded data, and later those data streams were carefully synchronized and combined using sophisticated algorithms. The result was an image of the black hole's shadow, a dark circle surrounded by a bright asymmetric ring of emission from the accretion flow. It wasn't a photograph in the traditional sense. It was a reconstruction, a detailed report built from millions of measurements, hours of observation, and patient computation. In 2022, they released a similar image of Sagittarius AI, our own galaxy's central black hole. Both images confirmed the predictions of general relativity in extreme conditions and provided direct visual evidence of the event horizon scale. In 1974, Stephen Hawking introduced a surprising twist. When you account for quantum field theory near the event horizon, black holes aren't entirely black. Pairs of virtual particles constantly pop into and out of existence everywhere in space, normally annihilating each other almost immediately. But near the horizon, one particle of a pair might fall in while the other escapes. From a distant observer's perspective, this looks like the black hole emitting radiation, as if it has a temperature. The effect is called Hawking radiation, and the temperature is inversely proportional to the black hole's mass. For a stellar mass black hole, that temperature is a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background, so in practice such black holes absorb more radiation than they emit. For supermassive black holes, the temperature is even lower. Only very small black holes, if they exist, would radiate significantly. Over unimaginably long timescales, far longer than the current age of the universe, a black hole left alone would slowly evaporate, shrinking as it radiates away its mass. It's less an immediate concern and more a note about long-term archival policy. Even black holes, given enough time, may not be permanent. Hawking radiation introduced a puzzle called the information paradox. Quantum mechanics says that information about the physical state of a system should never be truly destroyed. It can be scrambled or hidden, but in principle, it should always be recoverable. Classical black holes, however, seem to erase information. Everything that falls past the horizon is lost to the outside universe, hidden behind a one-way boundary. If the black hole then evaporates into featureless thermal radiation, where did the information about what fell in go? This tension between quantum mechanics and general relativity has prompted decades of theoretical work. Some proposals suggest information is stored on the event horizon in a holographic way, encoded in subtle correlations in the outgoing Hawking radiation. Others invoke exotic ideas like firewalls, quantum entanglement across the horizon, or new physics at the singularity. For now, the universe continues operating smoothly while theorists debate the correct filing protocol. It's a disagreement about how the records are kept, not whether they exist. There are more speculative entries in the black hole file. Primordial black holes, for instance, might have formed in the extremely early universe from density fluctuations, before stars even existed. If they exist, they could range from tiny masses to stellar scale, and might even contribute to dark matter. Microscopic black holes could theoretically form in high-energy particle collisions, though none have been observed and current theories suggest they'd evaporate almost instantly via Hawking radiation. Wormholes, hypothetical tunnels connecting distant regions of space-time, are often confused with black holes in popular media, but they're different solutions to Einstein's equations, generally requiring exotic matter with negative energy density to remain stable, and there's no evidence they exist in nature. Most of the practical cosmic bookkeeping is done by ordinary stellar mass and supermassive black holes, behaving in measurable, predictable ways. The rotation of black holes adds another layer to the filing system. Real black holes aren't perfectly static spheres like Schwarzschild imagined. They spin, sometimes rapidly, because the matter that collapsed to form them carried angular momentum. A rotating black hole drags space-time around with it, creating a region called the ergosphere just outside the event horizon, where nothing can remain stationary, not even light. This effect, frame dragging, means that space-time itself is rotating, and anything in that region gets swept along like a stick caught in a whirlpool. The mathematics describing rotating black holes comes from a solution found by Roy Kerr in 1963, and it reveals structures more complex than the simple Schwarzschild case. The event horizon is still there, but its shape and properties depend on how fast the black hole spins. Theoretical calculations suggest you could extract energy from the ergosphere, a process called the Penrose mechanism, where carefully aimed particles or waves could steal some of the black hole's rotational energy. In practice, magnetic fields threading the accretion disk might accomplish something similar, powering the intense jets seen in active galactic nuclei. The universe, it turns out, has built-in mechanisms for recycling energy, even from objects designed to trap everything. binary black hole systems offer particularly clean laboratories for testing general relativity. When two black holes orbit each other, they lose energy by radiating gravitational waves, causing their orbit to gradually shrink. As they spiral closer, the orbital period decreases and the gravitational wave signal increases in frequency and amplitude, producing that characteristic chirp. In the final moments before merger, the black holes are orbiting each other many times per second, moving at a significant fraction of light speed, deep in each other's warped space-time. The resulting waveform encodes detailed information about the masses and spins of both objects, the orientation of their orbit, and the properties of the final merged black hole. By comparing observed signals to theoretical templates computed from Einstein's equations, physicists can test whether general relativity accurately describes gravity in these extreme regimes. So far, the agreement is excellent. The universe follows the rules even when two of its heaviest objects collide at relativistic speeds. There's also the matter of intermediate mass black holes, a category that's proven surprisingly elusive. We have good evidence for stellar mass black holes, a few to a few dozen solar masses, formed from collapsing stars, and supermassive black holes millions to billions of times heavier. But black holes in between, perhaps a few hundred to a few 100,000 solar masses, have been harder to confirm. Some globular clusters and dwarf galaxies show hints of them, but the evidence is less definitive than for their smaller and larger cousins. Gravitational wave detections have started filling in this gap, with a few merger events pointing to black holes in the lower end of the intermediate range. How supermassive black holes grow so large so quickly in the early universe remains an open question, and intermediate mass black holes might be part of the answer, serving as seeds that merge and accrete gas over cosmic time. It's a missing piece of the evolutionary story, a gap in the ledger that observers are working to close. The interaction between black holes and their host galaxies forms a feedback loop that appears crucial to galaxy evolution. When a supermassive black hole actively accretes gas, the resulting energy output, radiation and jets, can heat or push away nearby gas, suppressing star formation. This prevents the galaxy from converting all its gas into stars too quickly, and may explain why the most massive galaxies have relatively old stellar populations. Conversely, when gas cools and falls toward the centre, it can fuel the black hole, triggering another episode of activity. Over billions of years, this cycle regulates both the growth of the black hole and the star formation rate of the galaxy. Observations show a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy's bulge, suggesting the two grow together in a coordinated way. The black hole is not just a passive resident, but an active participant in shaping its galactic environment, an administrative centre whose activity influences the entire institution. Tidal disruption events provide another window into black hole behaviour. Occasionally, a star wanders too close to a black hole, close enough that the difference in gravitational pull between the star's near and far sides becomes extreme. This tidal force stretches and tears the star apart, a process called spaghettification, which sounds dramatic but is really just differential gravity doing what differential gravity does. Some of the stellar debris falls into the black hole, producing a bright flare of radiation as it heats up in the accretion process. These flares can last months to years and have distinct observational signatures, a sudden brightening in a previously quiet galactic nucleus, followed by a gradual fade. Each event offers a chance to study how matter behaves in the final moments before crossing the horizon and to measure properties of the black hole from the light curve and spectrum of the disrupted material. They're rare, but ongoing sky surveys are catching more of them, adding yet another category to the observational files. The future of black hole astronomy looks toward even more sensitive gravitational wave detectors, both ground-based upgrades to LIGO and future space-based observatories like LISA, which will detect lower frequency waves from merging supermassive black holes across cosmic distances. Next-generation radio telescopes and continued observations with the Event Horizon Telescope will refine our images of black hole shadows and test general relativity with increasing precision. Multi-messenger astronomy, combining gravitational waves, electromagnetic observations and possibly neutrinos, will provide richer datasets for understanding the environments around black holes and the mechanics of matter under extreme conditions. Each advance adds detail to the portrait, sharpens the entries in the ledger, and occasionally surprises us with phenomena we hadn't anticipated. The universe remains an orderly place, but the order is subtle, and we're still learning to read it. So here we are at the end of the audit. Black holes began as a speculative calculation about dark stars in the 1700s, matured into a mathematical oddity in the early 20th century, and gradually earned a place as one of the fundamental structures of the universe. They're endpoints for massive stars, organizational centers for galaxies, sources of the most energetic phenomena we observe, and testing grounds for our deepest theories about space-time and quantum mechanics. They're not monsters or cosmic vacuum cleaners. They don't roam around devouring everything in sight. They're simply regions where gravity, following the rules to their logical conclusion, has created a one-way boundary in space-time. They record the history of collapsed stars, merged galaxies, long epochs of accreting gas. They shape the orbits of nearby matter. Occasionally they announce a merger with a brief gravitational wave signature, a quiet ping in our detectors. To a sleepy listener, they're less menacing and more like heavy, silent filing cabinets in the cosmic office, places where the universe sets aside material it's finished rearranging. We've learned to read the labels, check the contents indirectly, and slowly map the filing system. The paperwork is mostly in order, even if some of the deeper drawers remain locked. Good night. The next story is about to begin. Please relax and enjoy. The rain taps against the window of the small observatory control room, each drop catching the glow of monitor screens before sliding into darkness. Sarah watches the telemetry scroll past, numbers that represent a spacecraft sitting in nothing, balanced on the edge of falling forever. She's been awake for 36 hours straight, shepherding the telescope through its final approach to a point in space that doesn't really exist. Not as a place you could touch or see, just a sweet spot where the mathematics of motion allows a machine to hover without effort, almost. The coffee has gone cold again. Outside, the storm moves across the desert in grey sheets, obscuring the mountains. Inside, the room hums with the steady breath of computers translating signals that left the spacecraft 28 seconds ago, travelling at the speed of light across 1,000,000 miles of emptiness. 28 seconds is an eternity when you're trying to thread a needle with a robot the size of a bus. Approaching orbital insertion corridor, calls Marcus from the navigation console. His voice carries the careful neutrality of someone who's done this dance before, who knows that excitement leads to mistakes. Sarah nods, her fingers hovering over the command sequence that will fire the thrusters for exactly 17 seconds, nudging their telescope onto a loop around an invisible point that exists only in the language of gravity and spin. The Lagrange points aren't parking lots in any ordinary sense. They're more like those moments in a spinning top's wobble, where it seems to hang suspended, neither rising nor falling, caught in a negotiation between forces that should tear it apart. Between any two bodies locked in gravity's embrace, the Sun and Earth, Earth and Moon, a planet and its satellite, there exist 5 such moments frozen in space, 5 places where a smaller object can keep pace with the larger body's dance, without constantly burning fuel to stay in position. Sarah thinks of them as harbours, though that's probably too solid a word for what they really are. Harbours suggest docks and moorings, something you can tie yourself to. These are more like the eye of a hurricane, calm centres in a rotating storm of gravitational forces. You can rest there, but never truly relax. The universe is always trying to push you out, gently but insistently, and you have to keep correcting, keep adjusting. Tiny burns of hydrazine or pulses of ion thrust, whispers of force that add up to staying put. The one they're heading for sits 1,000,000 miles from Earth, directly opposite the Sun. From that vantage, the Earth, Moon, and Sun all cluster together in one direction, leaving the rest of the sky dark and cold and perfect, for looking outward into the deep night where galaxies sprawl like spilled salt across black cloth. This is L2, the second Lagrange point of the Sun-Earth system, and it's where humanity parks its most ambitious eyes. She remembers learning about orbits as a child, the simple picture of objects falling around Earth in neat circles. Later came the complication. Orbits are always falling, but falling sideways fast enough that the ground keeps curving away beneath you. You're perpetually missing the planet, threading the needle between escape and impact. But in a frame of reference that rotates with 2 bodies, say, a coordinate system that spins with the Earth as it circles the Sun, something strange happens. The centrifugal effects that emerge from that rotation add to the gravitational pulls in ways that create these 5 special regions where everything balances just so. not balanced like a ball on flat ground, stable and happy. More like a marble balanced on top of a beach ball, possible in theory, requiring constant attention in practice. Well, 3 of them anyway. L1, L2 and L3 are unstable saddle points, ridges you can perch on if you're careful. L4 and L5, the points that form equilateral triangles with the 2 bodies, are different. They're shallow bowls where objects can settle into lazy orbits, following tadpole or horseshoe paths that loop around the point without drifting away. Jupiter has thousands of asteroids lounging in its L4 and L5 points, fossil remnants from the solar system's formation, trapped in those gentle gravitational valleys. Burn sequence armed, Sarah says, and her voice sounds far away even to herself. This is the culmination of 8 years of design, 3 years of construction, 2 years of testing, and 6 months of travel. The telescope cost more than a small nation's GDP, carries instruments that can see wavelengths of light the human eye never evolved to detect, and right now depends entirely on 17 seconds of controlled fire. Marcus counts down. Mark in 10, 9, 8. The spacecraft doesn't actually sit on the point itself. That would be like trying to balance a pencil on its tip. Theoretically possible, practically absurd. Instead, it traces what they call a halo orbit, a 3-dimensional loop that circles the invisible point like a moth around a flame, except the flame isn't there and the moth is solar-powered and following equations that would have made Newton weep with joy. These orbits rise above and dip below the plane of Earth's orbit around the Sun, keeping the spacecraft in constant sunlight for its solar panels, while maintaining a clear view of both Earth for communications and deep space for science. 3, 2, 1, burn. The telemetry stutters, updates. The velocity vector shifts infinitesimally on her screen, rotating the spacecraft's trajectory from an approach hyperbola into the first graceful arc of its permanent waltz. Sarah holds her breath without meaning to, watches the numbers settle into their predicted ranges, green lights cascading down the status board like a slow waterfall of confirmation. Capture confirmed, Marcus announces, and the tension breaks like glass. Someone cheers in the back of the room. Sarah allows. Herself a smile, small and private, the kind you wear when you've just parked $1 billion machine in a spot that exists only as a solution to differential equations. The point they've reached has a strange property. From here, the Sun is always in the same direction, and so is Earth. The spacecraft's sun shield, a tennis court-sized structure of layered captain and aluminum, unfolded 2 weeks ago in a process that took 6 hours and aged Sarah 5 years, can block all 3 sources of heat at once. Behind that shield, in permanent shadow, the telescope's instruments will cool to just a few degrees above absolute zero, cold enough that their own heat won't swamp the faint infrared whispers from galaxies born when the universe was young. At Sun-Earth L1, a different class of spacecraft keeps watch. That point sits between Earth and Sun, upstream in the solar wind, and the machines there stare at the Sun's roiling surface, watching for eruptions that could damage satellites or power grids. They're sentinels, giving Earth anywhere from 15 minutes to an hour of warning when a coronal mass ejection comes howling outward at 1,000,000 miles per hour. From L1, you see the Sun's face clearly and constantly. No eclipses, no interruptions, just endless vigil. L3 sits opposite Earth on the far side of the Sun, and it's the least useful of the group. Too dynamically unstable, too expensive to reach, too difficult to communicate with when the Sun sits between you and your spacecraft for weeks at a time. Science fiction writers sometimes park secret planets there, hidden Earths riding our own orbit but forever out of sight behind the Sun's bulk. In reality, perturbations from other planets would reveal such a world quickly, and we've looked anyway, just to be sure. There's nothing there but empty space and unused potential. The Earth-Moon system has its own Lagrange points, closer to home and more immediately useful. EML1, sitting between Earth and Moon, serves as a conceptual gateway for missions heading to or from the lunar surface. EML2, beyond the Moon's far side, offers something more interesting. A place where a communications relay can hover, maintaining constant line of sight with both Earth and the Moon's hidden face, that hemisphere that always turns away from us, perpetually shy. Sarah watches the telescope begin its first science observations, cameras and spectrometers waking from cruise mode like a sleeper stretching after a long journey. The targets are prosaic at first, calibration stars, objects whose properties are well known, used to verify that the optics survived the voyage and the cryocoolers are working as designed. Later will come the real work, staring at patches of apparently empty sky for days at a time, collecting photons that left their sources when the universe was a fraction of its current age, light that's been travelling for most of cosmic history to reach this particular arrangement of mirrors and detectors. Station keeping will become routine, she knows. Every few weeks the flight dynamics team will calculate a small correction burn, a few meters per second of delta V to nudge the spacecraft back onto its nominal path. Solar radiation pressure, literal photons pushing on the sunshield, will perturb the orbit. The moon's gravity will tug irregularly. The model they use assumes two bodies, Sun and Earth, but reality includes Jupiter and Venus and Mars, all pulling in their own subtle ways, and the Earth itself isn't perfectly spherical, and the Sun's radiation pressure varies with the solar cycle. The universe is messier than the mathematics that describe it, and engineering is the art of succeeding despite that messiness. The halo orbit the telescope traces isn't circular. It's more of a lopsided oval in 3 dimensions, carefully chosen so that the spacecraft never passes through Earth's shadow. No eclipses means no thermal cycling, no batteries depleting and recharging, no stress on components designed to operate at constant cryogenic temperatures. The path keeps the sunshield properly oriented, always edge onto the sun, always blocking the view of Earth and Moon, maintaining that precious darkness behind which the telescope peers into deep time. Other spacecraft have called L2 home before this one. Early missions mapped the cosmic microwave background from here, measuring the afterglow of the Big Bang with exquisite precision, finding patterns in that ancient light that revealed the universe's composition and fate. Their data rewrote cosmology, turned speculation into measurement, answered questions humans had been asking since we first looked up, and wondered what all those lights meant. Sarah remembers studying those missions in graduate school, learning how they stabilized their orbits, how they calibrated their instruments, how they dealt with the slow accumulation of energetic particles that space hurls at anything that ventures beyond Earth's magnetic shield. L2 sits outside that protection, exposed to the solar wind and cosmic rays, and every spacecraft that goes there must armour itself accordingly, shielding its electronics and accepting that eventually radiation damage will end the mission. The advantages outweigh the risks. At L2, the thermal environment is predictable. Stable temperatures make for stable measurements, and stable measurements make for good science. The lighting is constant, which simplifies power management. Communications with Earth are straightforward. No occultations, no periods of enforced silence, and most importantly, the view is unobstructed. No warm Earth glowing in infrared, drowning out the faint signals from distant galaxies. Just cold darkness and patient observation. The engineering required to make it all work fascinates her in ways she doesn't fully understand herself. The sunshield unfolds like origami in reverse, layer after carefully designed layer, each one blocking a portion of the sun's heat, so that the final layer, closest to the telescope, reaches temperatures cold enough to freeze air solid. Attitude control keeps everything aligned, reaction wheels spinning to maintain orientation, momentum dumped occasionally by firing thrusters, a constant juggling act of angular momentum and propellant budgets. At L1, the engineering priorities differ. Spacecraft there face the sun directly, deliberately, instruments drinking in the light and radiation to monitor solar activity. They need different shields, different orientations, different orbits chosen to keep communications with Earth open, while staring into that nuclear furnace 93 million miles away. But the basic principle remains the same. Find the sweet spot, trace a loop around it, and nudge yourself back on course when you drift. The science that flows from these harbours transforms astronomy. Space weather predictions improve with better solar monitoring from L1. Exoplanet hunters use infrared telescopes at L2 to watch stars for the tiny dips in brightness when worlds transit their faces. Studies of star formation peer into dust clouds that visible light can't penetrate, seeing protostars ignite in their cocoons, and cosmologists map the structure of the universe itself, galaxy by galaxy, building 3-dimensional charts of matter's distribution across billions of light years. Marcus brings her another coffee, this one actually hot. "First light looks good," he says, and she nods, scrolling through spectra that mean nothing to her, but everything to the astronomers who will spend years analysing them. The data begins its journey earthward, packets of ones and zeros riding radio waves across the Gulf, arriving 28 seconds after they're sent, accumulating in storage arrays where scientists will sift through them like prospectors panning for gold. She thinks about the misconceptions, the questions journalists always ask when trying to explain these missions to the public. No, there's no gravity-free zone. Gravity is everywhere. It's the whole reason the Lagrange points exist. No, the spacecraft doesn't anchor to anything physical. There's no there, just a location where forces balance. And no, maintaining position doesn't require huge amounts of fuel, just tiny corrections, teaspoons of thrust spread over months and years, enough to counteract the slow drift that perturbations impose. The restricted three-body problem that yields these points is an approximation, she knows. Reality includes every massive object in the solar system, all pulling and pushing in their own ways. The sun isn't perfectly spherical. The Earth and Moon don't orbit in a perfect plane. Solar radiation pressure varies, but the Lagrange framework remains useful because it captures the essential dynamics, provides a map that's accurate enough for navigation even if it's not perfectly true. All models are wrong. Some are useful. Looking ahead, she imagines future missions, fuel depots at EML-1, staging points for lunar sorties and Mars missions, fleets of telescopes at L2, working in concert to achieve baselines impossible for any single instrument, communications relays at Earth-Moon L4 and L5, providing constant coverage of cislunar space, sample return missions using the Earth-Moon Lagrange points as waypoints, dropping off precious cargo before diving back toward the Moon or beyond, autonomous platforms that ride the weak stability boundaries, those gravitational manifolds that connect different Lagrange points, allowing nearly propellantless transfers if you're patient and clever about timing. Other worlds have their own Lagrange points, 5 accompanying every two-body partnership. Mars and the Sun, Jupiter and the Sun, where Trojan asteroids swarm by the thousand, even small asteroid moons create miniature versions of these same patterns. Wherever two objects dance in mutual orbit, the 5 notches appear, inevitable consequences of gravity and rotation. The rain has stopped, she realizes. Dawn lightens the eastern sky, and the desert emerges from shadow, brown and grey and beautiful in its austerity. Sarah stretches, joints popping, exhaustion finally catching up now that the critical phase is over. The telescope will orbit its invisible point for years, maybe a decade if the cryocoolers and electronics hold out, staring into darkness and finding light. She leaves Marcus to monitor the routine observations and steps outside, breathing air that smells of wet creosote and ozone. 1,000,000 miles away, a machine she helped design traces its loop around a point that exists only in mathematics, a harbour made of timing and geometry and tiny patient burns. It's not falling, and it's not floating. It's balanced in motion, perpetually catching up to two worlds that themselves never stop moving. Above her, invisible in the brightening sky, Earth continues its ancient orbit, and at 5 specific places in that orbit's geometry, spaces exist where humans have learned to park their ambitions, their curiosity, their hunger to see what the universe looks like from somewhere other than the bottom of a gravity well. The Lagrange points aren't destinations exactly. They're vantages, perches, quiet corners in a cosmos that never stops wheeling. Sarah thinks about all the light streaming toward that telescope right now, photons that began their journey before Earth existed, before the sun ignited, before anything but hydrogen and helium and darkness filled the universe. That light will arrive at precisely calibrated mirrors, bounce through precisely figured optics, strike precisely cooled detectors, and become data. Become knowledge. Become answers to questions nobody knew how to ask when she was young. The sun clears the horizon, and she raises a hand to shade her eyes. Somewhere out there, invisible and unreachable but precisely located, a point in space waits, and a spacecraft circles it like a faithful moon around a planet that isn't. There. It will stay for years, nudged and corrected, shepherded by engineers and guided by physics, until its fuel runs low, or its instruments fail, or its mission ends because there's nothing left to discover. But that day is far away. For now, the telescope stares into the deep black, and the data flows earthward, and Sarah stands in the desert dawn, tired and satisfied, thinking about harbours that have no docks and parking spots, that exist only in the language of motion and force. The universe keeps turning, and we've learned to find the still points in that turning, the places where we can rest, not forever, but long enough to see what needs seeing, to measure what needs measuring, to understand just a little more about this strange and beautiful cosmos we inhabit. She walks the perimeter of the facility, letting her mind drift the way it does when exhaustion becomes something close to meditation. The gravel crunches under her boots, and she notices details she normally wouldn't. The way the morning light catches on quartz fragments, the tracks of some nocturnal creature that crossed the path while she was inside watching numbers, the distant call of a hawk beginning its hunt. It occurs to her that she's been so focused on the far that she's forgotten the near, that the same physics that governs spacecraft also governs hawks and stones, and the way morning spreads across a desert. Inside, the team will be settling into the rhythm of operations, the long slow dance of maintaining a mission that measures its objectives in years rather than days. There will be anomalies to investigate, software patches to upload, science proposals to evaluate, budget meetings and status reports, and all the mundane machinery that keeps a spacecraft functioning across 1,000,000 miles of nothing. But right now, in this particular moment between the crisis of insertion and the routine of operations, there's a pause, a breath, a space where she can think about what they've actually accomplished. The transfer from Earth to L2 took 6 months, but it wasn't a straight line. Nothing in orbital mechanics ever is. The spacecraft followed what the navigators call a trajectory arc, spiralling outward from Earth's gravitational influence, while the sun's pull gradually took over as the dominant force. They fired the engines in carefully timed bursts, each burn calculated months in advance but adjusted in real time based on tracking data, nudging the path until it intersected with the halo orbit at just the right angle and velocity. Too fast and the spacecraft would overshoot, sailing past the point into the solar system's depths. Too slow, and it would fall back toward Earth, wasting fuel and time in a second attempt. Sarah had dreamed about those burns, literally dreamed about them in the weeks leading up to each maneuver. In her dreams, the numbers were always wrong, the velocity vectors pointing in impossible directions, the spacecraft tumbling uncontrolled while she watched helplessly from her console. She knows enough about psychology to recognize anxiety expressing itself in the language of her profession, but knowing doesn't make the dreams any less vivid or the relief of success any less sweet. The concept of weak stability boundaries fascinates her more than it probably should. These are regions of space where the gravitational influences of multiple bodies create channels, invisible highways that a spacecraft can follow with minimal propellant expenditure. They're related to the Lagrange points, but more extensive, forming networks that connect different parts of the solar system in ways that aren't obvious from simple two-body orbital mechanics. Some missions have used these pathways to reach the moon or asteroids, trading time for fuel, taking months or years to coast along these gravitational rivers, rather than burning directly to their destinations. She imagines a future where spacecraft routinely use these manifolds, hopping from one Lagrange point to another like stones across a stream, building up speed or changing direction by carefully timing their passages through each point's sphere of influence. It would require patience and precision, but both are cheaper than propellant when you're trying to move large masses across interplanetary distances. Fuel depots at the Lagrange points could serve these travellers, autonomous stations dispensing hydrazine or xenon to spacecraft that need a top-up before continuing their journeys. The Earth-Moon L4 and L5 points remain largely unused despite their stability. They sit 60 degrees ahead of and behind the Moon in its orbit around Earth, forming equilateral triangles with the Earth and Moon at the other two corners. Unlike L1, L2 and L3, which require constant correction to maintain, L4 and L5 are gravitationally stable, at least stable enough that small objects can linger there for thousands or millions of years without much perturbation. Earth has at least one confirmed Trojan asteroid at L4, a small rock designated 2010 TK7 that traces a complex path around the point, neither approaching nor receding, caught in the gravity well like a marble rolling around the rim of a bowl. Some proposals suggest placing communication satellites at Earth-Moon L4 and L5, creating a permanent infrastructure for cislunar operations. From those vantage points, you could see both Earth and Moon simultaneously, providing continuous coverage of the lunar surface, including the poles, where permanent shadow holds deposits of water ice that future missions might harvest for propellant and life support. The geometry is elegant. 5 points, 3 of them unstable ridges, 2 of them stable valleys, all of them useful in different ways, all of them consequences of the same fundamental physics. Sarah wonders what Lagrange himself would think of the uses we've found for his mathematical curiosities. Joseph Louis Lagrange worked out the 5-point solution in 1772 while studying the three-body problem, how three mutually attracting masses move under their own gravitation. It was pure mathematics to him, an interesting puzzle in celestial mechanics with no obvious practical application. He couldn't have imagined spacecraft, or that humans would someday need parking spots in space, or that his equations would guide machines carrying instruments that could detect light from the universe's childhood. That's the way of mathematics, she supposes. You discover patterns and relationships because they're interesting, because they satisfy some aesthetic sense of order and beauty, and only later, sometimes centuries later, does someone find a use for them. Number theory was recreational mathematics for thousands of years before modern cryptography made it the foundation of digital security. Calculus was Newton and Leibniz playing with infinitesimals before it became the language of physics and engineering. And Lagrange's 5 points were curiosities before they became addresses. Marcus appears in the doorway, squinting against the brightening sky. "You should get some sleep," he says, and it's not a suggestion so much as an observation of obvious fact. Sarah nods but doesn't move immediately. She's reluctant to leave, even though the critical phase is over, and there's nothing she can do now that the automated systems can't handle better. There's a possessiveness that comes with working on a mission for years, a feeling that the spacecraft is somehow hers, that she needs to watch over it personally. It's irrational, but she's learned that most feelings about space missions are. "How's the thermal balance?" she asks, because she can't quite let go yet. Marcus smiles, recognizing the delay tactic. Within nominal range, the sunshield is performing exactly as modelled. Cold side holding at 47 Kelvin, warm side at 300. The cryocoolers are cycling normally. Everything's fine, Sarah. The spacecraft doesn't need you staring at it to keep working. She knows he's right, but the knowledge doesn't make leaving any easier. This is the paradox of automation. The better the systems work, the less necessary humans become. But that doesn't stop humans from feeling responsible. They've designed autonomy into every aspect of the mission. Fault protection routines that can diagnose and respond to problems without waiting for commands from Earth. Science scheduling algorithms that optimize observations based on current conditions. Even the station-keeping burns can be triggered automatically if the orbit determination software detects excessive drift. The spacecraft could, in theory, operate for months without human intervention. But theory and practice are different countries, and humans excel at handling the unexpected. The edge cases that no algorithm anticipated. So there's always someone watching, always someone ready to intervene if the automation makes a choice that seems wrong or dangerous. It's a strange partnership, humans and machines collaborating across 1,000,000 miles of vacuum, each doing what they do best, trusting each other to handle their respective domains of expertise. Sarah finally allows Marcus to guide her back inside through the control room where the night shift is handing over to the day shift, through hallways that smell of coffee and electronics, and the particular staleness that comes from buildings where the windows never open, to the small apartment the facility provides for operations personnel during critical phases. She falls asleep within minutes of lying down, her dreams mercifully empty of tumbling spacecraft and incorrect velocity vectors. When she wakes, it's mid-afternoon, and the light through the window is harsh and bright. She checks her phone before doing anything else, looking for alerts, anomalies, anything that might require her attention. There's nothing urgent, just the routine status updates that accumulate when a spacecraft is operating normally. The telescope has completed its calibration sequence and moved on to early science observations. Some distant galaxy cluster is having its portrait taken, light from 1 billion years ago focused onto detectors that translate photons into electron counts, into digital values, into scientific understanding. She showers and dresses and makes her way back to the control room, moving through the facility with the easy familiarity of someone who's spent years in these corridors. The control room is quieter now, the urgency of insertion replaced by the steady concentration of normal operations. Fewer people at the consoles, less chatter, everyone focused on their particular subsystem or instrument. This is what most of a mission looks like. Long stretches of routine punctuated by occasional moments of interest or concern. The flight dynamics team is huddled around a monitor discussing something in low voices. Sarah drifts over, curious. They're looking at the orbit determination solution, the mathematical reconstruction of where the spacecraft actually is, based on tracking data from Earth's network of radio dishes. "We're about 15 kilometres off the nominal path," one of them explains when he notices Sarah watching. "Well, within tolerance. But we're planning a small correction burn for next week to tighten things up. 3 metres per second should do it." 15 kilometres sounds like a lot until you remember that the halo orbit itself is hundreds of thousands of kilometres in diameter. At this scale, 15 kilometres is like parking slightly crooked in a space large enough to hold a city. Still, precision matters in spacecraft operations, and letting small errors grow into large ones is how missions fail. Better to correct early and often, maintaining tight control even when the margins are comfortable. The burn planning process is intricate, a choreography of orbital mechanics and propellant budgets and thermal constraints. You can't just fire the thrusters. Whenever you want, the spacecraft has to be in the right orientation, the sun angles have to be acceptable, the communications link to Earth needs to be open so you can monitor the burn in real time, and you have to make sure the exhaust plume from the thrusters won't contaminate the telescope's optics or the sunshield's surfaces. Each burn requires days of preparation, checking and rechecking the calculations, simulating the maneuver in software, briefing the entire operations team on what will happen and what to do if it doesn't. Sarah finds it beautiful in its complexity, the way everything connects to everything else, how you can't change one parameter without affecting dozens of others. It's like a vast multi-dimensional puzzle where the pieces are constantly shifting, and the goal is to maintain a configuration that allows the telescope to do its science, while keeping all the subsystems healthy and the spacecraft safely parked in its invisible harbour. The engineers who designed the mission spent years thinking through these interactions, building margin into every system, anticipating failure modes and providing backup options, trying to imagine every possible problem and its solution. And yet, despite all that preparation, surprises still occur. They always do. Space is an unforgiving environment full of phenomena that don't appear in textbooks. Micrometeoroid impacts that create unexpected vibrations, solar storms that interfere with communications, cosmic rays that flip bits in computer memory, thermal gradients that cause structures to flex in ways the models didn't quite predict. Most of these anomalies are minor, solved with a software patch or an adjustment to operations procedures, but occasionally something more serious happens, and that's when the real expertise of the operations team shows itself. The ability to diagnose problems across 1,000,000 miles of distance with limited telemetry and even more limited ability to interact with the spacecraft. Sarah has seen missions fail, has watched helplessly as spacecraft died from causes that were obvious only in retrospect. A stuck valve, a short circuit, a software bug that should have been caught in testing, small failures that cascade into total loss when you're in space and can't send a repair crew. She's learned to appreciate the fragility of these missions, how much has to go right continuously for years to achieve the science goals. Every successful observation is a small miracle of engineering persistence. The universe keeps turning while she thinks these thoughts, Earth orbiting the Sun, the Moon orbiting Earth, and at 5 invisible points in that dance, humanity maintains its tenuous presence, watching and measuring and trying to understand. The next story is about to begin. Please relax and enjoy. A lone spacecraft approaches one of Saturn's smaller shepherd moons, designation S47, a tumbling fragment barely 15 kilometers across that dances at the outer edge of the ring where ice crystals catch starlight like scattered diamonds. The mission parameters are simple. Collect samples from the ancient surface, map the gravitational anomalies that shouldn't exist in something so small, and return before the narrow launch window closes in 48 hours. But as the landing module touches down on the spongy fractured regolith, the geologist notices something impossible in the spectrometry readout. Organic compounds, complex chains that mirror the signatures detected in Enceladus's plumes 200 million kilometers away, and beneath them, a thermal gradient suggesting the moon isn't the dead rock everyone assumed. The pilot wants to leave immediately, stick to the timeline, but the geologist convinces her to deploy the deep drill. Just one borehole, and what comes up in the core sample changes everything. Layers of water ice mixed with salts and amino acids, and stranger still, microscopic chambers in the ice matrix that look almost cellular, almost purposeful. They're not alone out here, not in the way anyone expected, and the question becomes whether they're looking at contamination from Enceladus's distant fountain, or whether something about Saturn's system, the constant exchange of material between rings and moons, the electrical currents that thread through the magnetosphere. The patient stirring of tides across billions of years has created not one place where the chemistry of life can begin, but many scattered across dozens of small worlds that brush against each other in the dark. Back on the ship, analysing the samples in the cramped laboratory, they discover the organic structures aren't quite like anything in Earth's tree of life, but they're not entirely alien either, as if the recipe is universal, but each kitchen adds its own variations, and the pilot makes the call that will end her career or make it legendary. They're not going home on schedule. They're going to spend their remaining fuel budget visiting 3 more Shepherd moons, checking whether this is an isolated anomaly, or whether Saturn has been running a quiet experiment in prebiotic chemistry right under humanity's observations for 50 years. The second moon yields similar results, but the structures are more complex, almost like they've had more time to develop, and the third moon, which orbits just inside the E-ring where Enceladus's ice grains fall like snow, shows clear evidence of layered deposits, each ice fall bringing new organic material, new possibilities, building up sediments of potential over geological time. By the fourth moon they're running on fumes and emergency reserves, and what they find isn't just chemistry anymore but something that might be metabolism, icebound pockets where chemical gradients drive slow reactions that look almost like breathing. And the geologist realises they're looking at the earlier stages of something profound. Not life exactly, but pre-life. The patient assembly of components in a freezer that paradoxically preserves and enables complexity, because molecules don't break down in the cold, they just wait, accumulating in higher and higher concentrations until the threshold is crossed. But there's a problem, several problems actually, starting with the fact that they no longer have enough fuel to make the journey home, and ending with the fact that Earth needs to know about this immediately, not in 5 years when the next mission arrives, because if this is happening at Saturn, then it's probably happening at Jupiter too, round Europa and Ganymede where the conditions are even better, and maybe it's happening in the Uranian system and around Triton and in the sub-ice oceans of 100 Kuiper Belt objects that haven't even been discovered yet, which means the solar system isn't mostly empty space with a few pockets of interest. It's a garden, or a laboratory, or a network of connected experiments all running in parallel. They send the data burst, compress everything they've learned into a tight beam transmission aimed at Earth, knowing it will take over an hour to arrive and years to be fully understood, and then they make the decision that nobody trains for in mission simulations. They're going to crash land on Enceladus, use the last of their fuel to match orbits with the one moon in the system that's definitely active, definitely connected to the processes they've been observing, and if they survive the landing, a long shot given that the terrain near the Tiger Stripes is fractured and unstable, they'll have front row seats to the source. The descent is controlled chaos, the ship's heat shield ablating as they punch through the thin atmosphere of ejected particles, the surface coming up fast, too fast, and the pilot pulls off a miracle, skidding across smooth ice plains before coming to rest in a field of ice boulders 3 kilometres from the nearest active vent. They have life support for 6 days, no way to launch, no rescue possible for years, but they have instruments, curiosity, and the knowledge that they're standing on the most important square metre in the solar system. The first EVA takes them to the edge of a tiger stripe, where the ice is young and blue and fractured into geometric patterns that reveal the stresses below, and they can feel the moon breathing, not metaphorically but literally, rhythmic pulses of pressure as tidal forces squeeze and release the interior, and in the cracks they see fresh ice constantly forming, crystallizing from below, bringing up dissolved minerals and organics in concentrations that make the Shepherd moon samples look dilute. They collect everything they can carry, knowing each sample is irreplaceable, and as they work, the geologist starts sketching a theory. What if Enceladus isn't unique? What if it's the beating heart that supplies the entire system? The plumes carrying pre-life chemistry out into the E-ring, where it gets deposited on every moon that crosses the band, seeding them all with the same starter kit, and over time, millions or billions of years, each moon develops its own variation depending on its composition, its orbit, its tidal heating, creating not separate experiments, but connected ones, a network where success on one world can propagate to others. The pilot isn't convinced, argues that the chemistry is too fragile, that radiation and vacuum would destroy anything complex before it could spread, but the geologist counters with the ice itself. Each grain is a tiny spaceship, frozen solid, protecting its cargo for the years or decades it takes to drift from moon to moon, And maybe that's exactly the timescale that matters. Not the quick chemistry of warm worlds, but the patient accumulation of cold ones. They spend days analysing samples in the ship, running every test they can improvise, and the patterns become clearer. The organic compounds aren't random, they're structured. They're selecting for stability and complexity. They're building towards something, and the question stops being whether this could lead to life and becomes how long until it does. On the 5th day, the pilot picks up a signal, faint and scattered, someone else in the system, and when they decrypt it, they discover it's a Europa mission that launched 2 years ago, just arrived, and they're seeing the same things: organic chemistry in the ice, thermal vents at the seafloor, signs of chemical gradients that look biological even if they're not, and suddenly the two crews are comparing notes across the gulf between Saturn and Jupiter, realizing that they're documenting the same process at different stages, Europa further along because the ocean is deeper and warmer, Saturn still in the early phases but with more worlds participating, and together they start building the bigger picture. By the 6th day, they're running out of air and out of time, and the geologist records a final message, not for the rescue mission that might come in 3 or 5 or 10 years, but for whoever finds their data cache. Keep looking at the small moons, the ones everybody ignores because they're too small to have interesting geology, too cold to have interesting chemistry, because that's where the real story is. In the quiet exchange of materials, the patient cycling of ice and organics, the way Saturn's rings act as a distribution system spreading ingredients from the active moons to the dormant ones, creating a system-wide metabolism that operates on timescales humans barely comprehend. They seal the data in a hardened capsule and place it in the ice near the ship, and then they do the only thing left. They walk out across the ice plains toward the nearest active vent, carrying their instruments, observing until the end, and as they approach the vent, the pilot notices something the geologist missed. Tiny structures in the ice around the fractures. Patterns that look almost like colonies, like communities of chemical reactions that have organised themselves around the energy source. And she realises they're not just observing pre-life anymore, they're observing the threshold, the moment when chemistry becomes something else, something that responds to its environment, something that propagates, something that might, given enough time and enough moons and enough exchanges of material across the rings, become what humanity would recognise as alive. The last transmission is just coordinates and a single line. We found the garden, and it's bigger than we thought, and as the signal fades, the two crew members stand at the edge of the vent watching the plume rise kilometres into the black sky, carrying with it the raw materials of biology, spreading them across Saturn's system like seeds in a cosmic wind, and somewhere in orbit their ship's automated systems are still recording data, still measuring the flux of organics, still documenting the quiet mechanics of how worlds share their chemistry, and on Earth the first fragments of their transmission are being decoded, and teams are already planning new missions, faster ships, better instruments, because humanity has just learned that the solar system isn't a collection of isolated worlds but a connected network, a web of relationships where moons talk to each other through rings and plumes and the slow traffic of ice grains. And the question is no longer whether life exists beyond Earth, but how many different experiments are running simultaneously, how many different pathways are being explored, how many quiet gardens are growing in the cold, dark places that orbit the giant planets, waiting patiently for someone to notice them. 3 years pass before the rescue mission reaches Saturn, and in that time the data from the lost crew transforms everything humanity thought it knew about the outer solar system, not just confirming that organic chemistry is widespread, but revealing patterns that suggest the process isn't random at all, that there's something almost orchestrated about the way materials flow between worlds, the way certain shepherd moons seem to act as reservoirs while others function as mixing chambers, the way the ring system itself appears to sort particles by size and composition in ways that maximize distribution efficiency. And while nobody is suggesting intelligence or design, the mathematics of it are elegant enough to make physicists uncomfortable. The rescue ship arrives with a crew of 12, not 2, and their mission parameters have expanded exponentially. Retrieve any remains, recover all data storage, and most critically, establish a permanent research station on Enceladus, because the political and scientific consensus is that humanity can't afford to study this phenomenon in brief flybys anymore. That understanding the origin of life, or the multiple origins of life, or the continuous creation of almost life, requires patient observation measured in years, not days. They find the original ship exactly where the automated beacon said it would be, partially buried in ice accumulation, and inside the data cores are intact, filled with observations that the crew kept recording even as their oxygen ran low, detailed measurements of plume composition variations, thermal maps of the tiger stripes showing how the vents pulse in response to Saturn's tidal cycle, and most hauntingly a series of microscope images showing the progressive organisation of organic compounds around energy gradients, like watching evolution in fast forward, except it's not evolution yet. It's the prelude, the sorting and testing that comes before natural selection has anything to select. They don't find bodies, not at first, but 3 kilometres away near the coordinates from the final transmission, they discover 2 suits, sealed and positioned carefully, as if the occupants simply decided to become part of the landscape they were studying. And when the recovery team opens the suits carefully, reverently, they find them filled with ice samples, dozens of vials and containers packed around the life support systems, a final act of scientific dedication that makes the rescue crew weep inside their helmets because they understand exactly what it means. These 2 people chose to turn themselves into cargo containers, to preserve one more set of irreplaceable observations, even if they couldn't survive to analyse them. The samples are extraordinary, showing a progression of complexity that the crew must have been tracking in their final hours, and among them is a vial labelled simply Threshold, that contains structures so organised, so responsive to their chemical environment, that the mission's biologist refuses to classify them as non-living, inventing instead a new category she calls proto-animate, to describe chemistry that has crossed some invisible line into intentionality, into persistence, into something that wants to continue existing, even if it doesn't yet know how to reproduce. The research station goes up quickly, prefabricated modules anchored into stable ice with deep pylons, and within weeks they're operational, running experiments around the clock. And the first discovery is that the tiger stripes aren't static features, but dynamic, shifting slightly in response to tidal stress, opening new vents and closing old ones in a rhythm that repeats every Saturn orbit. And someone realizes that this rhythm itself might be crucial, that the periodic exposure to vacuum and radiation when vents seal might actually be part of the selection process, weeding out fragile chemistry and preserving only the structures robust enough to survive dormancy. They start mapping the entire E-ring in detail, tracking individual ice grains as they spiral outward from Enceladus, and they discover what the original crew suspected. The ring isn't uniform, it's structured, with distinct bands carrying different organic signatures depending on which vent they originated from. And the shepherd moons don't just randomly accumulate this material, they preferentially capture certain bands based on their orbital resonances, which means each small moon is receiving a curated selection of chemistry, not a random sample, and over geological time this non-random distribution could lead to different evolutionary experiments on different worlds, each starting with a slightly different toolkit. The implications spiral outward faster than anyone can track them. If this is happening at Saturn, then Jupiter's system must be even more complex, with Io's volcanic output adding sulfur chemistry to Europa's water, and Ganymede's magnetic field creating unique radiation environments that might drive entirely different reaction pathways. And someone points out that this means the Galilean moons aren't just 4 interesting worlds, they're 4 connected laboratories, running parallel experiments with slightly different initial conditions, and the results from one can propagate to the others through particle exchange and magnetic coupling. The Europa team, still operating in Jupiter's system, confirms this within weeks. They're detecting organic compounds in their ice cores that match Io's sulfur signature, mixed with native water chemistry in combinations that don't occur naturally on either world alone, which means the moons are collaborating, exchanging notes in a language written in chemistry and electricity. And the timescale for this exchange isn't human, it's geological. Millions of years of patient trading that has built up a chemical complexity neither world could achieve alone. Someone on the research station starts calling it the slow internet, and the name sticks. A network of worlds communicating through physical exchange of materials, through magnetic field interactions, through the gradual redistribution of particles by ring systems and plasmatoruses, operating on bandwidths measured in grams per century, but with a data capacity that spans billions of years. And the question becomes whether this network has been running since the solar system formed, or whether it took time to establish. Whether there was a moment when the first organic molecules from one world reached another and found conditions suitable for survival, bootstrapping a process that has been accelerating ever since. The research team starts looking at older data with new eyes, re-examining images from the Voyager flybys in the 1980s, and they find evidence that the tiger stripes were active even then, probably active for millions of years before that, which means Enceladus has been seeding Saturn's system for geological ages, and if the process is that old, then some of the shepherd moons might contain not just proto-life but actual life. Organisms that have had millions of years to evolve in their tiny, frozen niches, and suddenly the mission profile changes again. They need to visit those moons with sterile equipment, need to be careful not to contaminate them with Earth life, or disrupt whatever processes might be unfolding there, and the ethics committees back home start arguing about whether humanity even has the right to study these worlds if they're already occupied, whether observation itself is a form of interference that could derail experiments that have been running since before humans existed. But the argument is academic because the missions are already launching, a fleet of small probes designed to visit every significant moon in Saturn's system with minimal contact, just spectroscopy and magnetic field mapping and particle collection, and what they find is staggering. Organic chemistry on every single world that spends time in the E-ring, increasing complexity correlated with proximity to Enceladus and with the duration of exposure, and on 3 of the smallest shepherd moons, the ones that orbit directly through the densest part of the ring, they find chemistry that's definitely animate. Microbial colonies living in ice-bound pockets, metabolizing sulfur compounds and perchlorate salts, and producing waste products that other colonies consume, creating little ecosystems barely visible under the highest magnification, but unmistakably alive, unmistakably structured, unmistakably doing what life does, persisting, adapting, spreading to every available niche. The discovery breaks across Earth like a wave, not the distant possibility of life on Mars, or the theoretical oceans of Europa, but actual, confirmed living organisms in Saturn's system, and the philosophical implications are immediate. Life isn't rare. It's not a fragile accident that requires perfect conditions. It's a natural consequence of chemistry plus energy plus time, and if it emerged in Saturn's system despite the cold and darkness and radiation, then it probably emerged in Jupiter's system too, and probably in the Uranian system, and probably around Neptune, and probably in the subice oceans of large Kuiper belt objects, and probably around other stars, and the Fermi paradox suddenly seems less paradoxical, because maybe the galaxy isn't silent. Maybe it's just that life spends its first billion years in places like this, quiet and cold and patient, and most of it never makes it to the stage where it builds radio telescopes. But that doesn't mean it's not there, not thriving in its own slow way, not mattering in the cosmic scheme. The research station on Enceladus becomes the most important scientific facility in human history overnight, and the crew expands to 30, then 50, then 100 as modules and supplies arrive on every available trajectory, and they start building outposts on other moons. On Titan, where the methane seas might host entirely different chemistry. On Iapetus, where the dark material coating one hemisphere might be organic fallout from ancient impacts on Hyperion, whose spongy interior might harbour protected pockets of ancient ice, with their own fossil record, and each outpost becomes a node in a growing human network that mirrors the slow internet they're studying. Information flowing between stations, observations building on each other, patterns emerging from the collective data that no single team could see alone. The geologist's theory, recovered from the data cores, becomes the framework everyone uses. Enceladus is the heart. The shepherd moons are the circulatory system, the E-ring is the bloodstream, and every world in Saturn's system is an organ with its own function, its own contribution to the larger metabolism, and just as no single organ in a body can be understood in isolation. No single moon in Saturn's system can be understood without reference to all the others, to the flows of material and energy that connect them, to the history they share and the future they're building together. Someone calculates that if the process continues at its current rate, if the complexity they're observing keeps increasing, then in another 10 million years, some of these moons might host not just microbial colonies, but actual ecosystems with specialized organisms, maybe even something like multicellular life. And in 100 million years, who knows, maybe intelligence, maybe civilizations that will look up at their ringed sky and wonder what's out there, never guessing that their world and its neighbors are all part of a single, interconnected system that has been growing and evolving since before their planet's current orbit was established. The research teams start finding evidence of cycles, periods of high activity when Enceladus's plumes are stronger, followed by quiet periods when they nearly cease, driven by orbital eccentricities that vary over thousands of years, and they realise that these cycles themselves might be part of the selection process. That life in this system has to be adapted to feast and famine, to boom and bust, to waiting through dark periods and exploding during bright ones. And maybe that's another reason why it's so robust, because anything that survives here has already been tested by the harshest conditions imaginable. The Titan station starts reporting strange readings from the methane lakes, organic compounds at the bottom of Kraken Mare that look biological, but use a completely different solvent system than water-based life. And suddenly, there are two separate biospheres in Saturn's system, one based on water and ice, and one based on liquid hydrocarbons. And the question is whether they're related, whether organic material from Enceladus can rain down through Titan's atmosphere and seed the lakes below, whether there's exchange happening not just between water moons but across fundamental chemical divides, and if so, what kind of hybrid chemistry might emerge where the two systems overlap. The Jupiter team sends an update. They've found life on Europa, confirmed and undeniable, living in the ocean under the ice, and it's related to the life in Saturn's system, sharing enough genetic markers or chemical signatures that they must have a common origin, which means life doesn't just spread between moons within a single system. It spreads between systems, probably through asteroid impacts that launch material into solar orbit, and over billions of years those fragments can travel immense distances, can carry frozen organisms or at least frozen organic templates from Jupiter to Saturn to Uranus to Neptune and back again, making the entire outer solar system a single interconnected biosphere, a galactic-scale ecosystem held together not by proximity but by the patient exchange of materials across millions of years and billions of kilometres. The philosophical weight of this realisation settles over everyone slowly. Humans aren't discovering life. They're discovering life with a capital L, not as a phenomenon that happens in isolated pockets, but as a fundamental characteristic of the solar system itself, something that emerges wherever conditions allow and spreads through every available pathway, limited only by time and distance and the basic requirements of chemistry. And if this is true for our solar system, then it's probably true for every solar system, which means the universe isn't mostly empty space with rare islands of life. It's mostly life with rare islands of emptiness, and everywhere there's matter and energy and time. The slow, grinding process of chemical evolution is working toward complexity, toward organisation, toward something that eventually becomes aware of itself and starts asking questions about where it came from. The original pilot's observation, recovered from the final log entries, becomes the mission statement for everything that follows. We're not observers anymore, we're participants. We're part of the network now. Our ships and stations are nodes in the slow internet, and everything we do, every sample we take, every measurement we make, every piece of equipment we leave behind becomes part of the system's history, part of the data that future organisms or civilizations will have to interpret when they try to understand their own origins. And maybe that's okay, maybe that's inevitable, maybe the universe is full of civilizations that arose from chemistry that was accidentally cross-contaminated by previous civilizations, an infinite chain of influences stretching back to whatever the first life was, wherever it started, and maybe trying to be perfectly sterile is missing the point, because contamination is just another word for exchange, and exchange is how complexity grows, how systems become more than the sum of their parts. The research station on Enceladus celebrates its first full Saturn year of operation, 30 Earth years compressed into months of work that feels like decades, and they throw a party, awkward in low gravity, toasting with recycled water, while outside the plumes rise like clockwork, and someone says quietly that the original crew would have loved this, would have understood exactly what it means to watch the slow garden growing. And everyone is silent for a moment, thinking about the two explorers who gave everything to document the first evidence of the network, who became part of the ice they were studying, whose final samples are still yielding new discoveries 3 years later, and the station commander proposes a memorial. They'll place a marker at the coordinates where the suits were found, something permanent that will last for geological ages, and the inscription will be the geologist's final words from the data cache. Keep looking at the small moons, because that's where the real story is. And underneath, the pilot's final observation: "We found the garden, and it's bigger than we thought." The marker goes up during the next EVA, a pyramid of machined titanium embedded deep in the ice, and around it they scatter some of the last samples the original crew collected, returning them to the environment they came from, completing a circle. And as they work, someone notices that the ice around the marker is already starting to develop the same patterns they've been observing elsewhere. The same organising principles, as if the organic material in the samples is teaching the native chemistry new tricks. And maybe that's fitting. Maybe that's exactly how the network grows, through exchange and mixing and the patient accumulation of innovations that get passed from world to world, generation to generation, species to species, civilization to civilization, until the distinction between native and foreign stops mattering because everything is connected, everything is related, everything is part of the same ancient experiment that began when the first organic molecules formed in the first protoplanetary disk and has been running ever since, spreading through every available pathway, turning the universe slowly, patiently, inexorably into a garden. The 5th year of operations brings the first evidence that the network extends beyond what anyone imagined. When a research team analysing meteorite impacts on the outer Shepherd moons discovers organic signatures that don't match anything in Saturn's system, compounds with isotope ratios pointing to origins in the Kuiper belt, frozen travellers that spent millions of years crossing the outer solar system before finally arriving here, and the implications cascade outward, like rings from a stone dropped in still water. If material from the Kuiper belt can reach Saturn's moons, then material from Saturn's moons can reach the Kuiper belt, and material from Jupiter can reach both, and suddenly the slow internet isn't just connecting the moons of individual planets, but linking every icy world in the solar system into a single vast web of chemical exchange that's been operating since the solar system's formation. The team starts modelling the trajectories, calculating how long it takes for material ejected from Enceladus's plumes to escape Saturn's gravity well, how it spreads through interplanetary space, how some fraction of it eventually collides with other worlds, and the numbers are staggering. Over the 4 billion years since the solar system stabilised, trillions of ice grains have made the journey from each active world to every other world, carrying their cargo of organic chemistry, their frozen libraries of molecular information, and even though the vast majority are lost to space or fall into the sun, or impact airless bodies where nothing can use them, the tiny fraction that lands in favourable environments is enough, given geological timescales, to seed the entire solar system with the products of every successful chemical innovation that's ever occurred anywhere. They find confirming evidence in the Kuiper belt data from the New Horizons extended mission, spectroscopic signatures on distant dwarf planets that match compounds first identified in Europa's ocean, and the researchers realise with mounting astonishment that they're looking at a postal system that's been running for billions of years, letters written in chemistry mailed from world to world at speeds measured in kilometres per second, taking millions of years to arrive, but arriving nonetheless, and every recipient world that has the right conditions can read those letters, can incorporate the information they contain, can build on it and send new letters of its own. The philosophical implications keep expanding. If the solar system is one connected network, then other solar systems must be networks too, and over the immense stretches of galactic time, material ejected from one star system can eventually reach others. Panspermia, not as a rare accident, but as an inevitable consequence of stellar dynamics and the sheer patience of frozen chemistry. And maybe that's why life uses the same basic molecules everywhere researchers look. The same amino acids and nucleotide bases and lipid structures, not because these are the only possible solutions, but because they're the solutions that worked in some ancient system billions of years ago and have been spreading ever since, copied and modified and adapted but still recognisably descended from whatever the first successful chemistry was, wherever and whenever it emerged. The research program expands again, this time looking at the very oldest ices they can find, samples from the most ancient surfaces where material has been accumulating since the solar system formed, and in a preserved layer on one of Saturn's most distant irregular moons, captured long ago from a different orbit, they find organic compounds that predate the solar system itself, interstellar molecules that survived the nebula's collapse and the violent early period when planets were still forming. And these molecules carry their own story, hints of chemistry that occurred in the stellar nursery before. there were planets at all, and someone realizes they're looking at evidence of pre-solar networks, chemistry that was already sophisticated when the sun was born, that came from previous generations of stars and planetary systems, an inheritance that goes back not just billions of years, but potentially to the earliest epochs of the galaxy. A xenobiologist on the station starts calling it the galactic genome, the accumulated chemical knowledge of every successful origin of life that's ever occurred in the Milky Way, preserved in frozen grains that drift between stars. And while the information density is low and the transmission time is measured in millions of years and the error rate is astronomical, the system has been running for 10 billion years, and that's enough time for even the slowest network to build up a substantial library, to spread successful innovations across vast distances, to create a kind of chemical culture that transcends individual worlds and systems, and even individual epochs of star formation. The team starts looking for patterns in the distribution of organic compounds across different solar system bodies, trying to identify which innovations arose locally and which were imported, and they discover something unexpected. Certain complex molecules appear everywhere, on every world with the right conditions, but they always appear in the same sequence, as if there's a natural progression, a chemical ladder that systems climb one rung at a time, and this suggests that the evolution from simple organics to proto-life isn't random but follows predictable pathways constrained by thermodynamics and reaction kinetics, which means that anywhere in the universe with the right raw materials and energy sources is probably climbing the same ladder, possibly at different speeds, but following the same basic route. They test this hypothesis by examining the timeline of chemical evolution on different Saturn moons, comparing the progression on shepherd moons that have been in the E-ring for different durations, and the pattern holds. Younger exposures show simpler chemistry, older exposures show more complex chemistry, and the sequence is consistent, suggesting that given enough time and material input, all of these systems will eventually reach the same endpoint, whatever that endpoint is, whether it's simple, self-replicating chemistry or something more complex, something that might deserve to be called alive. The implications for the search for extraterrestrial intelligence shift dramatically. If simple life is essentially inevitable given the right conditions, and if those conditions are common, and if life follows predictable pathways, then the question isn't whether aliens exist, but what stage different worlds and systems have reached in their chemical evolution, and whether there are predictable barriers or filters that prevent most systems from progressing beyond certain points, and what it means that Earth somehow passed those filters while presumably countless other worlds didn't. A theoretical biologist proposes what she calls the patient universe hypothesis, that the galaxy is full of worlds at every stage of chemical evolution, from the simplest organic compounds to proto-life, to simple organisms to complex ecosystems to intelligence. And the distribution follows a predictable curve with vast numbers at the simple end and progressively fewer at each stage of increasing complexity, not because the later stages are impossible, but because they take time, enormous amounts of time, and most worlds simply haven't had enough time yet, and Earth's intelligence is either a statistical fluke, arriving unusually early, or there's something about Earth-specific conditions that accelerated the process beyond the typical rate. The research station starts receiving data from the first dedicated Uranus mission in decades, and the findings confirm the pattern. Uranus's moons show the same kind of chemistry, the same progression of complexity correlated with exposure to material from active sources, and while Uranus doesn't have an Enceladus equivalent that's currently active, there's evidence that Miranda was geologically active in the past, possibly seeding the system during that period, and even now material arrives from interplanetary space, from other systems, keeping the slow chemistry working even in the absence of a local source. The Neptune data follows within months. Triton, captured from the Kuiper belt and still geologically active with its nitrogen geysers, is running its own version of the experiment, and the chemistry there is sufficiently different, influenced by nitrogen rather than water as the primary volatile, that it represents a parallel pathway, a different solution to the same basic problem of how to build complexity in a cold environment, and the researchers realize they're not looking at one way to make life but many, a whole space of possibilities that different worlds explore depending on their specific conditions, and maybe that's the real answer to why the universe seems so empty of radio signals, because most life doesn't follow the same pathway Earth did, doesn't emerge in warm oceans under thick atmospheres on rocky planets in habitable zones, but emerges instead in cold oceans under ice shells in systems where sunlight is irrelevant, and the energy comes from tides and radioactivity, and those systems don't build radio telescopes because they don't have access to fire or metallurgy, or any of the technologies that require atmospheric chemistry, but they might still be alive, still conscious, still wondering if they're alone. Someone points out that humanity's presence in Saturn's system is itself becoming part of the network now, that the research stations are shedding organic compounds and metabolic byproducts, that the ships landing and taking off are distributing Earth chemistry across the moons they visit, and while the teams are trying to minimize contamination, complete sterility is impossible, which means in 1,000,000 years some future system, whether it's evolved from native Saturn chemistry, or from Earth contamination, or from some hybrid of the two, will find traces of human presence in the ice record and will have to interpret them. We'll have to decide whether these strange compounds indicate natural processes or artificial ones. And maybe they'll never know that they're the descendants, direct or indirect, of a process that humans accidentally accelerated by their simple presence. The ethical debates intensify. Should humanity try harder to prevent contamination? Should they abandon the research stations to preserve the natural evolution of Saturn's chemistry? Or is contamination inevitable and possibly even beneficial, a way of accelerating the slow internet, of providing new information to systems that might be able to use it? And maybe the whole concept of contamination is anthropocentric anyway, based on an outdated idea that each world's chemistry should be pristine and separate, when the reality is that worlds have been exchanging chemistry for billions of years, and Earth's contribution is just one more voice in an ancient conversation. The station commander makes a decision that surprises everyone. They're going to stop trying for perfect sterility. They're going to accept that humans are now part of Saturn's system, part of its metabolism, and instead of fighting that reality, they're going to study it, monitor how Earth chemistry interacts with native chemistry, see whether the hybrid systems that result are more or less complex than either parent system alone, treat the human presence as an experiment in accelerated exchange, and what happens when systems that evolve separately suddenly have access to each other's innovations, and maybe the results will tell them something important about how the slow internet works, about whether exchange always increases complexity, or whether there are conditions under which it causes interference instead. The next story is about to begin. Please relax and enjoy. The rain begins softly, a whisper against the window, and you stand beneath clouds so thick the afternoon feels like dusk. You know that above this grey ceiling, beyond the atmosphere's veil, there are not just stars, but suns. Countless furnaces of light, each burning with its own colour and tempo, each setting the rhythm for worlds you will never touch. Some blaze blue and fierce, living fast and bright. Others glow dim red, patient enough to outlast empires, galaxies, perhaps even time itself. And somewhere among them, on a world you cannot name, beneath a sky lit by a sun nothing like your own, someone might be standing as you are now, watching rain fall, wondering what lies beyond their clouds. In the cold depths between those distant suns, where starlight fades to nothing and the void stretches dark and infinite, there are clouds of a different kind. Molecular clouds, they're called. Great drifting masses of gas and dust, cold enough to freeze thought itself. Within these clouds, gravity works slowly, patiently, gathering material into knots the way a river gathers silt. Over millennia, these knots contract. The material falls inward, pulled by its own weight, and as it falls, it heats. Not quickly, not with flame or violence, but with the slow warmth of compression, the way your hands warm when you press them together. At the heart of each knot, something begins to glow, a protostar, barely visible through its cocoon of dust, surrounded by a disk of spinning material that will one day become planets, moons, asteroids, perhaps even life. You cannot see this process, of course. It takes millions of years, but imagine it anyway. The dust grains in that disk colliding and sticking, building pebbles from sand, boulders from pebbles, worlds from boulders. Jets of gas flicker along magnetic field lines, carrying away excess energy. The disk flattens as it spins, a cosmic phonograph record with the protostar as its needle. And all the while, the core grows denser, hotter, its atoms pressing closer together, their dance becoming frantic. Pressure mounts, temperature climbs, and then, at some threshold that cannot be predicted to the second but is nonetheless inevitable, hydrogen nuclei begin to fuse. The star ignites, light steadies, Outward pressure from fusion balances the inward crush of gravity, and the star joins what astronomers call the main sequence, the long, stable middle age during which most stars spend most of their lives. Where a star sits on that sequence depends entirely on its mass. Mass is destiny in the stellar world. A star with 10 times the Sun's mass burns blue-white and fierce, exhausting its fuel in mere millions of years. A star with a 10th, the Sun's mass glows dim red, and sips its hydrogen so slowly it could burn for trillions of years, longer than the current age of the universe, longer than any measurement of time that holds meaning for human minds. Between these extremes lie all the gradations, white stars and stars, yellow stars, orange stars and amber stars, each with its own rhythm, its own lifespan, its own way of shaping the space around it. When you look at a star, you are looking at a message written in light. That light, when passed through a prism or a spectrograph, splits into a spectrum, a rainbow marked by dark lines where specific wavelengths have been absorbed. These lines are fingerprints. Each element in the star's atmosphere absorbs light at particular wavelengths. Hydrogen leaves its marks, calcium its own, iron and sodium and helium each signing their presence in the starlight. By reading these lines, astronomers determine what a star is made of, how hot it burns, even how fast it moves. If a star is approaching, its spectral lines shift slightly toward the blue, if receding, toward the red. Tiny shifts, but enough to reveal motion across the galaxy, enough to detect the gravitational tug of unseen planets pulling their stars into subtle wobbles. Most of the suns in the galaxy are red dwarfs, small, cool, patient M-type stars that make up perhaps 70% of all stars, but contribute almost nothing to the visible light of the night sky. They are too dim to see without telescopes, most of them, but they are everywhere, scattered through space like seeds. A red dwarf might burn for 10 trillion years, releasing its energy so slowly that the universe will have changed beyond recognition before it finally exhausts its fuel. Their habitable zones, the orbital distances where liquid water could exist on a planet's surface, are close in, so close that planets there are likely to be tidally locked, showing the same face to their star forever, one hemisphere in eternal day, the other in eternal night. And red dwarfs are restless. Their magnetic fields churn and twist, producing frequent flares that flood their inner systems with radiation. Any world in the habitable zone of a red dwarf must endure this flickering violence, this temperamental light that might strip atmospheres away, or perhaps drive evolutionary pressures toward resilience. A step up in mass and you find K dwarfs, orange stars that glow soft and steady, cooler than the sun but not as cool as red dwarfs, longer lived but not as patient. K-type stars offer a middle path. They burn for tens of billions of years, long enough for countless chances at complexity, yet they are calmer than their smaller siblings, less prone to violent flares. Their light is warm, autumn-tinted, and their habitable zones are wide enough, stable enough, that planets there might enjoy billions of years of gentle, predictable daylight. Time enough for oceans to form and life to experiment, to fail, to try again. Then there are stars like the Sun, G-type yellow dwarfs that sit in a comfortable middle range. The Sun has been burning steadily for 4.5 billion years and has another 5 billion to go before it exhausts the hydrogen in its core. That is enough time for continents to drift, for species to rise and fall, for intelligence to emerge and wonder at the stars. G-type stars provide steady, bright light without the intense ultraviolet radiation of hotter stars or the temperamental flickering of cooler ones. They are Goldilocks stars, not too hot, not too cold, and their habitable zones are wide enough that planets can orbit at comfortable distances, spinning freely, enjoying day and night in regular cycles. But go higher in mass, and you find the fast burners, the A, B, and O stars that blaze white and blue. These are the stars that dominate star-forming regions, that sculpt nebulae with their fierce winds and ultraviolet light. They pour out energy at staggering rates, living only millions of years, sometimes only a few million, before exhausting their fuel. Around such stars, planets would be drenched in UV radiation, their atmospheres stressed, their surfaces harsh. There is little time for the slow work of evolution in such systems. By the time a world might settle into stable rhythms, its sun is already dying. All stars die, of course, but they die in different ways. When a star like the Sun exhausts the hydrogen in its core, Fusion slows and gravity begins to win again. The core contracts, heats, and hydrogen in a shell around the core begins to fuse instead. This shell burning drives the outer layers outward. The star swells into a red giant, its surface cooling and reddening even as its core grows hotter. Red giants are gentle in a way, luminous but diffuse, their outer layers so tenuously held that stellar winds carry gas into space, enriching the interstellar medium with elements forged in the star's interior. Carbon, nitrogen, oxygen, ingredients for future stars and planets, drift outward in slow exhalation. Some giants pulse, their outer layers expand and contract in regular cycles, driven by instabilities in the way light moves through those enormous cool atmospheres. Cepheid variables pulse with periods measured in days or weeks, their brightnesses varying so predictably that astronomers use them as cosmic yardsticks, measuring distances across the galaxy. Our Lyrae stars pulse faster, with periods of hours. Mirror-type giants pulse slowly, over months or years, their variability visible even to ancient watchers who saw them flare and fade in the night sky, mysterious breathing lights. Most stars are not alone. Perhaps half of all sun-like stars, maybe more, are in binary systems, two stars orbiting a common centre of mass. Some binaries are wide, the stars separated by hundreds of astronomical units, each evolving independently. Others are close, their mutual gravity reshaping them. In some systems, one star pulls gas from its companion, drawing material through an invisible bridge between them. This mass transfer changes both stars, altering their evolution, sometimes producing spectacular outbursts as stolen gas spirals inward and heats. In the closest binaries, both stars may be locked in tight embrace, whirling around each other in hours or days, their surfaces nearly touching, their atmospheres mingling. Stars are also born in families, open clusters, loose gatherings of a few hundred to a few thousand stars form together in molecular clouds and then drift apart over tens or hundreds of millions of years. Globular clusters are older, denser, ancient spheres containing hundreds of thousands or even millions of stars, relics from the early galaxy, orbiting the Milky Way's halo like loyal attendants. Because all the stars in a cluster formed at roughly the same time from the same material, clusters are laboratories for understanding stellar evolution. The most massive stars have already died. The smallest are still burning. By studying which stars remain and which are gone, astronomers piece together timelines of stellar life. Within each star's light is a record of its birth. Astronomers call elements heavier than helium metals, regardless of what they actually are. Carbon, oxygen, iron, all lumped together under that term. A star's metallicity tells you when it formed. The first stars, born in the pristine hydrogen and helium left over from the Big Bang, had almost no metals at all. When those stars died, they scattered heavier elements into space. The next generation of stars formed from slightly enriched gas. With each generation, the metallicity increased. Today's stars, formed from clouds enriched by billions of years of stellar death, carry the signatures of countless previous lives in their spectra. Low metallicity stars are ancient voyagers, time capsules from the early universe. High metallicity stars are recent arrivals built from the ashes of many predecessors. Stars also have weather. Rotation and convection in a star's outer layers generate magnetic fields, and those fields erupt through the surface in complex patterns. Sunspots are magnetic knots where the field suppresses convection, cooling the surface and creating dark patches. Flares are sudden releases of magnetic energy, flooding space with radiation and particles. Coronal mass ejections hurl billions of tons of plasma outward at high speed. All of this affects any planets orbiting the star. Planetary magnetic fields channel these particles toward the poles, producing auroras, curtains of light in the upper atmosphere. Over time, stellar winds can erode atmospheres, especially on planets without strong magnetic shields. The star's weather becomes the planet's destiny. We find those planets by watching the stars. When a planet crosses in front of its star from our perspective, the star's light dims slightly, a transit. By measuring the depth and duration of the dimming, astronomers determine the planet's size and orbital period. If the transit happens repeatedly, precisely on schedule, it confirms a planet is there. Sometimes, during a transit, starlight filters through the planet's atmosphere, and the spectrum of that light carries the chemical fingerprints of atmospheric gases, water vapour, methane, carbon dioxide. We are learning to read planetary atmospheres from trillions of miles away, to taste the air of worlds we will never visit. We also find planets by watching stars wobble. A planet's gravity tugs its star, pulling it into a small orbit around the system's centre of mass. As the star moves toward us and away, its spectral lines shift, Doppler shifts, the same effect that changes the pitch of a passing siren. By measuring these shifts over time, astronomers determine the planet's mass and orbit. Combined with transit data, this gives a complete picture: size, mass, density, orbit. Rocky worlds and gas giants, hot Jupiters hugging their stars and ice giants drifting far out, all revealed by the star's subtle dance. There are other methods, rarer but powerful. Direct imaging captures the light of giant planets orbiting far from their stars, young worlds still warm from formation. Gravitational microlensing detects planets by the way their gravity bends the light of a more distant background star, a fleeting alignment that might happen only once and never repeat. Astrometry tracks the star's position on the sky, measuring its motion over years or decades to reveal the pull of long-period companions. Each method has its strengths, its biases, its blind spots. Together, they map the diversity of planetary systems, and as we find these worlds, we ask, could they harbour life? The answer depends on their stars. A star's type sets the boundaries of its habitable zone, the range of distances where temperatures allow liquid water. Red dwarfs have narrow habitable zones close to the star, where planets might be tidally locked and battered by flares. K and G stars offer wider, calmer zones. Blue stars flood their surroundings with UV radiation and change too fast, dying before life has time to gain a foothold. But habitability is not just about water. It's about stability, about time, about the kind of light that falls on a world's surface and the rhythms that light imposes. Imagine standing on a planet orbiting a red dwarf. Noon might be copper-tinted, the sun a dim red disk hanging motionless in the sky if your world is tidally locked. One side of your planet bakes in eternal day, the other freezes in eternal night, and only in the twilight band between them, where winds howl from the heat toward the cold, might conditions be tolerable. Or imagine a world around a blue-white star, where daylight is icy pale and intense, where summers are fierce and brief, where the star's brightness fluctuates as it pulses through instabilities. The colour of daylight shapes vision, photosynthesis, the very chemistry of life. The length of day and year sets rhythms for behaviour, metabolism, sleep. All stars end. The smallest red dwarfs will burn until they have fused all their hydrogen, then cool slowly into hypothetical white dwarfs, a fate that awaits them trillions of years from now, so far in the future that it's uncertain whether the universe will still resemble anything we'd recognise. Sun-like stars swell into red giants, shed their outer layers as glowing shells called planetary nebulae, and leave behind white dwarf cores, Earth-sized embers, hot but no longer fusing, slowly cooling over billions of years. Massive stars die violently. When their cores run out of fuel, they collapse in milliseconds, triggering supernovae that outshine entire galaxies for weeks. These explosions forge the heaviest elements, iron, gold, uranium, and scatter them into space. The shock waves from supernovae compress nearby clouds, triggering new star formation. Death and birth intertwined, the galaxy recycling itself. Stars are also travellers. They form in nurseries, dense regions within molecular clouds, where dozens or hundreds of stars ignite within a few million years of each other. After birth, the stellar winds and radiation from the hottest stars disrupt the remaining gas, and the cluster begins to disperse. Some stars drift into loose-moving groups, sharing similar velocities as they orbit the galactic centre. Others scatter, becoming isolated field stars. The Milky Way is crisscrossed with stellar streams, trails of stars pulled from clusters or small galaxies by tidal forces, evidence of the galaxy's ongoing assembly. By mapping stellar motions, ages and compositions, astronomers reconstruct the Milky Way's history, tracing merger events, identifying in falling satellites, watching the slow churn of galactic evolution. The rain continues, steady now, and you think about how strange it is that you can know these things. That light, travelling for years or centuries or millennia, carries information encoded in wavelengths and intensities, and that human minds, evolved to navigate savannas and recognise faces, can decode that information, can reconstruct the lives of suns they will never see up close. Behind the clouds above you, the sun is setting, though you cannot see it. And beyond the sun, thousands of light years away, a red dwarf is flaring, its planets huddled close, their atmospheres straining. A K-type star rotates slowly, its habitable zone calm and wide, its world cycling through gentle seasons. A binary system exchanges gas in a glowing stream. The Cepheid variable swells and contracts, its light pulsing like a heartbeat visible across the galaxy. A blue supergiant burns through its final reserves, months or years away from its explosive end. You will never visit those places. No one alive today will. But you can know they exist. You can understand, in outline if not in detail, the forces that shape them, the physics that governs them, the timescales on which they change. You can look at the spectra of stars and read their compositions, their ages, their motions. You can watch a star dim and know a planet has passed in front of it. You can measure a star's wobble and calculate the mass of an unseen companion. These are not small achievements. They are evidence of something remarkable about intelligence, about curiosity, about the human refusal to accept the night sky as mere decoration. The galaxy is full of quiet hearts. Most stars burn unnoticed, too dim or too distant to catch the eye. They do not care whether anyone watches them. They fuse hydrogen into helium, helium into carbon, some of them carbon into heavier elements still, following the logic of nuclear physics with no awareness, no intention, no purpose beyond the balance of gravity and pressure. And yet they create the conditions for everything else. They forge the elements that make planets, atmospheres, oceans, life. They provide the energy that warms worlds, that drives weather, that powers photosynthesis and all the cascading complexity that follows. They set the clocks by which days and years are measured, the rhythms to which life adapts. You think about the first humans who looked up and wondered what the stars were. They made stories, connected dots into constellations, imagined the stars as distant fires or holes in the sky or the eyes of gods. They had no way to know the truth was stranger and more beautiful than any story, that each star was a sun, that some had planets, that those planets might have weather and seasons and perhaps even life, looking back across the light years with their own questions. For most of human history, the stars were unreachable, unknowable. Now we reach them with light. Spectroscopy and photometry, interferometry and astrometry, all the ways we've learned to extract meaning from photons that have travelled unimaginable distances. The rain is easing now, the clouds beginning to break. A patch of sky appears, still bright with late afternoon light. No stars visible yet, but they are there. They are always there. Tens of billions of them in this galaxy alone, each with its own story written in light, its own cycle of birth and death, its own contribution to the slow alchemy that turns hydrogen into everything else. Some are giants, luminous enough to be seen across the galaxy. Some are dwarves, invisible beyond a few light years. Some are young, still surrounded by the disks from which planets are forming. Some are old, white dwarfs cooling in the dark, or neutron stars spinning in silence, or black holes marking where the most massive stars once burned. And around some of those stars, around how many, we still don't know, there are worlds. Rocky worlds and gas giants, ice giants and lava worlds, planets with thick atmospheres and planets with none. Worlds where volcanoes erupt under red light, where oceans freeze and thaw with the star's brightness, where storms rage for centuries, where surfaces are scoured by radiation or sheltered by magnetic fields. Worlds where maybe life has emerged, simple at first, perhaps staying simple, perhaps evolving into complexity, perhaps achieving intelligence, perhaps looking out at their own night sky and wondering, as you're wondering now, what lies beyond. You cannot know if anyone is out there looking back. The distances are too vast, the timescales too long, the chances too uncertain. But the question itself is worth holding. It changes how you see the rain, the clouds, the patch of clearing sky. It reminds you that you are standing on a planet orbiting a G-type star, that this star is one of hundreds of billions, that each of those stars has its own character, its own rhythm, its own influence on the space around it. It reminds you that the universe is not a static backdrop but a living system, constantly changing, constantly creating new conditions, new possibilities. The rain stops, the clouds drift east, the first stars appear, faint against the still bright sky, growing more visible as twilight deepens. You do not know which ones have planets, which ones are red dwarfs or blue giants or yellow dwarfs like the sun. But you know they are all suns, all burning, all shaping the worlds that orbit them. Their quiet hearts beat in fusion rhythms, setting the time for everything that happens near them, and their light, filtered through space and time, tells you their stories, stories written in spectra and brightness variations, in wobbles and transits, in the elements they forge and the winds they blow and the ways they change the darkness around them. You stand there a little longer, watching the stars appear, thinking about all those distant suns and the worlds that circle them, the rhythms they set, the possibilities they hold. The air has grown cold, the kind of cold that settles after rain, when moisture still clings to everything and the earth releases its stored warmth into the clearing sky. You can smell the wet pavement, the soil, the faint green scent of plants breathing in the dark. These are the smells of a world shaped by a particular star at a particular distance, with a particular atmospheric composition and magnetic field and axial tilt. Everything about this moment, the temperature, the oxygen you breathe, the water that just fell from the sky, exists because of where Earth sits in the sun's habitable zone, because of how the sun burns, because of what the sun is. But you are thinking beyond this world now. You are thinking about those planets around red dwarfs, where the habitable zone is so narrow that a planet must orbit its star in a matter of days or weeks, so close that tidal forces lock one face eternally toward the dim sun. On such a world, there would be no sunrise, no sunset, no daily cycle to mark time. The star would hang fixed in the sky, a dull ember casting long shadows, and everything would arrange itself according to that geometry. Weather patterns flowing from the hot side to the cold, ecosystems clustering in the twilight regions where temperatures are tolerable, evolution proceeding under constraints utterly unlike those on Earth. If intelligent life arose there, what would they make of their sky? Would they even think to look up? Or would their attention always be drawn horizontally toward the terminator where day meets night, toward the liminal spaces where their world is most habitable? And what of the planets around K-dwarfs, those patient orange suns? There, days and nights would cycle normally, but everything would happen more slowly, more gently. The star would live longer than the sun, offering more time for complexity to develop, for ecosystems to mature, for intelligence to emerge and build and wonder. The light would be warmer, more amber than Earth's sunlight, and photosynthesis might work differently there. Plants and algae tuned to a spectrum shifted toward the red. Autumnal light, year-round, never harsh, never scorching. A world like that might be gentler than Earth, its weather less violent, its seasons more measured. Or perhaps not. Perhaps the slower stellar winds would allow thicker atmospheres to accumulate, turning such worlds into pressure cooker greenhouses. Or perhaps the stability would breed stagnation, ecosystems settling into equilibria that resist change. You try to imagine what it would be like to live under a blue sun, an A-type or B-type star burning bright and hot. The light would be strange, pale and intense, flooding the world with ultraviolet radiation that would require any life to develop sophisticated protective mechanisms. Thick ozone layers, UV-absorbing pigments, perhaps living underground or underwater during the star's brightest hours. The star itself would be young, a few million or tens of millions of years old at most, and in another few million years it would begin its death throes, swelling and brightening and finally exploding. There would be no deep time on such a world, no billions of years for evolution to tinker and refine. Any life there would have to arise quickly, adapt quickly, live quickly, always under the ticking clock of the star's inevitable end. Perhaps that urgency would drive rapid evolution, or perhaps it would make complexity impossible, life never able to gain more than a fragile foothold before being erased. These thoughts lead you to consider the planets that orbit binary stars, those systems where two suns share the sky. Some of these systems are widely separated, with planets orbiting just one star while the companion shines as a brilliant point of light in the sky. A second sun that never rises or sets, just slides along its slow path through the constellations. But in closer binaries, planets might orbit both stars in figure-8 or circumbinary orbits, and there the sky would be truly alien. Two suns rising at different times, casting double shadows, their combined light shifting in colour and intensity as their orbits bring them closer and farther apart. Eclipses would be common, one sun passing in front of the other, the world plunged into partial darkness in the middle of the day. Seasons would be chaotic, unpredictable, governed not by axial tilt alone but by the complex gravitational dance of two stars pulling the planet along elliptical paths. What kind of life could evolve under such conditions? What kind of calendars would such a civilization develop? What kind of myths would they tell about their twin suns? The sky is darker now, the stars more numerous. You recognise a few constellations, Orion rising in the east, the Pleiades higher up, their clustered stars so young they still glow blue, having formed only 100 million years ago, cosmic infants. The Pleiades are sisters in more than mythology. They truly were born together, condensing from the same molecular cloud, and they still travel together through space, their motions linked. In a few 100 million years they will drift apart, scattered by gravitational interactions with other stars and giant molecular clouds, each sister going her own way, their family dissolved into the wider population of the galaxy. But for now they remain together, a visible reminder that stars have histories, relationships, origins. You think about the globular clusters you cannot see, those ancient spheres of stars orbiting the Milky Way's halo, each cluster containing hundreds of thousands of stars packed into a sphere only tens of light years across. The stars there are old, 10 billion years or more, formed when the galaxy itself was young. In the core of a globular cluster, stars are separated by only light weeks or light months instead of light years, and their sky would be filled with bright stars, hundreds of them as bright as Venus appears from Earth, the night never truly dark. But those stars are metal poor, forged before the galaxy had been enriched with heavy elements, and it is unclear whether planets could even form around them, whether there is enough silicon and iron and carbon to build rocky worlds. Perhaps life in globular clusters is impossible, or perhaps it is merely different based on chemistry we have not imagined. The thought of alien chemistry leads you down another path. Life on Earth is based on carbon, water, and a few dozen other elements, all forged in stars and scattered by supernovae. But the availability of those elements varies across the galaxy. Stars formed in the outer regions of the Milky Way, far from the dense star-forming regions of the spiral arms, are metal poor. Stars formed near the galactic centre, where star formation has been intense and supernovae frequent, are metal rich. Does this mean life is more common in some regions than others? Are there galactic habitable zones, not just stellar ones, regions where the density of heavy elements is high enough to form rocky planets, but not so high that the star formation rate produces too many supernovae, sterilizing nearby systems with gamma rays and cosmic rays? And what of the elements themselves? Every atom of carbon in your body was forged in the core of a red giant, where helium nuclei fuse together in the triple alpha process, a reaction so delicate that it requires a precise resonance. In the carbon nucleus, a quantum coincidence that seems almost designed to allow carbon's existence. Every atom of oxygen came from heavier stars, where neon and magnesium burning produced oxygen as a byproduct. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all of it created in the cores of massive stars, then ejected in supernova explosions, spreading through the interstellar medium, mixing with hydrogen and helium, eventually collapsing into new stars and new planets. You are quite literally made of stars your atoms cycled through multiple generations of stellar birth and death, before finally assembling into the form standing here under the clearing sky. This recycling is ongoing. Right now, somewhere in the galaxy, a star is exploding, and in the heat and pressure of that explosion, nuclei are being slammed together to create elements that do not exist elsewhere. Elements heavier than iron, like gold and platinum and uranium. Those elements will drift outward in an expanding shell of gas and dust, cooling as they go, eventually encountering a molecular cloud. The shock wave from the supernova will compress the cloud, triggering new star formation, and some of the heavy elements will be incorporated into the next generation of stars and planets. In this way, the galaxy gradually becomes more metal-rich over time, each generation of stars chemically distinct from the last, a slow enrichment that has been ongoing for more than 10 billion years. You wonder if there are planets where life developed earlier than on Earth, around stars formed when the galaxy was younger, its metallicity lower. Would such life be fundamentally different, working with a more limited palette of elements? Or would the same chemistry prevail, carbon and water and oxygen forming the backbone of biology everywhere, regardless of when the planet formed? And what of life that might develop later, billions of years from now, on planets around stars not yet born, formed from clouds enriched by countless more generations of supernovae? Would those organisms have access to heavier elements in such abundance that their biochemistry could explore possibilities unavailable to Earth life? The temperature continues to drop. You can see your breath now. Faint wisps of vapour catching the last light from the western horizon. Water vapour, H2O, 2 hydrogen atoms and 1 oxygen atom. The former from the Big Bang, the latter from a long-dead star. This simple molecule, so common in the universe that it forms vast clouds in space and ice mantles on interstellar dust grains, is the medium of life on Earth and likely on many other worlds. But water is strange. It expands when it freezes, making ice float, a property that keeps Earth's oceans from freezing solid from the bottom up, allowing life to persist through ice ages. It has a high heat capacity, moderating temperature swings. It is an excellent solvent, allowing the chemistry of life to proceed in liquid form. These properties are consequences of water's molecular structure, the way oxygen hogs electrons and gives the molecule a lopsided charge distribution, allowing water molecules to hydrogen bond to each other. Would alien biochemistry necessarily use water, or are there other solvents, ammonia, methane, even liquid methane on cold worlds like Titan, that could serve the same purpose? You shake your head, smiling at the way your thoughts spiral outward, each question leading to more questions, the universe revealing itself as infinitely more complex and strange than you can fully grasp. But that is the joy of it, is it not? That there is always more to learn, more to wonder about, that every answer opens new mysteries. The stars above you are not just points of light but puzzles, each one a laboratory, running experiments in nuclear physics, hydrodynamics, magnetohydrodynamics, each one producing conditions that do not and cannot exist on Earth. By studying them, by analysing their light and tracking their motions and modelling their interiors, astronomers are doing more than cataloguing the cosmos. They are learning the fundamental rules that govern matter and energy, the constraints within which everything, stars, planets, life intelligence, must operate. And now, finally it is fully dark, the clouds entirely gone, the sky a deep blue-black scattered with stars. You pick out a few more constellations, Cassiopeia, Andromeda, Perseus, and you remember that the faint smudge near Andromeda, barely visible to the naked eye, is not a star at all but another galaxy, M31, the Andromeda Galaxy, a spiral like the Milky Way, containing hundreds of billions of its own stars, its own molecular clouds, its own planets, and perhaps its own instances of life and intelligence. That galaxy is 2.5 million light-years away, meaning the light you see left there 2.5 million years ago, when the first members of the genus Homo were beginning to walk upright on the African savanna. You are seeing Andromeda not as it is now, but as it was then, and if anyone in Andromeda is looking back at the Milky Way, they are seeing it as it was 2.5 million years ago, long before humans existed. This time delay, this light travel time, means that the universe you perceive is not the universe as it exists in some objective now. There is no universal now. Every star you see is a message from the past, some more distant than others, and the farther you look, the further back in time you see. The most distant objects visible to telescopes, galaxies near the edge of the observable universe, are seen as they were more than 13 billion years ago, when the universe itself was young, when the first stars were just beginning to form. Those galaxies may no longer exist, their stars long since burned out or collapsed into black holes, but their light is only now reaching us, ghosts from a universe that no longer exists in the form we perceive. You turn your gaze back to the nearer stars, the ones you can see without a telescope. Sirius, the brightest star in the night sky, is only 8 light-years away, close enough that its light is recent, showing you the star almost as it is now. Betelgeuse, in Orion's shoulder, is a red supergiant, bloated and unstable, somewhere between 400 and 600 light-years away. When you see it, you're seeing it as it was in the 1400s or 1500s, during the Renaissance, and it is possible, unlikely but possible, that Betelgeuse has already exploded, that the shockwave and light from that explosion are racing toward Earth right now, unseen, and will arrive tomorrow or next year or 100 years from now, suddenly making Betelgeuse as bright as the full moon for weeks or months before it fades. No one knows when Betelgeuse will explode, only that it will, that it is near the end of its life, that its core is a tangle of fusion shells burning different elements, the star struggling to maintain equilibrium as gravity tries to crush it, and fusion pressure tries to blow it apart. When Betelgeuse does explode, it will be spectacular. For a few weeks it will outshine every other star in the sky except the Sun. Ancient records will be searched for omens and myths, new ones will be created, and astronomers will point every telescope on Earth and in space at it, capturing data about a supernova closer than any in recorded history. The explosion will create a neutron star or perhaps a black hole, and it will seed the interstellar medium with new elements, enriching the clouds from which future stars will form. And then, over tens of thousands of years, the ejected material will expand and cool and fade, leaving behind only a faint nebula and the compact remnant, and the constellation of Orion will be subtly different, one of its brightest stars gone, replaced by a dimmer point, a stellar remnant barely visible except in infrared or X-ray wavelengths, the ghost of a giant that once was. You realize that you have been standing outside for longer than you intended, that the cold has worked its way into your fingers and toes, but you are reluctant to go inside just yet. There is something about this moment, this particular arrangement of sky and thought and silence, that feels important to hold on to. The stars have always been there, of course, every night of your life, every night of every human life that has ever been lived. But how often do you actually look at them, actually think about what they are? How often does anyone? Modern life pulls attention downward and inward, to screens, to immediate concerns, to the small sphere of influence that defines daily existence. The stars become backdrop, decoration, something noticed only in passing if at all. But they deserve more than passing notice. Each one is a story, a process, a set of conditions playing out over timescales that dwarf human comprehension. That red point of light low on the horizon might be a dying star, swollen and cool, in its last million years before shedding its outer layers. That white point might be a young star, still surrounded by a disk of planet-forming material, worlds coalescing from dust even now. That steady yellow point might be hosting a planet where rain is falling, where oceans are stirring, where something lives and moves and perhaps even thinks. You cannot know, the distances are too great, the observations too difficult. But the possibilities are there, written into the physics of stars and planets, statistical inevitabilities emerging from the vast numbers involved. The Milky Way itself is visible now, a faint band of light arching overhead, dense in some regions and sparse in others. You are looking edge-on into the disk of the galaxy, seeing the combined light of billions of stars too distant to resolve individually. The dark patches are not empty space, but dust clouds, regions where new stars are forming, blocking the light of stars beyond. The brightest regions are the spiral arms, where star formation is most active, where massive blue stars light up their surroundings before dying young. The galaxy is rotating, all these stars orbiting the common centre where a supermassive black hole, weighing millions of solar masses, sits quietly, its gravity holding everything together. The Sun orbits that centre once every 230 million years or so, a galactic year, and it has completed about 20 such orbits since it formed. 20 trips around the galaxy during which continents have assembled and broken apart. Species have risen and gone extinct. The whole drama of Earth's history replaying 20 times over while the Sun traces its vast circle. And the galaxy itself is moving, falling toward the Andromeda Galaxy under mutual gravitational attraction. In about 4 billion years, the two galaxies will collide, though collide is perhaps the wrong word. since stars are so widely separated that actual stellar collisions will be rare. Instead, the galaxies will pass through each other, their gravitational interactions flinging stars into new orbits, triggering bursts of star formation as gas clouds collide and compress, eventually merging into a single larger galaxy. The Sun will likely survive this encounter, though it might be flung into a different orbit, perhaps farther from the galactic centre, perhaps closer. Earth might survive as well, or it might not. By then the Sun will be well into its red giant phase, and Earth's fate depends more on the Sun's evolution than on the galactic merger. But the night sky, 4 billion years from now, will be dramatically different. Andromeda no longer a distant smudge, but a vast band of light dominating half the sky, its stars mingling with the Milky Ways, the whole system in glorious chaos. You find yourself wondering what humans, or whatever humans become, will make of that sky. Will there still be observers, still beings capable of looking up and understanding what they see? 4 billion years is a long time, longer than life has existed on Earth, long enough for evolution to produce outcomes utterly unlike anything alive today. Or perhaps intelligence will have moved beyond biological substrates entirely, uploaded into machines or distributed across networks spanning star systems, no longer bound to planets or even to matter as we understand it. Or perhaps intelligence will have destroyed itself, a brief flicker in cosmic time, leaving Earth silent again, its atmosphere gradually stripped away by the aging sun, its oceans boiled off, its surface eventually sterilized and dead. There is no way to know. The future is not written in the stars, only probabilities and possibilities, the outcomes of processes too complex to predict in detail. But standing here now, under these stars, you feel a strange sense of continuity with all the other humans who have looked up and wondered. Ancient astronomers tracking the movements of planets, trying to predict eclipses and conjunctions. Medieval scholars debating the nature of the celestial spheres, whether the stars were holes in a crystalline dome or distant suns. Renaissance observers peering through the first telescopes, discovering moons around Jupiter and phases of Venus, realizing that the Earth was not the centre of everything. Victorian spectroscopists analysing starlight, discovering that the same elements present on Earth existed in the stars, that the universe was made of comprehensible matter following comprehensible laws. 20th century astronomers discovering the expansion of the universe, the cosmic microwave background, the acceleration of that expansion driven by something called dark energy that no one yet understands. And now, 21st century observers finding planets around other stars, measuring their atmospheres, searching for biosignatures, beginning the long process of determining whether life is common or rare, whether intelligence is inevitable or unlikely. Each generation builds on the work of previous generations, the accumulation of knowledge a long collaborative project spanning centuries, millennia. No one person understands all of it. The universe is too large, too complex, the details too intricate for any single mind to hold. But collectively the species knows more than it ever has, and that knowledge continues to grow, every new telescope revealing new puzzles, every new measurement refining our understanding or overturning old assumptions. It is a hopeful thought in a way. Despite everything, despite wars and famines and plagues, despite the petty cruelties and grand tragedies that fill human history, there has always been this thread of curiosity, this drive to understand, to look beyond the immediate and grasp at larger truths. The cold is becoming uncomfortable now, insistent. You stamp your feet, blow on your hands, knowing you should go inside but still reluctant to leave. Above, the stars continue their slow procession across the sky, rising in the east and setting in the west, the apparent motion caused by Earth's rotation, the planets spinning beneath the fixed stars. Except the stars are not fixed at all. They are all in motion, orbiting the galaxy, some moving faster and some slower, some heading toward the galactic centre and some away, the whole system in constant flux. The constellations you see are temporary arrangements, patterns that happen to exist now, but will change over thousands and millions of years as the stars drift relative to each other. The Big Dipper will not always look like a dipper. Orion will not always look like a hunter. The sky is not static but evolving, and if you could watch it in fast forward over millions of years, you would see the stars sliding past each other like boats on a river, the familiar patterns dissolving and new ones forming, the sky continually remaking itself. You think about the people who will stand here in the future, 1,000 years from now, 10,000, 100,000. Will they still look up? Will they still wonder? Or will the stars have become so familiar, so mapped and catalogued and understood that they lose their power to inspire awe? You hope not. You hope that no matter how much is learned, there will always be deeper questions, mysteries that retreat as you approach them, phenomena that surprise and confound. The universe seems constructed that way, every answer revealing new questions, every solved puzzle showing 10 more waiting behind it. Quantum mechanics and general relativity, the two most successful theories in physics, are incompatible with each other, both correct within their domains but unable to be unified into a single framework. Dark matter and dark energy together make up 95% of the universe's mass energy, and no one knows what they are. The fundamental constants of physics, the speed of light, the strength of gravity, the charge of the electron, have the values they have for no known reason, and if they were even slightly different, stars could not form, chemistry could not work, life could not exist. Are those constants truly constant, or do they vary across space and time? Are there other universes where they have different values? And if so, are those universes real in the same sense this one is? Or are they mathematical abstractions, hypotheticals that exist only in equations? These questions have no answers yet, may never have answers, but they are worth asking. They frame the boundaries of knowledge, the places where understanding fades into speculation and philosophy, and they remind you that for all humanity has learned, the universe remains fundamentally mysterious, its depths unexplored, its possibilities vast. Standing under these stars, you are standing at the edge of the known world, looking out into darkness that is not empty but full of stars too distant to see, galaxies beyond counting, structures and phenomena that do not yet have names. And somewhere in that vastness, perhaps, others are standing as you are, looking up at their own skies, wondering about the nature of things, asking the same questions in different languages, seeking the same understanding. The thought makes you feel both small and connected. Small because you are one organism on one planet, orbiting one unremarkable star in a galaxy, containing hundreds of billions of stars in a universe, containing hundreds of billions of galaxies, and connected because that very awareness, that ability to comprehend scale and distance and time, is itself remarkable, a product of 4 billion years of evolution, producing nervous systems complex enough to model the universe, to hold abstractions, to wonder about things far removed from immediate survival needs. Consciousness is rare, as far as anyone knows, possibly unique to Earth, possibly scattered across the galaxy, possibly common but never long-lasting, each instance flickering briefly before extinction. But however rare it is valuable, this capacity to know and question and care. It is what allows the universe to know itself, to examine its own structure and history, to ask why it exists and whether it means anything. You do not have answers to those questions, and you suspect no one does. But you have this moment, this experience of standing under stars on a cold night after rain, your mind full of thoughts about fusion and gravity and time, your body full of atoms forged in stars, your consciousness a brief eddy in the flow of matter and energy that constitutes the universe. It is enough. It has to be enough. The stars do not care whether you understand them, do not notice your attention, will continue burning long after you're gone. But you are here now, aware and alive, capable of appreciating them, and that seems like something worth protecting, worth preserving, worth passing on to whatever comes next. Finally, because you must, you turn away from the sky and walk toward the warmth and light of your home, but you carry the stars with you, their quiet light imprinted on your thoughts, their distant fires still burning in your mind. Tomorrow the rain might return, the clouds might cover everything again, and you will go about your day without thinking of stars at all. But they will still be there, above the weather, beyond the atmosphere, burning steadily in the dark, red dwarfs and blue giants, yellow stars and orange stars, binaries and variables, clusters and streams, all the quiet hearts of other suns, all the possibilities they hold, all the worlds they warm, all the stories they tell to anyone willing to listen.